Hello, everyone. Welcome to the 11th edition of the IEEE CASW Rio Grande do Sul workshop and the third edition of Young Professional Workshop. It's a pleasure for me and Guilherme Paim to be here today was general chairs of these amazing workshops. This slide shows the entire organization team, and in advance, we would like to thank you all. Without your help, you wouldn't be here today. So thank you very much again. Now, I would like to invite the CASW program chairs, Professors Leandro Rocha from IEEE and Alessandro Girardi from Unipampa, to present the complete scheduling of this edition.
So good morning, everyone. Thank you for attending to this CAS workshop. Let me just share our here. So let's see if it's okay. So welcome officially for the 11th IEEE Circuits and Systems workshop. I am Leandro Rocha, and I will be one of the program chairs of this event, along with Alessandro Girardi, my colleague. And during this program, during this event, we have scheduled some events, some activities. And let me just go through a very brief program overview of what we are going to see during this program. So today we have 4 talks from Felipe Rosa, Hussam, Amrouch, Jorge, Castro-Godínez, and Jimmy Tarrillo. And at the end of the day, we have the poster session. Tomorrow, we have a talk starting with Felipe França, Abby Friedman, George Tonfat, Yarjuna Mandanayaki. And then we have the final poster session for this event. And finally, on Friday, we have 2 talks from Ibu Fan and Helmut Grab. And in the afternoon, we have the Young Professionals Workshop. I hope that you have a very nice event and that you enjoy a lot what we have prepared for you as of now. Enjoy the event.
Thank you, Leandro. Now, the poster chairs, Professor Leonardo Soares from IEEE and Alan Rossetto from FEPEL will present the detailed information about the poster sessions.
Good morning, everyone. I'm Leonardo Soares, and it's my pleasure to present to you the poster session program. So I'd like to thank all the authors for the submissions, where we achieved 40 posters to this year event, covering very interesting topics. And more specifically, the presentations were organized in 4 sessions, starting today at 4 p.m. with the session 1, covering topics like approximate computing, machine learning circuits and algorithms, logic synthesis, system on chips, and FPGA designs. The second section scheduled to occur today will cover topics on approximate computing, digital design for low-power circuits, digital signal processing applications, and video coding. Tomorrow, we will have 2 more sessions, with the third session starting at 4 p.m., covering topics on analog design, circuit testing, and electrical characterization. And finally, the last session of tomorrow will cover topics on EDA and fault-tolerant circuits. More information about the program can be found on the conference website. I would like to strongly recommend you to attend this great opportunity to improve our knowledge. I would like to invite Alan to say some words, and thank you for attention.
Okay, thank you, Leonardo, for the introduction. And first, I would like to thank the authors for considering the CAST workshop for submitting their work. And a special thanks I give to the board of the reviewers who helped us to review the posters and provided valuable comments and suggestion to the authors, and they certainly helped to improve the quality of the works that will be presented here today. Thank you all, and enjoy the event and enjoy the poster sessions.
Thank you, Leonardo and Alan. Please, we would like to invite the young professional chairs, Professor Caleb Mikael from IFSU and Israel Lopes from CERMA, for presenting the planned activities for young professionals workshop.
Hi, everyone.
Hello.
Hello. Hello, everyone. My name is Israel Lopes, and me and Caleb are going to present the younger professionals of this year, whose the theme is advices for a successful career. When we think about successful career, we usually think about hard skills, but currently something that has been talked a lot recently is about soft skills that, besides of the hard skills or technical skills, are more human skills and something that's not related to the subject of the work itself, such as communication, networking, proactivity, and stuff like that. And then we will start covering different aspects of the process of searching for a job. So here is the program. As we can see, we will start talking about how to highlight the soft skills in a CV. That's the first process of looking for a job. This video will be presented by Tamara Andrade. Then we will provide reports of experiences of professionals from companies from all over the world, from different companies of the world. That will be very interesting. Where they will explain what was the impact of a presence or a lack of soft skills in their careers. And then after that, we will have the presentation of professors to explain the importance of soft skills on the academia. We will start with a video from the Professor Cristina Meinhardt, then the Professor Leomar Rosa, and finally the Professor Ricardo Reis. Then, finally, there will be a roundtable, a podcast roundtable, led by Gustavo Wilk. Also, the guests Graciele Poussier, Guilherme Flack, and Arthur Linareto, that will discuss current topics and hot topics related to soft skills on industry and also academic and so on. So thank you so much for your attention, and I hope you have a great event, and thanks so much. Bye.
Thank you, Israel. Finally, we would like to invite the CAST chapter president, Professor José Rodrigo Azambuja from URGS.
So good morning, everyone. Good afternoon, Alexandra, Guilherme, thank you, and all the organizing committee of CASW in its 11th edition. So on behalf of IEEE Circuits and Systems Society Rio Grande do Sul, I would just like to invite you all to this 3-day event that is CASW. I know that Alexandra and Guilherme and the whole committee spent a whole lot of time in organizing this event during this pandemic. It is actually the second edition, pandemic edition of CASW. So I wish everyone a great event. We have some great talks, as they just said. So welcome, everyone, and I'll see you in a few days. So thank you, Alexandre.
Thank you, José. So, on behalf of the organizing committee, we would like to thank all the speakers for accepting our invitation, the technical committee for poster reviews, and all the participants. Enjoy the event. Now I will pass the word for the session chair of the first talk. Professor Leandro, please.
So let's start with our event today, and our speaker for today is Felipe Rosa. Let me just add. Felipe was born in Porto Alegre, in the southernmost Brazilian state, Rio Grande do Sul. He holds a PhD in microelectronics and Bachelor of Computer Engineering degree from the Federal University of Rio Grande do Sul. Felipe participated in the BRAFTEC, studying in the Bachelor's of Engineering, Microelectronics and Automation from July 2012 to July 2013 at the École Polytechnique Universitaire de Montpellier. In parallel, he was an undergraduate research intern at the Laboratoire d'Informatique, Robotique et Microélectronique de Montpellier. In 2015, he was accepted to a one-year exchange at the University of Leicester at the postgraduate level in the engineering department. He researched the reliability of many core embedded systems using virtual platforms. Additionally, during this period, he worked as a software engineer at Impera Software Limited, incorporating performance estimation tools in its commercial engine. Felipe is currently a senior modeling engineer at ARM Cambridge, UK. His main work projects include system interconnections, example CMN600 and CI700, and platform integration such as Total Compute FVP. Thank you, Felipe, for accepting giving this talk at the CASW, and the floor is yours.
Thank you, Leandro. Thank you, everybody. Thank you for the invitation from the committee, inviting me to be the first presentation. I'm gonna share my screen now. Share my screen. Hopefully, you'll be able to see my presentation. So today I'm here to talk in my name and not represent ARM in any way. Most of this work was developed during my bachelor degree and PhD, where we had some collaboration with the company, but not supported fully by the company. So just a disclaimer. So the point of my talk today is to demonstrate that people can use high-level simulation to do a large number of simulations in a short time of period of time without having to research a lot of cluster or AWS time. So that's my point today. So why I'm talking about FPs. So this is basically my career path in the last 9 years. Since I met Dr. Ricardo Reis and Luciano in 2012, I started working with them. And since the first day, I work with virtual platforms. I work with several virtual platforms in different levels, different architectures, from IoT to large-scale systems. So I think I have a good enough knowledge on this background, so I can pass to you and help you to have new ideas to use virtual platforms to accelerate your research or do a better presentation during a class or anything that you can use simulation. So I work in ARM for the last 3 years, and that will be the last part of my talk, trying to talk about what I'm doing now and the project that we are doing with some partners that are public. So let's think what we are trying to achieve. Let's take the concept of a smartphone. A smartphone, it's a consumer good that takes several steps to reach the final user. And usually, if you're thinking in sequentially, this is not the reality, but if you think sequentially, you can have concept, you need to have a specification where you have a document describing what you need for this hardware, have the hardware design, a lot of hardware verification, then you're gonna have the tape out, and then on a conceptual way, you're gonna have the software bring up after you have the hardware. But that cannot be the reality because we cannot wait that much time to start developing the software. So later in the 90s, people started using RTL simulation to try to bring up simulation early in the development cycle, so you can start using your new kernel or new way earlier that's necessary without having the actual hardware. And that's the whole concept of using software to simulation to start earlier the software development. So, for example, if you choose to use RTL, which is a proven and well-known technique today, you can have your hardware, the whole hardware simulated, and that's good. You can have a lot of precision, but what's the drawback to have this? So usually RTL is very low. You need to have the actual hardware present. You have to have the commercial IP, the commercial interconnection, everything ready to you. Usually it's not that easy to work with RTL. You don't have any, you have some debuggability, but it's not on a hardware. You can access the memory, but usually don't know the concept of the memory, how the memory is structured inside a large system like the Linux. So I have virtual memory, multiple pages, and sometimes virtual machines on top of the Linux. So work on this setup, it's possible, but takes a lot of research, it takes a lot of time. So this, I'm separating 5 categories of simulation. That's not the reality. There's many others simulation tools available in different areas you can explore. So I decided just to simplify in 5 different categories. You have electrical simulation, usually your spines, where you simulate your transistor, maybe few transistors, and you can have for analog simulation and process that. We have the virtuals, which are a cadence tool that's a default RTL simulation tool that you can use. Usually it's very good to a very lot of VHDL simulation. You can have even the cell synthesized, everything to your simulation is very precise, but the speed is not that great. So usually I got this from the ARM website, so we can have up to 50,000 instructions per second on a big ARM core on a commercial tool, which is a lot, 50,000, but not a lot that you can bring up a full operational system or a rich environment. In the last years, people in the 20 years, they started developing new tools, usually trying System C to have some cycle created, but destroying some parts of the model, so you don't have the pipeline model, don't have each individual cells connected. So this bring you to some thousand of KIPs or couple MIPS, which is good enough to have Android boot in a couple of days, and which is still not good enough. So people continue to develop, and they create microarchitectural simulators, which is the best example I can find is Gene5. Gene5 is a C++ hardware description. You have cache pipeline, reorder buffer. Everything is there, depending the way you simulate it, but you only can get from 0.3 to 2 MIPS when you are not simulating the actual pipeline. So it's good, but not good enough. So how you can develop software on the fly without have this huge backlog of simulations? So in the last 10 years since I started to work with virtual platforms, this concept of simulating or emulating just a program view, so we can create the software way before you have the hardware, had and merge. There are many tools available. One of is not open source, but free license, depending on your university agreements. It's Impera that I work with them for 8 years. So they are a best free example what you can do. And usually on this concept of virtual platforms, I'm talking about some system C until programmers view. There's many different virtual platforms. Virtual platform is not one thing. It's a group of simulation that's fast enough that you can emulate a complete software stack and bring some rich environment to your operational system. So just recapping, virtual platforms can be anything like that. You can just need to make your software believe that's working on the real hardware. And that's the could be abstracted. You don't need to have a pipeline registers which the software interacts, and that's the most important thing. But there's the whole trade-off between how much precision do you need, how many accuracy that you need compared with this precision. Seconds, milliseconds, or milliwatts, and exactly what you need to have your simulation. It's how you're going to define which virtual platform you're going to use. So if you have a virtual platform, which is the modern way to develop or bring up a system, you can have a virtual platform description before we even have the specification. So we can start doing the virtual platforms when people are still drafting the specifications, because as we don't model everything, you can have a lot of blanks on your actual virtual platforms. You can abstract the new pipeline feature if we are not emulating pipeline. So we can have a bring up earlier in your. So in this example, you can start bring up your code several months before you even have the RTL ready. And that's the whole goal of on commercial tools. On academic, you can also use that. So you can skip all this. And if you're not a company, you don't want to bring up a software because you want to sell smartphones or IoT. What's the point of using virtual platforms? Usually virtual platforms are easy to model. They don't need a highly specified engineer to model in System C. You can model almost all the platforms that you can think about. So they are several mods, like there are MIPS, ARMS, x86, PowerPC, RISC-V. They're all available in different ways, and you can model and mix them together. Usually, the simulation targets thousands of MIPS, but if the system is larger, of course, it'll be smaller performance. But usually, on like hundreds of MIPS until thousands of MIPS, depending how big your system. Developing virtual platforms is super easy and is super fast, and that's something that we need in academia. You want to start developing your new mapping heuristic or your new file or your new OS change that you want to publish, and you can do this on a virtual platform on the fly. You don't need to simulate on RTL. That takes 2 days just to bring up the Linux, and then you start doing your work. And most important, because it's a C++ abstraction, you can add code, everything that you want from that simulation. You can get a number of instructions. The instruction, stop the instruction on a particular point. I'm gonna show some examples of it. And you can use this powerful environment to create any type of research inside the limitations of virtual platform, which is also something I'm gonna talk. So this is my first example, my actual research that we did in 2012, 13, 14. So what was the problem that we were trying to figure out and solve? So how I can profile an application, an embedded application, as early as possible and extract some cycle and power estimations to see if a code is improving or not improving, depending on the changes. So that was the problem that we were trying to solve in 2012. So we investigated hardware. So we can have the actual board. I have the board that we are modeling, but is the true data, which is awesome. I can have the number of cycles that each instruction takes. But the problem is we need boards, and they cannot change. I cannot change the cache in the board because it's already been fabricated. I cannot do that. So the other option, we tried RTL. RTL is as precise as the hardware, depending on the configuration you have, but the cost is large. We need a lot of machines. You have the licensing, and you have a lot of problems debugging, because if it's so slow that you need to bring up applications, You cannot debug on the fly, and that brings problem to create your software and work on the RTL. Also, most of the time, you're gonna need a complete IP, a commercial IP, and these are restricted by NDAs, and your university may be trying to get an NDA with ARM or Intel, and that takes time. So usually if you have the actual IP, it's way later when you start your research. You can use FPGAs. FPGAs are nice, they are flexible. You can do anything you want, but you still need to do all this modeling, usually in RTL language like Verilog or VHDL, and still it's a lot of burn in your research to create just this system that you want to model and then start your research. So we choose virtual platforms because they are very fast. They are hundreds of thousands times faster than RTL, but there is no concept of power or cycle on this. So that was the whole point of the research. So how we bring up an initial cycle estimation. We don't want to know how many cycles the application takes. We want to know, I estimated in a region of neighbor of 10%, how long you want your application gonna take, and then change the application, change the matrix size, for example, and see how long this will take after that. So for these examples, we use the OVP Syn, which is the free license tool from Imperis, which is a virtual platform company from Oxford. So how we did this cycle estimation or power estimation. So every time that we fetch an instruction from the simulation, we decode this instruction on the fly. We check which instruction we are trying to execute, and we have a hash table that you can access information about how many cycles it takes, and if it's after load, after store, how many cycles it takes. All this information is embedded in a hash table. We read this hash table, and we have the number of cycles. That's not that difficult to think about, but implementing that consistency is very slow and takes time. So we could implement this on a virtual platform in a month, less than a month, without much experience. And that's what we did. So we decided to test, well, we have a virtual platform that runs thousands of MIPS. How precise is that platform? So we bought the same board that we had been modeling, this board from ST, and we run the same software on both, same binary on both platforms, the FEP, OVP Syn, with cycle and power modeling, against this board from ST. So I'm not sure if you can see it's that big here, but this is the cycle count for the model, the cycle count from the actual board, and this is in points of percent, how big was the error. So if you can see, we have 39 applications from IoT, industrial, automotive, several applications that are in different benchmarks, and we combining this 39 set. You can see that the average is below 8 in 33 of the 39 applications, and the worst case is 11% of mismatch. And for something that is as early as we are doing, 11%, just to understand if you're improving the software or not, it's more than enough. So you can have your software ready when the hardware is available and everything is checked and the performance is improving. And then you can move to a board FPGA where you can focus on performance optimization. And that was the whole point of this research. But we are talking about virtual platforms. So we can create this tool. We can have all these tools implemented. Later on in my career, I implemented this in the Imperis, which is the commercial tool. We even feedback this cycle estimation to the timers. So the timer was dilated depending on the cycle estimation. So even the Linux timing side was a little bit more estimated, so closer to the reality, but mismatched by 8% in average, like I showed in the results. Okay, that's the good part. That part was published in these papers here. But what is the limitations? What things people need to think about before they're doing this on a virtual platform? So first of all, this model was single and in order pipeline. So our pipeline was 5 or 6 stage on that hardware. So it's a very simple pipeline. There's no much reordering. You don't need to do anything. You always know the order of the instructions. That's the whole point of the IoT embedded applications. And it's a single issue, or sometimes it's a double issue, but it's a single execution. So you always have one instruction per time. It's not like a big A75 processor that have 5 instructions being executed at the same time. So this productivity of how many instructions are executing makes possible to create this model where we can fetch one instruction per time in the OFP and have a very good precision. If you scale that for a out of order SCAR pipeline, the results will be way different. There will be a lot more work to create a usable cycle estimation. I know that someone ported this work for an A9 with dual pipeline, but I don't know if they continue the work later. Also, there's variability even in the hardware. The hardware has instructions like div and mult, where the cycle depends of the operators. So there's the division has early termination, the multiplication has early terminations. So later we add this information to the model, we aggregate this and try to define a little bit closer, so we reduce even more the mismatch between the hardware and the FP. But it's something that you need to predict and need to understand. If your tool has a skew about division or multiplication, your error could be larger, and you need to understand from where this error is coming from. So that model is portable to any application, but you still need to have a cycle or a power information. You need to have access to the RTL on a board so you can see how many cycles each instruction takes, or how many power you're going to take for each instruction. You need to have this information. This is not usually available for any commercial tool or any commercial processor. And for sure, you cannot use this tool for real-time or critical applications. On real-time, you need to know how many cycles everything going to take. So you need to have the predictability to execute that. So you cannot use that. So you need to understand that if you are using for embedded applications that can be loose-timed, you can use this tool. But if you have other times for real-time, you cannot use this tool because you're going to have skewed results. And that's the things you need to understand about virtual platforms, the limitations, and what is good on it. So this is the second example I'm going to give you. Just checking the time. So the second example is based on my PhD from 2014 and 18 with Dr. Ricardo Reis and Luciano. So the problem here, we have radiation everywhere. Everywhere that you are on this planet or out of this planet, you have radiation. And with the decreasing size of semiconductors from 180 nanometers to 10 nanometers, 8 nanometers, the amount of energy injected by a single neutron reaching and striking your semiconductor substrate causes enough energy to flip things inside your CPU. So a single neutron can attach to a flip-flop, for example, cause an energy spike and change the flip-flop's value. And you think it's just one flip-flop, and this is going to go away in the next cycle. But this causes a bunch of errors, and they need to be assessed as soon as possible. So that was our PhD idea. How we're going to check how your software behaves under radiation-induced software errors in an early development phase for multiple systems as early as possible. We don't want to wait until the hardware is there so we can run an Android stack or a multi-core MPI, OpenMPI, or OpenMP application. So we want to be as early as possible. So when the hardware is there, we can just have some idea how the software will behave under infrastructure software in those reliability. So again, we study what we can do. We can have board-oriented approach. We can buy the boards, put on the radiation, and see what happens. That's very precise, but usually cost times is per hour. The radiation is per hour. You need to have people on site, and it takes time. Each evaluation takes days, sometimes weeks, and each board at the end will be destructed. So you have a huge amount of boards and resources to do this type of investigation. We have some idea using RTL or gate level simulation, which are very precise, but again, there's not enough power on this, so we can develop the amount of simulations that we need to reach a good investigation. So end up scrapping the RTL. We try to think about System C, but the problem is there's a lot of System C models, but usually they don't communicate with each other. We can have a CPU System C description, but usually you don't have the interconnection that you want in System C, and have another interruption controller that's not in System C, could be another language, and you try to Lego and mount this, everything is sometimes very complicated. So we decide to use the virtual platforms and see how it can be used as early as possible and as fast as possible. So for this purpose, we decided to use two different OVPs. So our objectives on this project was, we want to target a modern architecture like ARM v8, the newest core that we could find. The idea was to have multi and many cores, from one core of ARM M4 to 100 cores of another ARM architecture, an ARM A9, for example, 100 cores from 1 to 100 cores. The complex workloads is one of the main points. We want to use OpenMPI, MPI, and other high-performance parallel applications, and that was the key point for our research. And also, we want to have a Linux kernel to be realistic, and this kernel doesn't need to be modified. You don't want to have a special simulation kernel that we modify just for that one, and then when you need to move to another kernel, we need to do a whole lot of work to port our changes to the new kernel. So that was the premise of our research, and we choose these two different virtual platforms. Gen5, which is a well-known architecture development virtual platform, it's cycle-created, quasi-cycle-created, depending on who you ask. It has more architectural elements, has the pipeline, it has a cache model, which is well-known, so we can create a very good cache model on that one if you want. As again, very slow. The models, they can represent a CPU, but they are not exactly that CPU. They have limitation on how precise you can model the Gen5 because you don't have all the information how to implement an x86, for example, or even if you have the information to implement that on Gen5, you're going to need to change how the Gen5 was modeled because there are limitations about how the classes interact in Gen5 and how the pipeline was developed 20 years ago. So you need to think about, you can add things, but there's not that easy to add this. And also G5 is not that scalable. Its simulation takes 10 gigabytes, 15 gigabytes, depending on the size of the system. It takes days. So you can run a lot, but not that much. And the opposite side have the highest possible simulation, which is the OVP simulation from in Paris. It's fast, it's easy to model, it's scalable to thousands of simulations, but there's no cache model. It's a gist-based simulation, which means that it fetches one instruction from the code, it decodes, and executes on the host machine. It doesn't simulate the pipeline, the fetching, the issuing, anything like that. So there's a lot of abstraction here between both. And it's a completely on-time simulation. You don't have the control time. Usually the time is one cycle per instruction, so just to have a notion of cycles, but it's just to make the timers going on and triggering later. So on this injecting files research, we have to define things, well behavior, and they need to be consistent. So what we need from any virtual platforms, in this case OVPC and G5, what we want from these platforms. So we want them to access the code of the CPU, get the registers, inject the file, see how the processor behavior, extract information, and see how the information compares with execution without errors. So you need to have all this level access to do this. And usually on RTL, we can do that. We can add extra hardware on that, but that's a lot of work and that takes a lot of time. That's just an example of our simulations, how many components we have and how we extract them from Gen5 and OVPC. One thing that usually people don't think about, but is a very good use of virtual platforms because you can debug anything, you can access any information, you can have very rich amount of information from any application. So usually people have 2 or 3 classifications on reliability papers. Usually they have completed without errors, not completed, and completed memory errors because you can only check if the CPU is finished on the right moment, or if it doesn't finish, probably it's a seg fault. And if it's not a seg fault, probably the memory is dirty, and that's what you can do. On a virtual platform, you can check each register. So you can check individual register that you want to check, not all the registers. You can check the memory. You can check pieces of the memory that you want to check and exclude the others one. Have a rich environment that you can do any type of classification, and that can make you a very good use of these tools, is to create specialized classifications just for you. You don't need to use the generic ones. You can use your own classification. That makes a lot more rich of information for your paper or your development of software. So for you that are not used to reliability expressions, this is the usual flow of a simulation. So you have an application, a target application, the operation system. We compile that. We run on a virtual platform, G5 or VPC, without inject errors, because we need to know how the application behaves when there's no errors. That's the whole point of reliability assessment. We extract a lot of information and we save this. And we use this information that we just extract to create faults, because we want to create faults within different moments. For example, in our examples, we never inject faults on the Linux boot. We inject faults after the application starts on the Linux. So we need to know when the application starts, and we can do that with virtual platforms because we know what is running on the platform, and we can exactly communicate, this is the start of my application, and inject faults after here. So that's very useful for targeting exactly what you want. After generating the faults, you need to inject the faults. And if you need to inject faults, usually each simulation is independent of the others. The simulations are independent, so you don't need to sequentialize them. And that's we're going to discuss in the next slide, how we can improve virtual platforms to an even greater scale of simulation. Then you aggregate all the information, and then you create reports. We could create reports like these ones, that are graphs. We create different graphs. We create even visual explanations why they are happening here. And that's all possible because virtual platforms can have you a great deal of information for you. So on this scenario, we decided to use different kernels. I think we had 3 different kernels on this PhD. Have 45, at least 45 different real workloads from high performance benchmark sites. For example, we use the Rodinia benchmark, which is well-known, and the NAS parallel benchmark, which is the NASA benchmarks for high-performance computing. All these are parallel, and they try to use as many cores as they have. Most of them are OpenMP and MPI, so they are well-known parallelization libraries. So for each time I have one application for one kernel with one virtual platform, I need to run this 8,000 times to get a good statistics for each fault injection. That's why we need performance, because with reliability, you usually need to take a lot of runs to have a good probability statistic. And that's a lot for RTL. For example, 8,000 RTL simulations that take one day will be a lot. On the whole PhD, I think we took 3 million fault injections, and at the end we had like 2 million simulation hours. This was thanks to the University of Leicester. They had a high-performance computing there. They call Alice, and they have like 5,500 cores. I was able to use up to 1,500 cores, more or less, sometimes 1,000 cores at the end of the day, and use all this for fault injection. That's why we could get to 2 million simulation hours in 6 months or 1 year. For all the experiments, we have 3 different virtual platforms fault injectors. We have the OVPC, which is the virtual platform instruction level, no time. We have the Atomic G5. The Atomic G5 is a G5 that has a pipeline model, but it's a simplistic pipeline model. Usually it's 2 MIPS. It's faster than the other G5, the classical G5, but it's not that fast. And they have the classical detailed G5, which takes 0.3 MIPS, 0.5 MIPS, and has the whole cache modeling, the whole pipeline modeling. It's very precise for architecture exploration. So how we could increase a little more, because you have to do 3 million of simulations, how we can improve that. So we decide to first checkpointing. So with checkpointing, you divide your application in, like, say, 5 period of times, and you do 4 different checkpoints. And with that, you can just restore the checkpoint for the fault inject that you need. For example, if you want to inject faults here, you can recover here. You don't need to execute all this boot and the application installation. You can start here and inject your fault here, and that saves a lot of time. In our experiments, doing checkpoint saves 50% of the simulation time. And that's good, but was still not enough for us, and we had to improve even more on that. So we decide to use that supercomputer, but the problem is usually supercomputers have a NTFS shared repository somewhere that's mounted in a different CPU, and if you try to access everything from your home node, doesn't work. So we have to create a scheduling and dispatching unit using the IEEE queues. So we're gonna create a job that takes 1 day, and this job we're gonna do a lot of simulations sequentially, and we're gonna divide our 8,000 simulations in as many packets we can, and send this to the server in different queues, so we can maximize how much simulation we have in parallel. So we can have up to 1,000 simulations in parallel with different applications because they are all independent, and we have a queue to manage that in our server. So that was one of the tests that I did on page 3 was how to create this. And one of the things you need to think about is if you access remotely memory, it will be way slower than accessing local memory on your executing node. So usually it's better to copy everything from your home node to the local machine, the server machine somewhere in the cloud, and execute that locally, delete everything, and copy just results. And that it took a lot of time to figure out and finicky, and sometimes it doesn't work, but after it working, you can dispatch thousands of jobs in parallel and have the as performance as you want. So this is just one example of the simulation time. So on the first column, we have the smaller simulation time for each virtual platform. For the smallest routine application, which was smaller than the NPB, was like 100 million instructions, 200 million instructions. It took 4 seconds on the OVP, 11 seconds on the Gen5 Atomic, and 30 on the classic Gen5. And if you scale this to the NPB, you should take billions of instructions, sometimes hundreds of billions of instructions. We couldn't run the detailed version on the NPB because it's too big. It took more than 1 day for its simulation. So we had to restrict to the Gen5 Atomic to have at least some results. So the smallest simulation was 163 seconds, and the largest one was 42,700, which is almost 12 hours. As you see, as big as the simulation grows, as faster the OVP sync goes, because the OVP doesn't need to have all the context for the reorder buffer, the pipeline, the raster renaming. So as longer the simulation goes, the G5 is a little bit slower, and the OVP is the other side is faster and faster and faster, because when you translate one instruction, this instruction goes to a dictionary, so you don't need to translate this instruction several times. You can use a hash table. So as much instructions you decode, as fast as you go. So after some time on OVP, you reach your perfect simulation point at which you are 200 times faster than Gen5 Atomic. It could be thousands of times faster than Gen5 detailed. So this, I'm not showing 3 million of simulation fault injections on this paper on here, but we're just saying that if you check all the results, OpenMP was worse than the MPI, and we got thinking, why the OpenMP it's worse? Why the MPI is better if they are sometimes the same application with different parallelization techniques? So just a parenthesis, I'm going to explain what is the difference between Gen5 quickly. So the Gen5 simulates the pipeline, each instruction is fetched, there's a cycle, everything takes on this cycle. On OVP Sync and all JIT-based engines, you don't have this ticking idea. You have a series of models that need to run on the same CPU, on the whole CPU, and you need to divide the time to execute that. So, for example, here you have two processor example. You have processor 1 and 2. So processor 1 executes, it stops, synchronizes with the whole simulation, and then processor 2 executes. Okay. And then after a fixed amount of time that we call quantum, this processor 1 resumes, processor 2 finishes, saves all the context you need to do, synchronizes processor 1 and the other models, and starts again. And this cycle here happens all the time. So you can have the quantum as larger or as small that you want, but if you think about it, the synchronization point where processor 1 talks to processor 2 is when they switch context. And you have to take this in mind when you see the next example. So here we have the OVP scene running with different time slices. So if you have a time slice, or in this case, the quantum size, changing from the smallest as possible, which is on the right side, to the default one, you see that the results change drastically just by changing a small portion of the time slice, just reduced by half, have a lot of information that you lost. You can see that changing the quantum will affect the reliability, and we need to investigate that more, why this is happening. So why this happened? When you have an OpenMP application, usually you're parallelizing the for with a pragma, and this for usually synchronize at some point. So all the fors need to synchronize at some point and see what happens and go to the next stage of the OpenMP. Because you have a quantum that is a fixed amount of time, or let's say 100,000 instructions, your OpenMP is gonna execute all the way, and when you finish, it doesn't have how to jump to the next CPU because the model doesn't know that your OpenMP finished. So the synchronization point of OpenMP is gonna still be waiting for the synchronization and execute the whole till the end of the quantum. When the quantum finish and the processor synchronize, the OpenMP from the previous simulation, the processor number one, you're gonna see, I finished this, I can go to the next step. But the problem is that processor is already finished, so we need to wait for the next quantum while the processor 2 executes. And processor 2 executes until it finishes the OpenMP part. And then you're gonna say, I need to wait for processor 1, but processor 1 is not synchronized yet because it didn't execute yet. So you have a lot of quantum time or simulation time that wasted just waiting for the synchronization. And this depends how small your application is. This example, we run with few applications in Virginia, and we figure out that by changing the time slice, we could have a better OpenMP accuracy that we had before without losing that much of performance. Because when you simulate the time slice and reduce the time slice, you have more synchronizations, and more synchronizations mean more time during memory moving, and then you lost some speed on your performance. I'm gonna show some examples of that. So here you can say, I change the time slice from default to 10 times or 100 times smaller, and you see that the behavior is almost identical to the Gen 5 atomic, which is our point. We don't want to mimic the detailed because we don't have all this precision, but we want to mimic the atomic version. And you can see that's way closer than it was before. So here we have a lot of mismatch, and now it's way closer to what the reality on the Gen 5 atomic. So we run all this information and rerun the applications and got way better accuracy compared to the Gen 5 atomic. The Gen 5 detail was a little bit worse, but the point was not mimicking the detail because the detail was executing more structures, not because of the quantum simulation, but because the cache delay, the pipeline delay. So when we reduced the number of instructions, it got a little bit worse compared to the detailed, but the actual simulation performance and the simulation, the software behavior was closer to reality on the Gen 5. So these are just the bands of simulation speed using different simulators and different software stacks. This on the left here is the Rodinia, and this on the right are the NASA applications. So we can see that the average simulation for the top end from the small OpenMP to the large MPI was 250% of improvement just by increasing your application. By reducing that time slice, we got 5 times lower, but still it's way faster than the Gen 5 atomic for the NASA and way faster than the Gen 5 atomic for the Rodinia applications. So you can see that's a lot of improvement here. And we couldn't even run the atomic for the NASA because they're too big. So with all this power, what we can do with this power? So we can execute these days software stack for autonomous driving, which is huge and takes a lot of simulation. And we can execute that and inject faults on that. And that's the end of my PhD and the continuation of this work on the lab. So with billions of instructions, just for executing one frame of one of these applications takes 10 billion instructions, 100 billion instructions. How are you going to execute a whole software stack that takes trillion of instructions on a simulation? On RTL, usually going to take a month, maybe 2 months. On a FPGA, maybe 4 weeks, 3 weeks. I don't know. We never did that. So it opens the possibility to do a lot more investigation if you can focus what you're doing and how you're doing the fault injection. So that was what we're targeting, the final application and how it works. So for this final example, we are comparing the Gen5, the OVP-SIG. We have a library called LibVision 2, which is a visual odometry. Visual odometry when you have images, and by being 3D images, the car can say, I'm going left, I'm going right, and knowing where the car went in the past without having GPS. The whole purpose is not having cars using GPS, but tracking where they was at the start and where they are now, just by seeing the roads and seeing the difference between the landmarks. So for one application that we got 2 different applications. They are same library, and one set has 920 frames and the other 400 frames. So the car moves through 430 frames, and it has a rule that has to follow, and it has to verify which rule it just followed. And for example, just for comparison, the OVP takes 6 minutes. Gen5 Atomic, not detailed, take almost 2 days. In the time that I executed Gen5 once, I can do the whole fault injection 8,000 times with OVP-SIG. So that opens the opportunity to understand how this software that's very complicated, state of the art, is going to behave under fault without having a supercomputer with 500,000. You can use your own desktop machine. So this is the 2 frames. This is the sequence, what the car should do. These are the pictures, and these are what the car is doing. So the first one that's set 11, it needs to go here and go back. And the other car starts, go around the block, and returns to the same point. Shouldn't be that complicated. And how imagine that a single fault injection, a single register bit is going to be changed in one of these simulations. We execute that 8,000 times. And you can see this is set 1, where the car is going this way. You can see that one single bit flip in one register, that's not the PC, because if you inject in the PC, the car is going to die way earlier than the simulation. It just stops here. Just on the data, your car is going to think that was 10 meters apart from the other worst case. So I think the final destinations here on dot lines, this was the expected one without faults. With faults, a single bit flip on one register, you can have cars that I think are 10 meters away. And this case is even worse. I think this one from here to here is 15 meters of span that the car could be. Of course, the cars have other options. They have GPS, they have different cameras, and they have different ways to know they are not in the right position. They are not 10 meters on that way, on the other side of the lane. But that's one of the applications that we use today on cars and could be subject to this with a single bit flip. And that's what we could explore with virtual platforms, because they are fast enough to do all this simulation. So a single bit flip causes all this. So what's the takeaways from fault injection? Fault injection, you can be as fast as you want, and that's the point. But what's the main drawback? The main drawback to virtual platforms is that I cannot tell you how exposed your hardware is. I cannot tell you the car has one fault in 100 hours, 1,000 hours, 1 billion hours. I can tell you how the software behaves under fault. That's clear. But I cannot tell you you need to protect your car in this way because you have to have 1 billion hours of interval between faults. I cannot tell how many faults you're going to have one day or in a year, but I can tell how the software is going to behave. And the other drawbacks is depending how your architecture simulator works, how big is the pipeline, which is the pipeline is cracked. Then it depends if you are trying to show that duplicating the pipeline, for example, works. You need to consider how the pipeline was modeled, and it's a virtual platform, so there's abstraction. You need to think about that. If you are trying to show how cache ECC is going to help on this particular case, you're going to have a good cache ECC model, and you need to think about that if the cache model is good enough for it. If you're trying to change the order buffer, you need to change the order buffer and check actual hardware implementation follows that. All these considerations need to be followed. So that's my current work. So I work on ARM, creating large platforms and bringing up them with software guys as early as possible, way before I have any smartphone or infrastructure platform available. So how you are a company, you have up a new smartphone, a new server, you want to bring up your server, you don't want to wait for the FPGA to be ready, you want to bring as early as possible, and that's proven to work today. You can use virtual platforms, you can bring up your software, have the Linux, have the Android all running before, test the new features, check if the architecture is compliant with your software, and that's awesome. Sometimes we have simulations that run same on the virtual platform like Android. We run Android every day. Sometimes the Android takes 5 minutes, 40 minutes on the FTP. If it is the newest, best Android, it will take 40 minutes. On the RTL days, on the FPGA, I think 1 day, depending if you have checkpoints or not, or don't have checkpoints. And then with something that takes days, how are we gonna bring up something that interactive? Every time you do a change, you need to do a simulation and wait for 1 day. You cannot run and see what you did was working. And that's the whole gap that we are filling with virtual platforms on the market, and all major companies use virtual platforms these days. So this is a platform that we work on it. It's the software guidance for mobile. So we create in ARM a platform that is this is possibly a mobile platform. That's not what you're supposed to do, it's how we would do, and now you choose how you're going to implement. So we create this in hardware, we create this in FPGA, you can create this in virtual platform, and I create the virtual platform, and the other guys from OSS, the software, creates the software, and everything is open source. You can go here and download the platforms, the software, and build everything together. So imagine that you need to build a platform and boot this platform with multi-core clusters, a GPU, a global interruption controller, the complete boot, I'm gonna show you later. And nowadays, all the CPUs, all the big computers have a controlling system. This is a system control processor. It boots the system, it controls the power, it checks if everything's working correctly, and that's how the simulation starts. So have to model all this and then bring up a boot system that we start on EL3, which is the most secure, and have to build all this together until reach your application. I have a better picture here. So this is the sequence by time. So you reset BL0, reset the processor, it starts, then resets the BL1, then the 2, the 3.0, 3.1, 3.2, and 3.3. At the point of you are in the 3.3, you are in the bootloader of your Linux or Android, and have all the 7 steps to reach this point. This is doable in RTL, we do that, but it takes a long time. And it's not feasible for software development. I cannot develop the newest Android with RTL if it takes days. Everything needs to be faster, and everything needs to be more quickly to change. If there are bugs, we need quickly fix, and that's not what happens with FPGA and RTL. And that's the whole point of virtual platforms on a commercial environment. So this is another platform we are working to. It's an infrastructure server or networking, depending on how you're using. This one has 96 clusters of the biggest CPU that we have ever released, the V1. Has a mesh connection that has, I think it's 8x6 XPs, and it's very large. It's connected to MMU, the system MMU. There's a bunch of peripherals, connect here, connect here. There's 2 controlling processors. We have the system control processor and the MCP, which is the power controlling. So we have not just the system control, we have power control. So we have a lot of things to model. Everything need to be tightly integrated and work. So we need to run all that boot flow and bring up your UEFI and bring up all the servers and have this working together. I think I'm running out of time now. So that was the last example, but I think we can open to questions. And thank you very much for your attention. Thank you very much for inviting me.
Well, thank you, Felipe, for your presentation. It was a very, very nice, very, say, complete presentation, because there is a lot of stuff there. So people in the chat, you are free to ask questions. As you ask questions, I will send them to Felipe. Meanwhile, I had some questions because I recently started studying a bit of let's say virtual platform modeling, something like that. So doing very more like studying things than in fact implementing. Like in these platforms, we know that there are memory accesses. The way that you access memory, the way that you implement memory has a huge impact in both performance and power consumption and energy efficiency. So is it possible to model these particular characteristics of, let's say, memory access schemes or something like that to have an idea how the system will behave in these virtual platforms?
There are several ways that being studied for a few times. So, for example, on G5, you can have the cache model that's very precise. You can have a cache model that's like hardware, but your simulation is going to suffer 100 times. So if you want to explore how memory consumption or latency affects our application, you can do that with virtual platforms. The problem is you'll be 100 times slower, even though it's 1,000 times faster than System C and 1,000 times faster than the RTL. You can do that with a G5, even with our tools like OVPSync and the fast models, what I work, we have cache models. You cannot create cycle precision from nothing, but you can create a cache protocol that emulates the latency, and you have a notion how cycles are going to take, and then you can do your power by area of cache using some tools that are available on the internet, or there are researchers. So you can create that. You just need to think that if I need precision on the cache, on the memory path, you need to know which components are using, and these components are processing, because if you have a very good cache model, okay, that's awesome. But how good is your branch prediction? Because if your branch prediction goes wrong, you have a new reorder buffer fault, and you have to refetch a bunch of stuff. So if your reorder buffer and your branch prediction are good, and you have a good cache model, you can do what you want. But you need to think about the details. That's the difference between working in RTL. In RTL, you have that and works. You do whatever you do, and you have always the same results, the precise results or the golden results. But if you're working with virtual hardware, you need to think the limitations before you start your work, and then thinking how I overcome these limitations, or if I don't overcome the limitations, how I implement a software or a hardware that don't steps on these limitations, and how I go through these limitations, and I get very clear on the paper I have those limitations, because there's a bit further thing people want to say to you.
Yeah, well, that really explains a lot of what's going on. But yeah, in fact, when you go to RTL, like even though you say it's 100 times lower when you have that cache, for sure you're gonna take you will be speeding up your let's say testing or experimentation process, because writing a cache protocol in RTL is not something very trivial. And so while we wait for questions from the audience, this is more general questions. Have you ever worked with these systems? It's a kind of solutions that some CAD companies have, where you have a hardware-based emulation system. Like you can emulate them using FPGAs or like platforms specifically for that. Have you ever worked with that?
So our teams are way separated, but I'm more. We have these projects. For example, this project I showed you, the STM775. I do the FPGA and the FEP. Someone does the software. Someone else do the FPGA. Someone else do the RTL. And we have all this same software working different levels, starting with the virtual platform. Cool. So I don't work directly, but we work with people that work that. So they can port a big platform to FPGA, but the problem is the size of the platform. So today you have an ARM processor. You should have 8 cores in a cluster. Have GIG controller, SMU controller, GPU controller, and usually doesn't fit in the largest FPGA, so people have to cut stuff. So you can do that. And let's say I have a system that holds inside the FPGA. Now you need to run that thousands of times. You need a farm. And we had people that work in farms. They are good, but it's a farm of FPGAs. If you are working on FPGA in your PC, you know how many times that things breaks and how many times you need to reset things and reflush. Imagine now that you don't have access to FPGA. You need to do that by command line on a server somewhere in the world that you don't have access, and then things crash and the FPGA dies. Who's gonna fix that? So we need to get another FPGA and open a ticket and say it's doable, but it's all in time. So if you want to develop Android, you cannot do on FPGA, but you're gonna run Android on FPGA to know that your features work. And if the features work, then you're gonna move to our RTL. Sometimes in parallel, everything happens in parallel these days, but we're gonna have RTL simulation at the same time have FPGA and FP simulation. So we do everything FP, move to FPGA, the features you want to explore, and then you move to RTL to just complete and say everything works, and we are ready to go.
Okay. Well, I just have one final question, which was something that in the last system that you were working, which is a very complex system, there are several cores, IPs, and when you have these, these ones. So let's say you model this in a virtual platform. Let's say this part of all these green parts here. How do you use, let's say, an in-house model for these IPs, or when you have a specific IP, like let's say the 400 gigabit Ethernet, do you model this in some way, or does the IP already have some, let's say, model for it so that you can embed in the platform, or you don't use that? You don't consider?
So all in green, that things that we are modeling on the FEP nowadays. FEP is fixed virtual platforms, which is the binaries that you can get from free from the website. But we have a whole team inside ARM called Fast Models, which they create these C++ models. And usually we have all the ARM models plus some other models. We have a cache model that's our cache, but we don't have a DMC because we don't sell DMCs anymore. But we have a model for DMC, and we have a model for Ethernet. I don't think we have a 256 gigabytes high performance because it's a virtual platform. We don't have the concept of queuing in PCI Express. Don't need to have the hardware that do 4 gigabytes. We just need one Ethernet that works, and that abstracts for the software because they just need Ethernet. They don't need to know the speed. It's a simulation. But usually what ARM does, we sell the fast models for some kinds, but usually we sell the models to Synopsys and Cadence. They wrap together inside System C, and they sell them to other clients. So everybody use our models, but they're buying from Synopsys because it's a chain. But this FEP, so this platform here, you can get that from the ARM website for free, and there's whole open source software. You just compile the source, get the binary, you can run this 96 platform. I think it's on the website is 16 or 64, but have a large platforms and have all these components in green.
Yeah, I was just a bit unsure because I know it's an untimed, the part that you said that we don't have, like, it's not a cycle accurate, but still you have a lot of data that you have to process. So, but this is, let's say, given an infinite time, you can process anything, basically. So,
usually you are way faster. So even with Ethernet, we are way faster than anything else. So because you don't have time, you don't know if it's 4 gigabytes or 10 gigabytes. You're sending data as fast as possible on the virtual machine. So the concept of gigabytes per second doesn't exist, but it's super fast because you have access direct to the memory. You're not sending something to another model. You just everything together in a binary.
Okay, then, if we don't have any more questions from the chat, let me just see here. Apparently, we don't. I'd like to thank you for your presentation. It was very, very. I'm sorry for the background noise, and I'd like to thank you for this presentation and for accepting giving this talk to our event. Thank you.
Thank you very much. Thank you very much for inviting. I'm very, very happy to present.
Okay, so let me just add.
So thank you, Leandro. Thank you, Felipe, for a very nice presentation. Now we have a break. We'll be back in 20 minutes, more exactly at 10:45 a.m. All right. Thank you very much.
So, welcome back, everyone. Let's keep our event. I would like to invite Professor Sergio Bampi to be the session chair for this presentation.
Thank you. Good morning, everyone. Good afternoon, wherever you are.
Okay.
Okay. Let's start this presentation. This invited talk will be given by Professor Hussam Amrouch. Let me introduce the speaker for this talk. Dr. Hussam Amrouch, who is a professor at the University of Stuttgart in Germany. He is the chair of Semiconductor Test and Reliability, the STAR research group. And he's also, for many years, has been and still is a research group leader at the Karlsruhe Institute of Technology, also in Germany. Dr. Hussam Amrouch earned a PhD in computer science in 2015 from the KIT in Karlsruhe with distinction, summa cum laude, and soon after, he led the Dependable Hardware Research Group at KIT. He has, over 140 publications in journals and prestigious conferences. And he's very actively engaged in the research in emerging technologies and machine learning as an application, and machine learning for CAD. And, he is covered in his research many areas of the computing systems, from semiconductor physics, devices, circuit design, then, on top of that, computer architecture and computer-aided design issues. He serves as an associate editor of the VLSI journal, the Integration Journal. He's a guest reviewer of many journals and review editor for Frontiers in Neuroscience. He has served in committee of many prestigious conferences in those areas. So it's a pleasure here on behalf of the IEEE Circuits and Systems Society chapter in Rio Grande do Sul, who has organized this workshop. It's the 13th edition, and I welcome back, even virtually here. And I remember in 2019 you have been speaking here for the CAS eMicro, School of Microelectronics event. So welcome back, Hussam. It's a pleasure for all of us here in Brazil, all those organizing the CAS. This is being broadcast over YouTube, and we'll get questions at the end of your talk through the YouTube channel. So please, the audience, feel free to address questions to the speaker as he goes speaking, and in the end, we'll collect those questions and go for the question and answer. Again, the floor is yours, Hussam. You can share your screen, and very good to have you here in the CAS Rio Grande do Sul workshop.
Thanks a lot, Sergio. Many thanks for Guilherme, who invited me to here. So it's a great pleasure to be with you again, unfortunately virtually. So I still remember my trip to Brazil, visiting you and others, talking in 2019. So yeah, I'm glad to be with you, at least virtually, and thanks for having me here. I have already shared the screen, so I assume hopefully all good. So, and I'm going to start. We are, as engineers, always obsessed nowadays by the amazing improvement that's coming from deep learning. We are always obsessed about the significant improvement in the accuracy that we are obtaining from our deep learning models. Many things and many applications, many breakthroughs would not be possible in the last, or we could not dream in the last couple of years without the breakthroughs from the deep learning and machine learning models. But we need that we remember and we be careful that's all started when the specialized hardware and the invention or the breakthroughs in the hardware and the accelerators that came from Google around 2016, the so-called Google TPU. And many, how to say, inventions in the last couple of years happening in the area of neural processing units in order to accelerate deep learning, training, inference. So this is a very active area from both sides, algorithms and system level sides, how to say, as well as from the underlying hardware. However, today I'm going to share with you and draw your attention about one enemy that we need that we be very careful and find against when it comes to deep learning and neural processing units. It's temperature. Temperature, in fact, I call it the unseen enemy for our future chips, and this is why we need that we be careful about it and we think proactively how we can solve it and deal with it, which is quite different challenge that we used to do with our traditional multi-core systems. And that's actually in summary, the main topic of the talk today. First, we are, again, as engineers, always obsessed in increasing the efficiency of our system. Our hope and our dream is if we increase the efficiency of the systems, we will gain more and more saving. However, this is not always true. If you think about using a very efficient car, you would hope that at the end of the year you will save lots of money because the driving or the cost per driving is very little. But that's not actually the case. If we have very efficient car in which the cost per drive is very little, then we will start to drive our cars more and more often. And at the end of the year, we will actually spend more money for the maintenance and guaranteeing the reliability and the maintenance of our car. And those hidden costs will compensate, if not canceled out, most of the gain that we have obtained at the first place from the saving. Environmental problems, which one of the main driving force behind inventing efficient cars, will start to increase because the efficiency is so high, everyone will start to drive his car more and more often, and environmental problem will start to increase instead of decrease. And that's actually very well known in the automotive industry. In economy, this is known as Jevons paradox. He observed more than 100 years ago in England that after the invention of the steam engine, which became, or at that time it was a breakthrough and was very efficient compared to other engines, Jevons observed in England that the total consumption of coal was keep increasing instead of decreasing. How could it be after the technology made the process very efficient? Then the total consumption start to increase instead of decrease. How could it be the efficiency did not provide us with saving? Many years later, this became as Jevons paradox. Jevons paradox, whenever the technology makes a process very efficient, the gain, the large demand, the large demand and the demand and the increase in the demand, the large increase in the demand for that resource will compensate, if not canceled out, most of the obtained saving in the first place. And this is well known in economy that efficiency not always lead to saving. How this is really related to technology and silicon and chips and microprocessors and what we used to do in our community. In fact, I see a very straightforward relation. If you think about the transistor's efficiency has been tremendously improved in the last couple of decades. More than 1000x improvement we have obtained in our transistors and energy switching energy in the last 4 to 5 decades. Because the efficiency of transistor became amazingly good, the demand behind transistor increased. Nowadays we have chips with more than 10 to 20 even billions of transistors. And how this could happen? That's actually because we were able to keep scaling down our transistor geometry and our transistor feature sizes in order to provide this large and serve this large increase in the demand for transistor and packing more and more transistor within the same chip die, we had to scale down to below 10 nanometers. Nowadays, Samsung and TSMC already producing 5 nanometer chips, and the 3 nanometer is already in the near future roadmap. However, when we reach such fundamental limits in transistor scalings and we reach such an atomic level, the reliability of our systems and our transistors cannot be guaranteed anymore. And to ensure safety and to ensure and fight against uncertainty, we have to include larger and larger safety margins and larger guard bands, otherwise the reliability cannot be ensured. And such guard bands will compensate, if not cancelled out, most of the obtained saving that we have obtained from the efficiency when we scale down the transistors at the first place. And this, in my opinion, one of the manifestation of Jevons paradox, but in technology instead of economy. Let's remember and let's take a look where we stand nowadays in technology scaling. If you think about it, the blood cell is around 100 micrometer, and even coronavirus that's causing all these problems nowadays and the pandemic, and the reason why we are meeting virtually today, it's just 100 nanometer, which is amazingly small. But we as a humans, we are able to create transistors that's by far even much smaller than the coronavirus itself. As I have just said, the Samsung devices, the 7 nanometer, already in the production since 2019. And even they have announced that the 3 nanometer transistors is coming soon in 2024 or 2023. And the only reason for such a delay is due to the pandemic nowadays. But let's remember that the DNA and the protein itself is just 1 nanometer. So we are so close to such fundamental limit in scaling. However, as usual, whenever we are reaching such a fundamental limit, there is breakthroughs should come. And we need that we remember when before talking about the breakthroughs, what's actually the reason for the breakthroughs, the need for such an emerging technologies and breakthrough. It's not only the minimization of the feature sizes of the transistor, but actually there is another problem that's coming along the aforementioned, how to say, minimization problem. It's actually the voltage crisis, the voltage wall. If you think about the transistor, it's actually, you can abstract it as a switch between on and off. What really dictates and determines the speed of the transistor is the steepness of the curve. If we could make the transistor much steeper and we make the subthreshold swing much smaller, we could actually achieve the same on current, but at much lower voltage. What that really means, it means we can keep clocking our circuit at the same frequency, at the same clock, at the same performance, without any loss in the performance, but at much lower voltage. But what is the problem? Why can't we arbitrarily make our transistors as steep as possible? Well, the so-called subthreshold swing has a fundamental limit. And in semiconductor physics, this is very well known since the invention of the transistor, or almost since the MOSFET came. This is actually attributed to the so-called two capacitance in series and the voltage drop that will happen always in between. If you think about your MOSFET transistor and the field effective transistor in general, it's actually you have the insulator capacitor and then you have the underlying MOS capacitor. And the subthreshold swing, it's actually always 60 millivolt per decade multiplied by a constant factor. Let's call this constant factor lambda, which is known, or typically it's called as a body factor. Now this lambda, it's coming from these two capacitors in series, as you can see here, and that's actually 1 plus a positive value. And that means this lambda always larger than 1. In the best case, could be 1. As a result, you have the subthreshold swing. It's always fundamentally larger than 60 millivolt per decade. But let's think about it for a second. Where we stand in technology scaling nowadays, TSMC more than 5 years ago, they have already achieved the 64 millivolt per decade. So if the 60 millivolt per decade is a fundamental theoretical limit in subthreshold swing, and we are already in technology scaling almost at the 64 millivolt per decade. And let's remember what we have learned in the last few slides, that we also at the 5 nanometer and the 3 nanometer is coming soon. That means we are reaching at the same time two problems, two crises. One is from the technology scaling and the feature sizes minimization itself, and one from the voltage scaling itself. So whenever we have very small feature sizes, at the same time, voltage is not really scaling, what do we expect? We expect very high power densities, very high temperatures. From here, you can start to predict why temperature is a hidden problem and also is getting much larger in the upcoming technologies. Temperatures is very well known to be as the key source for failures in semiconductor devices. Temperature, once it increases, it impacts our devices, our circuits, our systems in two ways. One is short term. That means in the next few milliseconds, microseconds after the temperature has increased, the reliability and the resiliency of the circuits goes down. If you don't include enough safety margins and timing guard band, timing violations will start to appear in your circuit because the clock frequency becomes unsustainable. Similarly, when it comes to memory, if you have the temperature or the temperature increases, what will happen, the memory and the SRAM memory becomes more and more susceptible to noise. Therefore, data corruptions, the data integrity of the memory cannot be ensured anymore. So at the short term, once the temperature increases, lots of problems start to appear in the circuit. So temperature is not good in the short term, even in almost immediately or instantaneously. On the other side, if you have a chip that's suffering from elevated temperatures and excessive temperature, excessive heat for a long time, aging in the circuit and the transistor start to become larger. That means the lifetime of the chip cannot, or they'll become smaller and smaller, and the reliability of the chip for the long term, let's say after 5 years or 7 years, cannot be guaranteed any further. Therefore, temperature is bad immediately for the chip as well as for the long run because the lifetime of the chip becomes smaller. The temperature is a result of two things: having voltage that's not scaling. Because the voltage is high, the power is high, the power density becomes high, and the reason, remember, voltage is not scaling, but also the feature sizes is keeping scaling and reaching atomic level. Temperature is, in fact, the unseen enemy for technology, and literally the unseen enemy. And as have been said, the unseen enemy is always the most fearsome. Why? Because once it's here, it's too late. In my opinion, nowhere in technology is that more true than when we look at chips temperature. If you think about it, how you could really fight against the temperature and how we can really predict and protect your chip against temperature, if you cannot see the temperature at the first place, what you get your silicon die with a package with a heat sink and a heat spreader and heat sink on top of it, yet you really need to predict precisely your temperature, how it's evolving in order to protect against its effect. In order to predict the temperature accurately, you need to predict the power accurately, you need to have the entire floor plan, and at the end, all those estimations might not be as accurate as possible, and the crisis, a hotspot could emerge during the runtime somewhere across your chip, causing a temporal or even a permanent failure. So therefore, temperature, if we don't see it, is very hard to fight against it. And again, the key question is how we can really see the temperature underneath, how we can really clearly measure the temperature that's happening during runtime in our chips. In order to solve this problem, we have built the first infrared camera, the first thermal setup that can measure precisely the thermal map, the entire thermal image for modern processors without any layer in between. That means you have your infrared camera measuring directly the infrared emissions of your silicon die directly, which allows you for the first time to see how the temperature evolves in those complex modern chips in order to analyze it at the design time and understand how the temperature can really evolve at the runtime. This gives lots of insights for the reliability management, even for chip designers to understand where they have to locate their thermal sensors and how many they have to put. This is an image of the thermal setup where the infrared camera measures directly the chip temperature. We see here the Intel 8-core chip without any package, any heatsink, and any heat spreader, like a naked, silicon die, and then the camera itself measures directly the infrared image. However, it's not always easy to see the temperature. In this example, I gave you and show you a solution in order to see the temperature at the large granularity at the chip level. But the temperature is not always to be seen. When we think about the transistor itself, not from the macro level, and let's look at the micro level, we have also another type of problem, by far more difficult. Revealing temperature is not always easy. When it comes to advanced transistors, such as what we see here, the FinFET transistors, the temperature and the current density and the power density inside the channel of the transistor itself becomes very high, which means that even though you measure the temperature of your silicon substrate, of your silicon die, and that temperature still looks cool or cold relatively, the temperature inside your transistor channel is so high, but it's so encapsulated, so trapped inside your transistor, in which it's very difficult to escape to outside and then be captured. And that means your temperature or your transistor is almost heating up from inside, but you cannot even observe or measure that. Your sensors inside the chip still tell you the temperature is cold. It's like a room temperature, 27 degrees, like you see here in this analysis for 14 nanometer FinFET technology calibrated with industrial measurement data. We see how the temperature near to the drain is so high, yet the substrate of the transistor, the silicon itself, is relatively cold. That die, again, if you measure the temperature of it, it will tell you it's still cold, but the transistor channel itself goes 100 degrees above the ambient temperature. We have done the analysis also for more advanced transistors, such as the nanowires. We can see even with the nanowire, the temperature problem getting even more challenging. And this is very well known and so-called or often called or referred as self-heating problem in transistors. When we have such a 3D confined structure where the channel is surrounded by the gate in order to have better and better electrostatic control, what we have that the generated temperature from the channel is facing more and more difficulty to escape to outside and be dissipated. We see here in the nanowire, due to the very high confinement and the 3D structure of the gate all around, how the temperature near to the drain is getting so hot that it's not able to escape to outside. We have also done the analysis for advanced nanosheets, which is the next generation after the FinFET technology and expected to replace FinFET at the 5 nanometer and below that. Also, the problem is challenging there, even it's more than the FinFET itself, because the sheet itself facing the metal sheet, for instance, facing more difficulty to dissipate the heat compared to other sheets. All in all, in summary, the temperature in advanced technology nodes is getting more and more challenging at the micro level and the macro level. Within the transistor itself, generated heat facing extremely difficulty in order, very high difficulty and extreme difficulty in order to be able to dissipate and go outside due to the advanced 3D structure, quantum confinement, and many other effects that's happening at the extreme feature sizes like 5 nanometer and below, or in general below 10 nanometer, where quantum effects becomes dominant. On the other side, when we go to the larger scale, we also have the problem that temperature, especially in advanced heterogeneous structures, we don't understand very well where the hotspot will be evolved at the runtime and what's actually, or where actually the problem could appear, and therefore we cannot really fight against. And if we want to be just very pessimistic and just fight against temperature and worst case of temperature, we will definitely lose lots of the efficiency gain that we have obtained at the first place from our technology scaling and from adopting advanced technologies. How this is really related to AI chips and deep learning, the main motivation of my talk and how I have started? Well, it's all very well connected, as you will see in the next couple of slides. First of all, deep learning models and breakthroughs in the accuracy of many AI applications made many of our, how to say, dreams that we could not even dream in the last couple of years became possible. But such breakthroughs in the accuracy of models and algorithms and systems would not be possible without other kind of breakthroughs in the underlying hardware. In fact, many of those improvements in the accuracy attributed to the very tremendous increase in the complexity of deep learning models. Nowadays, models consist of, I don't know, many hidden layers, and you have millions of parameters and sometimes billions of weights. But in order to train such models, it's not easy to do it with your traditional hardware. This is why breakthroughs in the underlying hardware was really necessary in order to make those complex model, training those complex model feasible. And that opens actually the door for deep learning to get more and more accurate. This started all with Google TPU 4 to 5 years ago, which is deployed in data centers, started with the inference, and nowadays the Google TPU version 2, 3, 4, all of them able to support even training, speeding up the training tremendously, making complex models feasible. Also, we see now these accelerators and those AI specialized hardware. We see them already in our even mobile devices. Most of the mobile devices from Samsung, from Huawei, already including even Apple, nowadays everyone, including already a specified engine to accelerate deep learning models. We see also that such neural processing unit also at the extreme edge, which as an example, the Google HTPU. But we have a problem. In such, how to say, complex systems, and if we take a look at the picture here, which is from the ISCA 2017 from Google, TPU, the first version, and what we can observe that the large portion of the chip is actually dedicated for systolic MAC array. The systolic MAC array consists of, in this example, 64,000 MAC unit. And this 64,000 MAC unit all confined in a very tiny problem, a very tiny area, which is 24% of the chip. And this is really a problem because this will consume huge power confined in a very small area and will lead very quickly to excessive heat generation. But you can say, where's the problem? We have a cooling solutions. We have our fan, our heatsink, which will make sure that the heat is dissipated effectively. That's actually not really true because we have an inherent problem in the cooling solution. They are actually inefficient. If you think about it, you have to cool down the entire chip, putting the fan, whereas your fan and the large heatsink, whereas actually the hotspot is located only in one place. In order to investigate this problem, we have actually done a complex multiphysics simulation using an ANSYS, which is a finite element simulator, commercially or commercial tool, ANSYS for very advanced heat simulations. And we have done that for the entire system where we have this systolic array mimicking the TPU, and we analyze the temperature under the maximum and the highest air cooling thermal convection. And what we have observed is, and the technology that we use, it was 14 nanometer FinFET technology calibrated with Intel data. And what we have observed that the temperature of the systolic array will go beyond the maximum temperature of 100 5 or the critical temperature 105, and we can see at the nominal voltage of around 0.7 or at 0.7, the temperature will reach above 120 degrees, which is indeed critical. And whenever even we boost a little bit the voltage and we go to 0.8 volt, the temperature of the systolic array will even exceed, the 130 and the 140 degree. And no surprise because, it can even reach the 180 degree. There's no surprise of that if we look at the power density. The power density, the total power consumption of those 64,000 meg units, and remember, multiplier is always very power hungry. And if you put 64,000 of those multipliers working simultaneously, jointly, generating huge power confined in a very small area, 24% of the entire chip, then the power density can easily reach 200 watt per square centimeter and even nearly to 300 watts per centimeter if you boost your voltage. Such a massive, such a very high power density with the limited capability of the air, even at the maximum thermal convection, will lead to temperatures that can exceed the critical temperature. Is that really true in reality? Is that what we have observed in our simulations really match what's happening in data centers and other companies? Actually, interestingly, that the Google TPU and has caused the problem, as it has been announced by the Google CEO himself. He said during the announcement of the I think the version 3, the Google TPU version 3, he said, these chips are so powerful that for the first time we have had to introduce liquid cooling in our data centers. That shows that the problem that's coming from the neural processing units and the problem of packing and putting thousands of Mac units in a very small confined area. But let's take one step back and think about the problem in the traditional cooling and why we need some emerging cooling solutions. Traditional cooling will try to cool down the entire chip using, traditional fan or maybe even water cooling. But remember, this is a little bit inefficient or maybe largely inefficient. Why? Because actually you are trying to cool down the entire chip even though your hotspot is located in a very small area. Yet you are trying to cool down the entire chip. Remember, for instance, if you take a look here, you have 30% of your chip reserved for the on-chip SRAM memory, which is not really critical because it typically has a very low power density compared to the systolic MAC array. What is the solution? Actually, if you think about it, the solution should be straightforward if we could invent a cooling that can be localized. If you could cool down the chip only where it's needed, instead of cooling down the entire chip, which will cause efficiency loss because you are paying cost for the cooling for everywhere where it's actually needed only at a specific and certain location. If you could cool down your chip only where the hotspot is located and only when the hotspot is emerging, you could actually do much better job. You could actually cool down more efficiently your chip. And that's actually one of the need for the emerging cooling solutions. And in this regard, I would like to introduce one of the many breakthroughs in the material science that's happening, not just recently, actually in the last decade, but maybe we in our community, we don't hear often about it. It's called superlattice thermoelectric device. And the thermoelectric device is an old concept. Actually, Peltier discovered this phenomenon more than 100 years ago. And thermoelectric devices are very well-known devices to provide a controlled source of cooling. The problem always with the thermoelectric devices is actually the thickness. Bulk thermoelectric devices that commercially exist since many, many decades actually very thick. So therefore, using them and large in general. So therefore, using them and integrating them in the traditional cooling solutions for our microprocessor and IC chips was always not a good choice because they would isolate the heat from the die itself to the heatsink itself, and this will cause a problem instead of solving the problem, unless you pump them with a huge current to overcome that. But then it becomes very, very inefficient. The breakthrough that came in the last decade is actually through inventing a way where you could fabricate the thermoelectric devices in a way that the ultra thin, they call them ultra thin film or superlattice. The thickness of them is just 50 micrometer, for instance. And by integrating them within the chip die, we are able actually to put them where the hotspot is generated, and then we can cool down only the hotspot and paying the cooling cost only at that location. Now, in this case, what we will have, for instance, we have done this analysis for the thermoelectric device where the hotspot is located at where the thermoelectric device is located on top of the thermal hotspot. And we can see here how we are able to suppress actually the temperature of the hotspot, and it goes down from the critical temperature of around 124 all the way down to around 108. And that shows the effectiveness of the thermoelectric device in order to, the superlattice, to be precise, the superlattice thermoelectric device in order to cool down localized hotspot. In this analysis, we have used the multi-physics simulations. And in this example, we were able to dissipate or to suppress even a thermal hotspot of around 200 watt per square centimeter. Now, let's connect all the dots and go back to our original problem, the neural processing unit. How we can really manage the temperature of the thermal, manage the temperature of the neural processing unit? What are the different means and options that we have in hand? First of all, we have precision scaling. Remember, the problem is coming from the multiplier, and the multiplier is a very power-hungry component. But the multiplier itself could be a different precision. What really, determine which precision we need is the accuracy demand of the neural network model. We know that neural processing, the neural network models typically, they don't really need very high precision. Some of them they need, some of them they don't need. So we have a knob in our hand, which is related to the precision of the multiplication, the precision of the arithmetic unit itself. If we decrease the precision, we could actually reduce the dynamic power, we could reduce the power in general of our fundamental block, the MAC unit, and as a result, the entire systolic array, the entire MAC array, power will go down, hence temperature will go down. So the first knob that we have in our hand is the precision scaling. On top of that, we have our traditional knob, which is frequency scaling. Reducing the frequency, no doubt, will reduce the temperature because the power is related linearly. But reducing the frequency means a loss in the throughput, as we will see soon. Finally, we have this nice new knob that I call it advanced cooling solution using thermoelectric. Nowadays, it's commercially not there, but many labs and some companies even start already to demonstrate that. There's no reason why we don't imagine and envision this could be possible in the near future, and there's no other place to be true more than the neural processing unit due to the big challenge that comes with them with respect to power density and on-chip temperatures. So to summarize, we have the precision scaling as a knob. Reducing precision allows us to improve or mitigate the temperature with the cost of accuracy. Frequency scaling allows us to reduce the temperature and the cost of throughput. Finally, advanced cooling and thermoelectric device will allow us definitely to suppress temperature, but at the power cost, because you have to power it on. You have to feed it with lots of current and power in order to create this nice cooling effect. So it's not cheap, it's actually expensive when it comes to power overhead. However, the key is, instead of we focus only on a single solution, why don't we focus on hybrid solution? Why don't we reduce the precision a little bit, reduce reduce the frequency a little bit, apply advanced cooling a little bit, and then such a hybrid solution can open door for us in which accuracy loss of our deep learning model is minimized, power overhead due to cooling is minimized, and then throughput is maximized and temperature is maintained under certain thresholds. And that's actually what I'm going to demonstrate and tell you about how the thermal management of neural processing unit could be achieved using those different knobs that we have in hand. Let's start with a key question, how we can evaluate all those things together. In fact, there's a large gap. We talk about deep learning models, which is something at the high algorithmic system level. We talk at the same time on something like superlatives, which is complex multi-physics simulation. And then we talk in between about power density, which necessitates a full chip design in order to be precisely estimated. And how we can really evaluate all those different pieces coming from different abstraction layers all at the same time. Let me show you how we built that and how this framework could be realized. We started from the system level where neural processing units can be trained. PyTorch in this context has been employed. We trained different neural networks, for instance, for the dataset ImageNet. And then in order to explore the impact of precision scaling, we had to do quantization. And the quantization is a famous, powerful technique for neural processing unit in which after you train for your floating point precision, which is a high precision that's required during training, you can apply quantization. In fact, the Google TPU version 1 was for 8 bits, but the models were trained for 32 bits floating point. And many studies show there is a minimum and very marginal loss when we really reduce the precision and quantize from the original 32-bit level all the way down to 8-bit. But we ask ourselves another question, how about if we reduce the precision further and further? Of course, we are not the first to ask this question. Many other studies investigated, and it's a very hot topic nowadays about investigating the impact of quantization in deep learning models, on the impact of them on the accuracy, because it's very well known will give a very nice reduction in the power. So let's start from the highest level. We use at the system level the PyTorch. It allows us to train the neural network, to quantize the neural network, to get the inference accuracy. So everything with respect to precision and accuracy would be studied there. Then we need to answer the next question, how the power density will look like. And to answer that, we have actually to do the full chip design, and we need to do the traditional chip design, how to say, and using the traditional sign-off tools for power, for timing, and this will give us how to say accurate temperature, because accurate power, because we can get the area and the floor, the area, and then the power accurately after the layout, and this provides us with the power density. So to estimate the power density, there's no magic. You really need to do the synthesis, the chip design, the floor plan, the power, the area, and then you could estimate the power density. And then we have done that for 14nm FinFET, and the underlying model card was calibrated with available data, publicly available from Intel 14nm devices for more, how to say, insights about the calibration process and the library characterization to achieve that, all provided in our paper. So then we reach the next level. We want to understand the impact of heat, the impact of cooling, and all those we have studied using the multi-physics simulations from ANSYS, which is, as I said, commercial tool that employs finite element methods to study sophisticated heat simulations process. And there we have implemented the cooling from thermoelectric devices as well as the baseline heating effect. So all those studied there. Now, once we have those three different pieces, we can actually integrate all those ingredients together, and we perform design space exploration to trade off temperature, power, overhead, cooling cost, neural network accuracy, and throughput. All of those we can study now. Once we have this how to say, multi-layer framework, we can start from deep physics all the way to accuracy of deep learning. And I will show you a few examples in the next couple of slides. Let's recap. We have frequency scaling, very powerful, very well known, traditionally to fight against temperature. The cost is the throughput. Precision scaling, very well known, accuracy will be dropped as a cost. Advanced cooling, not very well known, it's emerging cooling solution. The cost of it is additional power overhead. We studied the hybrid solution in order to minimize the overheads. We can employ actually precision frequency scaling, where you combine the precision scaling with the frequency scaling. What would be the cost, throughput, and accuracy? Finally, you could actually combine all of them and do precision scaling, frequency scaling, as well as emerging cooling and thermoelectric cooling, which is referred to as TE, and then you will get, the throughput, accuracy, power as a cost, but that would be very powerful, as we will see soon. Let's take a look here. No surprise, reducing the frequency will reduce the temperature almost in a linear fashion, because the power is linearly impacted by the frequency. However, the throughput also linearly will be degraded. So temperature will be reduced with frequency scaling nicely, but the cost will be very high when it comes to the throughput. And remember, with deep learning, we really like high throughput. When it comes to the precision scaling, you can see here, and the green line, it shows the accuracy drop for 20 different neural network models have been all of them analyzed, and then the accuracy or the average accuracy has been reported. We can see here for the 8-bit, the accuracy is quite high, no surprise, but then 7-bit is not too good, and then it starts to really drop very quickly. While the temperature is reduced, the accuracy is not maintained anymore. So therefore, the precision scaling, even though it could be perceived as a nice technique to reduce the temperature, however, it's actually a little bit limited. It has a limited capability, and at the same time, the accuracy can be severely impacted. Now, when it comes to the superlattice thermoelectric device, we can see how the temperature is dropping or reducing very nicely. More than 40 degrees can be reduced. Of course, the cooling cost is high, can reach 40%. Well, there is a trade-off. If someone really wants to reduce the chip temperature from 120 degrees all the way down to 40 degrees, no free lunch, as we used to say, and a cost of around 40% must be paid. Now, the superlattice thermoelectric device, I want to mention that it actually allows us to open a new door, because a new door for a new design space exploration. So if we put the thermoelectric device on top of the MAC array, we could actually cool down only the MAC array there, and that allows us to not reduce the frequency a lot, allows us not to reduce the precision. And now, based on the deep learning model and the neural network model, we can actually figure out how much we have to reduce the frequency, how much we have to reduce the precision, how much cooling cost we have to pay in order to satisfy a certain requested temperature constraint. This is an example of the new design space that we can explore when it comes to neural processing unit temperature management. You see here we have those different trade-offs: temperature, power, overhead, throughput, etc., precision, and then based on the requested temperature constraint could be 420, for instance, in data centers, or maybe 75 degrees for your mobile devices or for each device. Then based on that, you could figure out the Pareto optimal solution. This is an example about the effectiveness of such intelligent cooling on the TPU. We measured here, or we focused on the efficiency as a frequency multiplied by throughput divided by the power cost. We can see here how the efficiency this is the normalized efficiency, and we have different examples: ResNet, neural network, and BGG11, and mobile net, just as an example. The paper has all the results for the 20 different neural network models. Temperature constraint was here quite tough. It was like a 70 degree, which is really, really tight. And remember, originally you start from almost 120 degree or above even 120 degree. What we can see here, how for some models that can tolerate precision scaling, we are actually able to reduce or increase the efficiency by, let's say, around 3x, while the accuracy drop is very small. For other models, where, for instance, this mobile net, the tolerance for the precision scaling is almost zero, so we have to stick at the 8-bit, and then we have to pay the cost differently. So this is the beauty of having such larger design space to be explored, which will allow us to figure out kind of the different knobs, how they can combine in a hybrid way to get the best solution. Before finishing, I want also to introduce another kind of more fundamental, how to say, solution to the temperature problem. Let's remember what I have introduced at the very, very beginning of my talk. We said all of those happening, all those temperature problems happening because voltage is not really scaling down. And we explain it, or not me, this is, as it's very well known in device physics, this is attributed to the fundamental subthreshold swing, which is 60 millivolt per decade at least. And that's attributed by itself to those two capacitances in series. But can we make anything where we push this below the 60 millivolt per decade? In fact, yes, if we could achieve a negative capacitance. Why? Because if you look to this constant factor, the lambda, it's 1 plus something. And as long as this term is positive, we always have higher than 60 millivolt per decade. But if we could make it negative, we could actually make the lambda smaller than 1. And if it's smaller than 1, then we could actually push the subthreshold swing to go below 60 millivolt. But do we have a negative capacitance in the nature? Interestingly, it has been demonstrated that the ferroelectric material, under certain circumstances and certain capacitance matching, can exhibit a negative capacitance effect. That's amazingly important because instead of we have a voltage drop, as we used to have in any two capacitances in series, we have kind of voltage amplification. As a result of that, we can achieve the same on current of our transistor, but at much lower voltage, as this analysis that we have done at the 7 nanometer FinFET technology. We see here in the red curve, which is the NC FET, how it's a steep, could achieve the same baseline on current at much lower voltage without any increase in the leakage, without any increase in the off current. That means we can operate our circuits at much lower voltage without any loss in the performance. What that really means for neural processing unit? Well, we have recently answered that question, and we did the analysis using the complex framework that I have shown you, and it was using the Google TPU example. And we have shown that the power reduction can be around 40 to 50% in the systolic MAC array at the same performance. And this is all attributed nicely to the reduction in the power that's coming from the reduction of the voltage without a loss in the frequency. Let's remember the Google TPU, or in general the neural processing unit, they have this gigantic systolic array, consume lots of temperature, confined in one small area. If we could reduce the voltage without any loss in the performance, that means lesser power intensity, and lesser temperature, and that means less cooling cost. Therefore, we could solve the problem fundamentally if we could realize steep transistors or steep subthreshold transistors, such as the negative capacitance transistors, in which performance is not sacrificed while voltage is reduced. This will solve fundamentally the problem. Well, until these breakthroughs or to be adopted commercially, and we see such amazing devices replacing our existing mature CMOS technology, this will take lots of time, and we have to use our traditional solutions such as voltage scaling and frequency scaling, precision scaling. However, I just wanted to tell you there's lots of activities happening in a different research community in device physics and material physicists in order to solve fundamentally the problem. And I personally believe that would be, of course, the best, because this is where we can suppress the problem from where it starts. But it's not that easy, especially when it comes to replacing CMOS technology that is adopted for many decades. Before finishing, I want also to show you an example that instead of fighting against the temperature, and sometimes if you cannot fight against your enemy, why don't you try to live with that enemy? That's also, this concept could be applied for deep learning. Temperature is a problem because ultimately will cause errors. However, neural processing unit can tolerate errors if you train them with errors. That's not easy, but if you could do that, you could actually create deep learning models that inherently resilient against temperature effect. This is a third way to fight against the temperature. So either you will do your traditional solutions that I have explained, or you would go to fundamental solution like replacing your transistor, or if you could not do anything, why don't you live with the temperature effect and train your neural models with respect to temperature effect. That necessitates modeling the errors that's coming from temperature, and then go to your framework where you do the training and live with it, training with it. We have done this work in collaboration with Jian Chen from Dortmund and others, and we have shown that binary neural network, which is one of the new forms of neural networks, they are able actually to survive with errors. If we could model those errors and put them during the training, we see here how the different temperatures did not cause any drop in the accuracy, and this is an example where we could live with the errors. This brings me to the end, and if you are interested in those areas and based on your background, and I know this talk is for the CAS community, so if you are coming from circuit or system, you will find papers from our research group for different perspectives, how to say, starting from device physics, circuit to system. So please take a look, and I'm sure, or I hope that you will find something fits your background. Before finishing, indeed, I would like to acknowledge all our PhD students that contributed largely to this talk. Some of them left, like the analysis that I have shown for the temperature is coming from an old student, Hammam, that he's not, his name is not here, and some of them is here, and also acknowledge all our research partners from outside, as well as the funding agencies. This brings me to the end, and to summarize, first and foremost, fighting against temperature is inevitable in the upcoming technologies. The effectiveness of conventional techniques, frequency, voltage, precision scaling is limited and becoming more and more limited. Advanced on-chip cooling opens doors for new optimizations. Hybrid cooling solution is the key because it will allow us to minimize the cost. If we could not fight against the temperature, maybe we could teach neural networks to live with it. Error-aware neural network training is a key in this aspect. Errors are coming, whatever we try to do, errors are coming from the hardware. We have to make our neural networks live with that. There are many different walls facing our technology, and fighting the temperature, we are still at the very beginning. The path and the way is very long. Finally, AI is reshaping the future of humankind, there is no doubt. But the question is, at which cost? Many studies show that training a complex neural network can emit carbon footprint more than not only the lifetime of one vehicle, but 5 vehicles together. Therefore, it's now the right time to investigate how coupling innovations in technology with innovations in architectures can rescue. This brings me to the end, and thank you very much.
Thank you very much for your talk. Thank you so much again. That was a very excellent talk. I have a few questions. Maybe you could shed some more lights on the thermal issues and the thermal profiling that you did, and also how to fabricate the TEC layer. So let's take in parts. So in the slide 12, okay, you have a thermal profile across nanosheets and FinFETs. Can you comment about which tool, which TCAD tool was used to simulate this? And if the temperature profiles in the sheets and the fingers in the FinFETs, if they are basically at the given time for lattice temperature to equilibrate, because these tools can also provide electron temperature, they can provide hole temperature from the electron momentum distribution. So what's the best way to advise our students how to use those TCAD tools?
Okay. So thanks, Sergio. This is an excellent question. And actually, this is one of the very hot topics nowadays in device physics, because the self-heating is really big challenge for sub 7 nanometer devices. Here we have used the TCAD tools from Synopsys, the Centaurus device is process. First of all, we calibrate the TCAD with the measurements, and in this case, we have relied on publicly available data from Intel. And once we calibrate it, then we have to really calibrate all the thermal properties of the material. And that's not easy, but we keep calibrating until we should be able to match the measurements that we have from the devices. So once the calibration is happening and we are able to capture all the physics, including quantum confinement and all other type of defects, then there is a certain method, which is the conductance versus frequency, which allows us to capture, to calibrate the thermal capacitance as well as the thermal resistance. Once this is really happening, we are able actually to get even the thermal time constant, the tau. Therefore, we would be able not only to see the steady state, the static temperature, how to say, which is I'm showing here, for instance, as an example, but also, and more importantly, how long does it take for the heat, for the lattice to be heated up? That is actually, just to give you feeling, I'm sure you would ask that. Nowadays, in the 10 nanometer technology, it's already at the 1 nanosecond, and even several studies showed that they could reach a 0.5 nanosecond. That means the time to heat the transistor is getting very small, and this time, then the tau at the area of 0.5 to 1 nanosecond makes even digital circuits becomes already subject to self-heating. And in the old days, we used to think self-heating is a problem often only for analog devices, but nowadays even the digital circuits operating in the gigahertz regime, it started to become already subject to self-heating as well. So calibrations needs to be done with measurements, material, and then the only proof is we should see the frequency versus the conductance measurement, the GDS versus frequency. This tells us where it increases, and once we match this from the available data or the data that's coming from measuring the devices, then we would be able to calibrate the thermal resistance, thermal capacitance, and from there we can continue. If this
yes, thanks. Sorry, we have another question coming from Costa Rica, from Jorge Castro-Godínez. You know him. He's asking this question to you, Hussam. Basically, besides simulations, have you performed thermal measurements to the actual TPU chip, like the Edge TPU, with your temperature measurement setup? That's his question.
Yes, actually, that's actually a good question, and we have just ordered the Google TPU, the Edge TPU, to do this measurement pretty much soon. So the answer is not yet, but I'm planning to do this pretty much soon. So the Google Edge TPU, we have already ordered it, and we plan to do this analysis.
Thanks. Another question, follow up on the important issue of the let's say localized, or let's say fraction of a chip TEC, the thermoelectric cooling layer. That's an emergent technology that's been perfected, I think. And my question is on slide 17. How is the post processing to get the T layer over the chip? So we are familiar with the standard. I think it's slide 17. We are familiar with the standard.
Yes.
Yeah, that's one. Yeah, 17.
Yeah, actually,
with say the conventional packaging. So can you explain more about how to do the post processing after the chip is packaged? How to assemble, the TEC layer? How much post process has to do? How stable this process? And why, if you could put over the entire chip, why just put it over, let's say, the most active hotspot? So I imagine that the area you would like to scale as much as possible. So why not do chip-wide?
very good. Two questions, very good. First of all, you would be now surprised that they are actually able to grow up this superlattice layer on top of the silicon itself. So because the superlattice layer at the end is a PMP, so similar material to the semiconductor, therefore they are able actually to integrate it on the chip. And if you look to this picture, or if you look to the original paper from Nature, they were actually, it's not an additional layer, it's within the silicon itself. So on chip cooler. Other people, they did it, as you said, they did it on top of the silicon. There is advantage and disadvantage for both solutions. And then they integrated inside the thermal interface material. So those all will happen in the package, or so I would say in the advanced packaging. So there are two solutions. So you could really grow it while you are fabricating your chip itself. You could do it after that. There is advantage for every solution. Now back to your next question, why don't you just put it on top of the entire chip? That is actually goes back to the main goal that we want to do. We want actually to minimize the cooling cost. So why we would really cover the entire chip and pay large cost for the cooling if we could only cool down where the hotspot is evolving and emerging? So of course, if the entire chip is hot somehow, then why not put the thermoelectric device for the entire chip? But the larger, the more the cost, no doubt. Now, many systems like complex processors, and even for the neural processing unit, you have a very large area for the SRAM. Those SRAMs typically have very low power density, so you don't really need to cool them down. The best solution, and we also work on this, we have several papers on it, that you build a grid. The grid is you have many thermoelectric devices, and you decide at the runtime to turn on and off whatever you need, whenever you need.
Okay. Thanks, Professor Hussam. Another question in your algorithm part for the NPU thermal management. For the thermal management, you adopted precision scaling on the neural network, and as well as frequency scaling. My question is, I think that's addressed in slide 21. Since you're doing frequency scaling, can you mention more about using both the more conventional voltage and frequency scaling? My question is, in this paper, in this study that you have shown on slide 21, are you using also voltage scaling or just frequency scaling?
Okay, in this work, we have focused only on the frequency scaling. However, in other follow-up work, we also looked at the voltage scaling. The reason is, once we touch the voltage, it has a very large impact on the frequency. And that will really kind of screw up the throughput. So we wanted here to be more subtle, and we wanted to not go aggressively to the voltage, because we wanted to keep the throughput as high as possible. However, as I said, in this study, we only focus on the frequency as a knob. In other studies, we looked also to the voltage, but no surprise, once you reduce your voltage, frequency goes down very quickly. And another important issue, those advanced technology nodes, they already operate at 0.7 volt, and reducing the voltage, let's say 0.6 or 5, you start already to be, approaching the near threshold regime, and many problems, if you don't make your design really great in advance, start to appear, and you work in this area for almost a decade.
Yeah, right. Yeah, the throughput the throughput drop is too steep as you go below 0.7. Yeah, indeed. The last question on this middle slide on chip design. In the case of the Intel FinFET, you had to calibrate your SPICE models with some IV data that they published, or did you get the model card? Because I think they're very secretive about those SPICE model cards.
So everything is publicly available. So maybe I should not say Intel 14 precise, it's calibrated. So in other slides, I wrote calibration. So what we do, actually, we look to the available Intel data from publicly available, typically from IDM conference. And then we take these IV characteristics. We go to the TCAD, complex TCAD simulations to reproduce those IVs. And once we have those calibrated TCAD, then jointly with the BSIM group, we develop the calibrated compact model, the calibrated SPICE model, how to say. Then we moved and we characterized the entire standard cell library using this calibrated compact model. And once you have the cell library, then you can continue with the chip design. So the whole procedure, we explain it in the paper and other related papers, but this involves calibrations from device to SPICE to libraries, etc.
Very interesting. Very interesting. Well, just to close, we are about 10 minutes over time, but it's very interesting. You touched so many grounds and topics. We are thankful for you. Basically, on the negative capacitance, FET. Okay, in slide 29, you mentioned that the advantage of having a steeper slope on subthreshold. But it seems to me that still they have not got the red curve in this picture, having the same ion current as the conventional FinFET, the blue curve, and that's a problem that has been plaguing, hindering the adoption of those transistors, just because the ion current does not go as high as we'd like to. So what's the status of this development for the negative capacitance FET, which is I know you've been working in this subject for many years and published very important work on this. But from the device side, are they getting good enough ion from actual devices?
Actually, with respect to NCFET, they are getting very good ion. Even some of them, they showed an 2x improvement on top of the original ion. So this is amazingly good. The problems with the NCFET, and it's actually how to get the device without hysteresis. And this is not easy because the steepness of the slope that makes it really not easy to get hysteresis free. Also, all the underlying physics is still under debate, and whenever you don't fundamentally understand what's happening, then it's also difficult. Another challenge is if you really want to adopt those emerging technologies, you really need to ensure their scalability. And having a very thin ultra-thin ferroelectric device, ferroelectric layer, in which to allow the scaling, then there is a debate about if the negative capacitance effect could really still exist in 1 nanometer or 2 nanometer. There is an amazing work came from Sayer from University of Berkeley 2 years ago, or 1 year ago. He also showed that what has been believed for a long time, that the ferroelectrism does not hold or will be lost at the very thin layer, could still work with lots of material engineering. So this is the biggest challenge. It's the on current is doing well. The hysteresis free is very challenging. Having a very thin ferroelectric layer is not easy. And nowadays there's lots of investigations in not NCFET but ferroelectric device for memory. So this is a very active topic I did not talk about. But also nowadays, also even from logic, they talk about, let's have it as a better high K layer, high K gate, not necessarily to be super, negative capacitor effect, but at least, a better high K to have a better capacitor and a better electrostatic integrity.
Okay, thanks, Professor Hussam Amrouch. Thanks very much for being here with the IEEE Circuits and System workshop in South Brazil. That's organized by our CAS chapter in the Rio Grande do Sul state. I hope to see you again, all of you who are in this workshop. Remember, at 1:30 p.m. Today, on September 29, 2021, at 1:30. Jorge Castro will be working on accuracy for energy trade-off and approximate computing coming to the, let's say, rescue to energy efficiency. And so he'll look at this design paradigm of approximate computer. That's at 1:30, GMT -3. Brazilian time is going to be 6:30 p.m. Europe time, Central Europe time. Thanks a lot, Hussam, on behalf of the organization. I hope to see you again. That was very, very nice talk. All our students here in the chapter really appreciate. And last words for you.
Thanks a lot, Sergio. Thanks for all the organizers. It was a great pleasure. So I hope you enjoy the remaining of your workshop. Thanks for the nice.
Yes. We'll have 3 days more. That will run Thursday and Friday, 2 days more. So please come back at 1:30 to listen to Jorge Castro-Godínez on his talk on approximate computing. Bye-bye. Have a nice one until next section.
Bye-bye.
Bye. Thanks, Hussam.
Sure.
Okay, so everyone, thank you very much for being here for this presentation or this next presentation. We end here our morning presentation. So I'd like to thank Professor Bambi for being the session chair. And I'd like to remind you that we will come back at 1:30 this afternoon. Yeah. 1:30 this afternoon. And stay tuned that we have a lot more interesting talks. See you in this afternoon.
See you then. See you 1:30 p.m. Bye-bye.
It definitely changes your life. It helps you establish relationships that are really tighter because you already have a lot of things in common in the way you think, work, want to change the world around you.
As you get involved in IEEE, you really get a sense that you want to give back and to grow the community that you have.
I think there's a natural intersection between IEEE and its role in promoting the emergence of new technologies and entrepreneurship.
IEEE was a great channel to get to connect with professionals in the field. You never know what's going to happen when you meet so prominent people that are foreseeing the future.
What has IEEE brought me? I've worked full-time in power system automation, which we call smart grid, for over 41 years now, full-time. And the job changes I've made were through industry friends that knew of opportunities that I wouldn't have known otherwise and opened up the door for me. And many of these industry friends I met through IEEE.
What other place can you try to take a risk of doing our presentation skills and bringing in somebody from industry to talk to other scientists and engineers? I've been a member of IEEE for 25 years, and I still talk and mentor about this to this day.
IEEE has given me opportunities to network in terms of getting to know the leaders in the field, and also has provided an outlet for those leaders to know what I'm doing. So it's been good for both of us.
Given the world that we're living in now, where everything is pretty much about the internet and about connectivity, it's actually a good time to be an engineer and to be a telecommunication and networking engineer.
We know it's about the dynamics between people and people groups where our future is. And engineers can facilitate that, but they don't have the answers. It's the answering of us together as a community, not as engineers alone. So engineering is not going to solve the world, but it's going to facilitate that problem solving and getting together.
At IEEE, we believe technologists are the key drivers of tomorrow's innovations because we can really do what IEEE's motto states. We can advance technology for the benefit of humanity.
I always wanted my education to mean something more than just, doing a day job that pays my checks. I wanted to see how my background in engineering and other things could have an impact that can make somebody's life better.
Being able to connect our members with younger students and engaging them to emphasize that it is important, that what they are pursuing in their STEM careers is truly going to be the next thing that affects all of humanity, because all technology that we make is affecting people, and it's not just IEEE members, it's everybody.
Hello and welcome everyone to the IEEE Circuit and System Society Microlearning Initiative. As president of the society, I am really thrilled to reveal our new project that will bring benefit to our community and beyond our community. Education has been inseparable from technology because education and technology, they go hand in hand, and technology allows us to improve education delivery and to increase the reach of more learners beyond geographical limitations. Digitalization has allowed new opportunities to learn from available content via our devices, be it our laptop, our iPad, or even our smartphones. And today, everyone is talking about microlearning. It's an effective approach to enhance our knowledge and skills. Micro lessons delivers targeted lessons so we can easily gain new concepts one at a time. It's based on single learning that can naturally occur when we need to upskill or reskill ourselves. Microlearning allows us to immediately apply these new concepts to solve our problems. And this is why microlearning is so amazing. IEEE Circuit and System Society realize how much we all can benefit from microlearning. And that is why we are introducing our latest initiative, CASSW-RS. CASSW-RS is a microlearning initiative that hopes to advance and promote circuits and systems knowledge to diverse technical communities all across the globe. We aim to provide a platform for IEEE members and lifelong learners to learn and empower themselves via bite-sized content that is flexible to individual needs. CAS microlearning experience is personalized to meet your individual learning goal. CASSW-RS connects you to renewed experts in the field and utilizes wired learning framework. What is unique about CASSW-RS is that you could earn CAS badges by completing a number of micro lessons. Each micro lesson comes with a competency tag, and we encourage you to plan your own learning pathways and collect CASSW-RS points as you progress. We hope this will encourage you to explore and complete your microlearning journey, as every mile in CASSW-RS counts. We hope that the CASSW-RS initiative excites you as much as we are excited to bring it to you. This is a beginning for us. As we say, the journey of 1,000 miles begins with one step. So let's take that first step together.
definitely changes your life. It helps you establish relationships that are really tighter because you already have a lot of things in common in the way you think, work, want to change the world around you.
As you get involved in IEEE, you really get a sense that you want to give back and to grow the community that you have.
I think there's a natural intersection between IEEE and its role in promoting the emergence of new technologies and entrepreneurship.
IEEE was a great channel to get to connect with professionals in the field. You never know what's going to happen when you meet so prominent people that are foreseeing the future.
What has IEEE brought me? I've worked full-time in power system automation, which we call smart grid, for over 41 years now, full-time. And the job changes I've made were through industry friends that knew of opportunities that I wouldn't have known otherwise and open up the door for me. And many of these industry friends I met through IEEE.
What other place can you try to take a risk of doing our presentation skills and bringing in somebody from industry to talk to other scientists and engineers? I've been a member of IEEE for 25 years, and I still talk and mentor about this to this day.
IEEE has given me opportunities to network in terms of getting to know the leaders in the field, and also has provided an outlet for those leaders to know what I'm doing. So it's been good for both of us.
Given the world that we're living in now, where everything is pretty much about the internet and about connectivity, it's actually a good time to be an engineer and to be a telecommunication and networking engineer.
We know it's about the dynamics between people and people groups where our future is. And engineers can facilitate that, but they don't have the answers. It's the answering of us together as a community, not as engineers alone. So engineering is not going to solve the world, but it's going to facilitate that problem solving and getting together.
At IEEE, we believe technologists are the key drivers of tomorrow's innovations because we can really do what IEEE's motto states. We can advance technology for the benefit of humanity.
I always wanted my education to mean something more than just, doing a day job that pays my checks. I wanted to see how my background in engineering and other things could have an impact that can make somebody's life better.
Being able to connect our members with younger students and engaging them to emphasize that it is important, that what they are pursuing in their STEM careers is truly going to be the next thing that affects all of humanity, because all technology that we make is affecting people, and it's not just IEEE members, it's everybody.
Hello and welcome everyone to the IEEE Circuit and System Society Microlearning Initiative. As president of the society, I am really thrilled to reveal our new project that will bring benefit to our community and beyond our community. Education has been inseparable from technology because education and technology, they go hand in hand, and technology allows us to improve education delivery and to increase the reach of more learners beyond geographical limitations. Digitalization has allowed new opportunities to learn from available content via our devices, be it our laptop, our iPad, or even our smartphones. And today, everyone is talking about microlearning. It's an effective approach to enhance our knowledge and skills. Micro lessons delivers targeted lessons so we can easily gain new concepts one at a time. It's based on single learning that can naturally occur when we need to upskill or reskill ourselves. Microlearning allows us to immediately apply these new concepts to solve our problems. And this is why microlearning is so amazing. IEEE Circuit and System Society realize how much we all can benefit from microlearning. And that is why we are introducing our latest initiative, CASSW-RS. CASSW-RS is a microlearning initiative that hopes to advance and promote circuits and systems knowledge to diverse technical communities all across the globe. We aim to provide a platform for IEEE members and lifelong learners to learn and empower themselves via bite-sized content that is flexible to individual needs. CAS microlearning experience is personalized to meet your individual learning goal. CASSW-RS connects you to renewed experts in the field and utilizes wired learning framework. What is unique about CASSW-RS is that you could earn CAS badges by completing a number of micro lessons. Each micro lesson comes with a competency tag, and we encourage you to plan your own learning pathways and collect CASSW-RS points as you progress. We hope this will encourage you to explore and complete your microlearning journey, as every mile in CASSW-RS counts. We hope that the CASSW-RS initiative excites you as much as we are excited to bring it to you. This is a beginning for us. As we say, the journey of 1,000 miles begins with one step. So let's take that first step together.
definitely changes your life. It helps you establish relationships that are really tighter because you already have a lot of things in common in the way you think, work, want to change the world around you.
As you get involved in IEEE, you really get a sense that you want to give back and to grow the community that you have.
I think there's a natural intersection between IEEE and its role in promoting the emergence of new technologies and entrepreneurship.
IEEE was a great channel to get to connect with professionals in the field. You never know what's going to happen when you meet so prominent people that are foreseeing the future.
What has IEEE brought me? I've worked full-time in power system automation, which we call smart grid, for over 41 years now, full-time. And the job changes I've made were through industry friends that knew of opportunities that I wouldn't have known otherwise and open up the door for me. And many of these industry friends I met through IEEE.
What other place can you try to take a risk of doing our presentation skills and bringing in somebody from industry to talk to other scientists and engineers? I've been a member of IEEE for 25 years, and I still talk and mentor about this to this day.
IEEE has given me opportunities to network in terms of getting to know the leaders in the field, and also has provided an outlet for those leaders to know what I'm doing. So it's been good for both of us.
Given the world that we're living in now, where everything is pretty much about the internet and about connectivity, it's actually a good time to be an engineer and to be a telecommunication and networking engineer.
We know it's about the dynamics between people and people groups where our future is. And engineers can facilitate that, but they don't have the answers. It's the answering of us together as a community, not as engineers alone. So engineering is not going to solve the world, but it's going to facilitate that problem solving and getting together.
At IEEE, we believe technologists are the key drivers of tomorrow's innovations because we can really do what IEEE's motto states. We can advance technology for the benefit of humanity.
I always wanted my education to mean something more than just, doing a day job that pays my checks. I wanted to see how my background in engineering and other things could have an impact that can make somebody's life better.
Being able to connect our members with younger students and engaging them to emphasize that it is important, that what they are pursuing in their STEM careers is truly going to be the next thing that affects all of humanity, because all technology that we make is affecting people, and it's not just IEEE members, it's everybody.
Hello everyone, welcome to the IEEE CASS workshop. Don't forget to register for free on our website in the description. Subscribe to the channel, like the video, and enjoy this workshop. Now the session chair will introduce the speaker of the afternoon. Professor Leonardo Soares, please.
Hello everyone. So continuing the program of the IEEE CASS workshop, I would like to introduce the presenter Jorge Castro-Godínez. He is a doctor of engineering and is currently an assistant professor at the School of Electronics Engineering in Costa Rica in the Institute of Technology. He was a scientist and PhD student at the Chair for Embedded Systems in Karlsruhe Institute of Technology under the direction of Professor Dr. Jorge Henkel between 2015 and 2020. He received his 5-year engineering degree and master in electronics engineering from the Costa Rica Institute of Technology in 2011 and 2014, respectively. Prior, he worked as embedded systems engineer at Canon Technology from 2010 to 2012, and he was also research assistant at the Sino and Image Processing Lab in the Institute of Technology of Costa Rica, and took part in an industry joint research and development project with Bounce Imaging from 2012 and 2014. His primary research interest is in energy-efficient computing across the different abstraction layers, with a particular interest on approximate computing and machine learning on edge computing. So, thank you. In the name of the organizing committee, I would like to thank you for accepting to participate of this workshop, and the floor is yours.
Thank you very much, Leonardo. It's a pleasure for me to be part of this activity, and I'm very thankful for the invitation from Guilherme to talk a little bit about this very interesting research topic, and to share a little bit regarding what also I have been working about the topic. So thank you very much, and I hope that the people will enjoy the talk and ask any questions regarding what I'm going to present. Good. Just a little bit about myself. Leonardo already shared a lot. I'm starting here in Costa Rica as an assistant professor, so I'm trying to build my own research group. So it's an incipient research group. I'm calling it this way, efficient computing across the stack, because I'm very interested in the different ways that efficiency can be achieved in computing, and it's spanning across all the different layers where this can be done. And currently I'm keeping collaborations with my old research group in KIT in Germany, with the University of New York University in Abu Dhabi, also trying to establish some work with you guys down there in Porto Alegre, and also with some people in the University of Texas in Dallas. And mainly focusing in this type of works regarding with design automation, low power design, IoT and edge computing, as Leonardo mentioned, with all this emphasis in how to make the efficiency or computing in an efficient way, this type of applications in edge computing. And keeping, of course, some eye in the evolution of the topic of approximate computing. I will share a little bit about what I have been working, but I'm trying to move, so to say, at a higher level in the abstraction, moving into a cross-layer system-level approximate computing approach. That I will also, at the end, share a little bit of my perspective regarding that. Just to put in context, because this is something that it's very common. So Costa Rica, it's not an island. So Costa Rica is here in Central America. So we're kind of connecting the big chunks of this part of the hemisphere. and this is Puerto Rico, which is the island. So normally there is this confusion with people. I hope that for all our Latin American colleagues, it's not the case, but it's something funny that I always try to bring just to make sure where am I. Good. And just to tell a little bit about my university, it's the technical leading university here in Costa Rica. I would say it's a young university. It's reaching the 50th anniversary actually this year. And in the last decade, it's moving towards this, so to say, change of the paradigm that has been historically a more focused teaching university, so to say, but now moving into the steps of doing more research and being a more research-oriented university. So I wanted to talk a little bit about that. And even though we are a very small country, at least for instance in comparison to Brazil, and we have just a population roughly reaching the 5 million people, there is a growing industry that has been, I will say, very pleased with the technical capabilities that our engineers and the education that they're receiving mainly by the public universities. It's attracting this type of big companies. So we have an Intel facility here that, yes, back in the day, they start doing some manufacturing, but nowadays they do a lot of research and development here. We have divisions from Hewlett-Packard, National Instruments, Emerson, Boston Scientific, and many, many more, even Microsoft doing very interesting things more into the software side. But I wanted to just point out that even we are a small dot, so to say, in the map, we have been able to, so to say, attract this type of investment, this type of companies because of the technical level that our people is reaching. So this is something that also I'm proud of, and I'm happy to, in a way, to collaborate in that sense from the university with the teaching and the research that we're trying to do. We're going to talk a little bit about approximate computing and how this proposes a way to trade off the accuracy that we need for the computations in order to try to gain savings, and mainly focusing in energy savings. But for me, it's interesting to also recall and talk a little bit how is that we get here to the point that we are trading accuracy for energy efficiency, power, or area efficiency. Well, one of the things that I'm pretty sure you all know is that a long time we have been, or the industry have been followed Moore's law, which is an auto-predicted prophecy, so to say. And we know that what the industry has been trying to pace in the way that they develop the microelectronic is to try to achieve this doubling the amount of transistors every 2 years. Of course, this has many implications. And of course, by following this, it's that we have reached the point where we are. But not only Moore's law is something that the industry has followed and that has allowed us to have this massive amount of transistors in processors nowadays that span not just high performance computing, but also considering mobile devices, like here's represented in this graph, like for instance, the Apple system on chips, or even the high silicon keyring that the Huawei utilizes in their cell phones. So yes, we have been reaching this point and having this power in the consideration of computation power performance due to this insanely amount of transistors. But of course, this also has some other implications. We have also the large scaling that has been followed by the industry that has, in the past, tried to establish the way that we can keep scaling and increasing the number of transistors. But the challenges that also arise with this is more related into the power density, and which means that we need to dissipate more heat. And Hussam, early in his talk, Professor Amrouch, talked a lot of this, and how this is also a big challenge that we need to tackle. In response of all these problems that we were not able to keep scaling the way that the law was proposing, is that we have in the middle of 2000s this switching to multi-core architectures in a way to respond to this problem. But even now that we have still a big amount of silicon available, and that we could put like many cores into this, these thermal problems that Professor Amrouch was talking about arise. And then about 10 years or a little bit more, we start listening about this utilization wall, that we have like many silicon available, we are not able to use the silicon at the same time, and because of these thermal and power issues that we are facing. So this is also part of this motivation into looking for novel ways to do computations that can mitigate all these problems. And Professor Amrouch talked in his presentation about precision scaling, which is at its core one way to move into this direction to try to mitigate this power and thermal barriers that we're facing by trading the precision that we need. Not necessarily, or not only in the case of machine learning applications this is needed, and I will talk a little bit of that, but certainly is a way to try to tackle these problems that we have been facing. But not only from the thermal and the power perspective, this is a challenge, but also in considering nowadays all the informs that we are listening in the news, that the UN experts say, okay, we are reaching a point of no return in terms of the carbon emission and all the effect that we are doing into the environment. It's important also to take into account that the computation, or the way that we do computation, has an impact in that sense. And I came across this article some time ago and really opened my eyes regarding this case that mentions one particular NLP application that just the training of this application can consume even up to 5 times, or can produce a carbon footprint similar to 5 times the carbon footprint that an average car powered by fuel will produce in his lifetime. So this is very, very critical that we also pay attention into this, how our computation is in a way incrementing these environmental problems that we have. And not long ago, just a couple of months ago, also ARM came with some article pointing a little bit about that, into the need that we have to decarbonize the computations that we do, and that in some way nowadays the new Moore's law, probably the one law that we need to follow in the way that we do computing, it's trying to maximize the performance that we obtain per watt. And I think this is very important to consider, very important to take into account, and to be aware why are we now in this point that we need to find new ways to do computations due to the limitations, physical limitations, thermal limitations that we're reaching, but also the impact into the economics or into the carbon footprint that our computation is reaching. This is one thing at one hand, and in the other hand, another thing I want to talk as a motivation is that in many scenarios, we don't necessarily have or can afford to have a complete, accurate computation. And this idea of best effort that has been also in the community for about 15 years is not something new. By reading some book totally not related to technical part, I came across to this term called satisficing. Turns out that it was more into the economics, it comes from the economics field, and it was coined by Herbert Simon, which was a Nobel laureate. And in a nutshell, what he described is that not necessarily you have to get the very best option in whatever you're doing, but normally what you need is a good enough option. So you can imagine that you get into a bookstore and you have a huge amount of pens that you can select. And you probably can come across with your own benchmark, so to say, to define what is going to be the best pen that you need. But at the end of the day, probably what you need is just something that writes good enough. And then facing this big scenario of possibilities is overwhelming. And then probably you just need to find a compromise and just make the choice that satisfies you, and which brings also the need to find this equilibrium between the effort that you need to pay, so to say, to pick what is going to be the pen that you want to buy, and the benefit that you're going to obtain from this pen. In a similar way, the way that we do computation needs to find this equilibrium, this effort that we need to pay in order to obtain the computations and the benefit that we will obtain. Normally, we heard in different aspects that the more that we do, the better it is, but not necessarily. Indeed, this also come across this law of diminishing returns, which in a nutshell, what it says is investing more resources into a process not necessarily will improve its output in an indefinite way. And I took this graph from Wikipedia, but represents in a good way what it means. Normally, when we reach a maximum point of yield, a maximum point of performance, even if we keep adding resources to this process and thinking from the way of computation, adding more computing resources, not necessarily will make a big change into the result that we obtain. So we also have to take into consideration this, that probably we can reduce the resources that we apply and still obtain a good enough output. And this brings me in a way to this phrase, which is a little bit popular into the approximate computing community, that it is better to be vaguely right than exactly wrong. So in that sense, probably it's better to invest a little computation and still obtain a very good enough solution than invest tons of computing resources, but doing it in a wrong way. So these power and energy concerns are inherently now in every computing paradigm and any computing idea that we are looking at. And these are driving forces, not only the so to say the old school performance that we were looking at, which is still is very important, but this concerns, this power and energy concerns limit actually this part of the computation, this part of the performance that we can obtain. And on the other hand, there are many applications, many workloads that can have or can experience some error tolerance into their computations. And this is how, in a way, approximate computing consolidates into the research community as a novel, energy-efficient design paradigm for error-tolerant applications. I would say that this idea of using approximations is not new. It's what we experience, for instance, with even with floating point computations, that it's something well-known and well-established. But even though having, let's say, a 32-bit representation for floating point, we are still, in a way, approximating some values that could have more significant numbers after the floating point. Just to bring it into the consideration that this is not something new. And in many cases, and I see it, for instance, from the video game perspective, we have been okay with the graphics that we have been able to get because there were the computing resources that we have. But now we have more computing resources. Now we expect, so to say, more graphics quality, for instance. What is the idea in a nutshell of approximate computing? So we have into a balance the quality that we expect from the computations and the effort that we need to pay to actually do the computation. So we want to reduce in a controlled manner the accuracy of the results in order to then reduce the effort that we need to pay, the execution time, the circuit area, the power, or the energy. And in a way, and this is just to motivate, we can consider, well, we are doing some image processing. And of course, if we reduce the quality of our computations and allow, in this case, more errors that we can experience here as noise in the image, the idea is that we can then probably have more savings in any of these different aspects that we can consider, depending, of course, of the implementation that we have in mind. But in a nutshell, this is the idea that we try to chase with approximate computing. And I was mentioning that this is very important because we have a good amount of applications that present this inherent error tolerance. And for many, many reasons. For instance, because the actual inputs are noisy, we do use probably redundant information, even probably the algorithm itself produces some healing or some iterative process internally that can, so to say, cope with this type of errors, or just because there is no actual golden output. This is, for instance, the case of machine learning applications, where, for instance, in classification applications, we get this percentage of the probability of that, for instance, the image that we are putting into or a deep neural network is it's one type over another. And in many cases, and this is, for instance, the case of image processing and computer visions, there are perceptual limitations that our naked eye cannot distinguish up to certain threshold the amount of noise in an image. And it's particularly important that in applications like this, that goes from document research to eye detection, image segmentation, and so on, then the percentage of the application that represent an error-tolerant part is significantly big. In many cases, because there are some specific kernels that are dominant into the application. And these kernels present exactly this type of behavior, that they can be error-tolerant, that we can introduce on purpose inaccurate computations and then reduce the resources that we need. So from the approximate computing, there is, of course, many questions related to how can we utilize this type of techniques. And I will mention some of the different techniques that have been proposed across the stack. But of course, this is some question that always pops up. And I always receive this type of questions, like how much can I relax my computations? How much is a good enough answer? And one of the challenges that the approximate computing presents is that it's very tied, or the level of approximations or the type of techniques that we can apply, it's very tied to the type of application and the actual, let's say, consumer, user, or final implementation requirements to define, okay, how much can I relax my computations and still produce an answer that is good enough? And as I say, it depends on the application, depends on the final accuracy requirements. And something that it's very important to take into account is it's my critical section, the critical section of my application error tolerant. And normally we heard about this 80-20 rule, 90-10 rule, that normally 80%, 90% of the execution time of many applications is consumed just by a small percentage of the actual code, for instance. So we need to look at, well, is this hotspot into the application ever tolerant? And can I introduce approximations to then profit as much as possible of this relaxation, of this reduce in the precision, and then profit from the savings that I can accordingly achieve? Can I support, or do I need to just have errors that are deterministic, that I know that for the same input data I will achieve the same errors? Or can I tolerate non-deterministic errors? What I am trying to achieve is an energy reduction. I'm trying to reduce the runtime, or is some data density involved and I need to reduce memory transactions, for instance. So there are many different vectors that need to take into consideration. But in most of the cases, if not almost in all, regarding the approximate computing techniques that have been reported in the literature, is that the techniques are applied in the way that the data is processed, but not necessarily in the control flow. So we don't want to change, in most of the cases, as I say, the way that the actual flow of the computation is performed, but we want to have some impact in the way that we process the data, and then have the chance in that process to introduce these inaccuracies into the computation to then profit and get some savings. And in many cases, it will be required, from a high-level perspective, that we identify into our application which parts are actually resilient to this type of errors, where others will be sensitive, to then know in which parts we can introduce the different techniques according to the different abstraction layers, or depending on our final implementation, if it's something at a software level or hardware level, will define or will open the door to different techniques that can be applied. But this is something very important to have in mind, that not all parts and applications will be tolerant to errors, and that we need to identify which of these sections of the applications are actually error tolerant, to then define the techniques that can be applied into the application. And as I was mentioning, and this is at least from my perspective, I find pretty exciting is that at the different layers of the computing stack, and probably you are very aware of this type of, or this classifications of the different stacks in the computing, different techniques have been proposed. And this is very interesting because depending on the level or our final implementation, or where we already have our application, we can look at to see what type of techniques can be applied in order to achieve savings. And of course, at the different levels, we can set different questions to find, okay, how can we do, for instance, approximations at the electrons level, the circuit level? What granularity can we introduce approximations at the architecture? Or how can we, at the instruction set architecture level, define approximations, and so on, moving up to the algorithm level, to define how we can, for instance, can tweak and change our algorithm and still produce good enough results, but then achieving some savings by introducing these approximations in the way that normally the algorithm is produced. And different ways, different means of utilization, and different means of approximations have been defined in the community. I want to go for different levels and try to highlight at the different levels of this computing stack some contributions that I have done in the past years. And at the end, I want to share a little bit of my perspective of what is, at least what I see it's going to be the future into approximate computing, more particularly in the way that we can interact and introduce different techniques at the different abstraction levels in order to maximize the savings that we can achieve, and not only applying one of the techniques at one of the computing or the abstraction layers. And thinking about electrons, and at the end, and we know that what we do in terms of computing is just orchestrating electrons in a way to do certain type of work and then produce at the end certain type of computations. But one way that we can sort of say tweak this level of abstraction is decreasing the voltage beyond the circuit limits, or in this case introducing some timing effects while keeping in this case the frequency the same. So the idea in this case is, if I move into essential circuits like adders, many of, or most of the computations can finalize in less time of the critical path. So normally just the most significant bits will be stressing, so to say, this critical path, and then, for instance, voltage can be reduced, try to obtain savings, try to so to say cope to the way that these computations, the ones in the less significant bits, finalize. But of course, having certain drawbacks, that if we apply this type of techniques and we affect the most critical paths, well, these errors could be or could present a higher significance. And of course, this is input dependent, and this can be very dramatic if our information is located actually in the most significant bits. But one of the ideas here is, if we can tweak the voltage that we are applying to our circuit, then we can reduce significantly the dynamic power. And this has been applied. This is some work that has been reported in the literature to different cases. And what is interesting to see is it applied to different adders, for instance, to ripple carry adders and so on. We can experience certain error probabilities, but in some cases, and considering, for instance, the less significant part, can even be error-free in some of the cases for different factors of voltage overscaling. Of course, this behaves differently for different architectures of adders. But what is interesting to see is, even by doing this, as I say, this tweak into the voltage and reducing the amount of voltage, we can get some savings, and we can, of course, compromise the accuracy, not necessarily going into this level with the error probabilities, it's even higher, but according to the application, keeping it to a level where still the outputs can be, or can satisfy the results that you need, or can have the errors that you can tolerate. But this is just to put into context that even into this bottom layer, so to say, in the computing stack, we can have this type of approximations. One that has been insanely highly work in the community is at the approximate functional level. So many approximate arithmetic circuits, mainly adders and multipliers, have been proposed. When I was writing my dissertation, I made a quick search in Scopus, and about 35% of all approximate computing papers reported there in Scopus or indexed there were related to adders and multipliers, to approximate version of adders and multipliers. So the community has to spend a lot of effort and time into this part. And just to bring in as illustration, mainly the two types of approximate functional adders, in this case that have been proposed, are focused either in reducing the precision of the lower part of the computation, so affecting the less significant bits, and in this case is by performing an architectural change, so to say, in the regular way that we do the computation, and in this case, considering that we have as a ripple carry adder, something very, very traditional, very well known. And on the other hand, something called more into a high performance adders, approximate adders, where the addition itself is just cut into smaller additions that are still accurate, that normally are overlapping, that ideally will perform faster as the critical path is shorter in this case. These two types of approximate adder present different error profiles, here represented as a probability mass function, and of course different compromises and different savings that we can expect. So for instance, in this case, probably we're paying a little bit more of area, trying to achieve a faster adder, where here probably, in this case, well, yes, we reduce the delay, but significantly reduce, for instance, the power in the area by simplifying the way that the full adder we're computing and just replacing by an OR gate. But this is just to mention that, well, the community has spent a lot of time and effort into this. And it makes sense because many computations, so if we go, for instance, from the machine learning perspective, most of the computations that we care about are MAC operations, so it's multiplications and additions. But in many applications from the image processing domain, we see that about 75% and above of the computations are mainly additions and multiplications. So, of course, this makes sense that we can, or that we pay attention to this type of applications like Sauvel, Gaussian filter, Sharper and Laplace filter, and so on. And the reason that the community has spent time to propose this type of approximate components. And it's interesting that still, I mean, from many of those that have been proposed in the community, we just can still keep adding into the list many different components, approximate ones, but just, for instance, proposing a different way to perform the addition, to provide the summation bit or the carry out bit. And this has been taken into account, for instance, in having some designs where we can just replace from this plethora of different approximate components those that are normally accurate ones, and in this case, from a SED computation, just considering, for instance, a replacement of all these adders and performing an exploitation of the design space to then find those that are into a Pareto optimal frontier. So this, of course, it's what in the community has been proposed. Performing this type of explorations, of course, it's very exhaustive, but considers, for instance, a long list of different components that in the community have been proposed, and even for a very simple design, I will say, because it's not that complex in terms of the computations, we can explore the different scenarios that it's possible to achieve by introducing approximations. At this level, and not just by proposing approximate components, that by nature, I mean, are modifying the architecture that traditionally it's been used, the community has looked also a lot into how to perform an logic synthesis that introduces approximation. So the idea is to generate approximate circuits from accurate implementations, mainly performing a traditional accurate synthesis, so generating from an RTL description an accurate netlist representation, and then introducing approximations into this representation. So basically, it's performing a functional simplification, trying to make it simpler, either at this level, the netlist transformation, Some others have proposed some Boolean rewriting, so changing the Boolean representation and rewriting itself the so to say the RTL that we are taking as an input, and then having a synthesis which is accurate, or even moving a little bit higher into the abstraction by using high-level synthesis in an approximate way, which I'm going to talk a little bit later on. So back in the day, I was looking at this, trying to see what it was missing, because there are many techniques that have been proposed in the community regarding approximate logic synthesis, but we were facing a challenge where there were no open source framework where we can apply this type of netlist transformation based techniques to then have some exploration and see what we could contribute in that sense. So we were looking at that and decided to propose a small tool, so to say, to try to apply this type of techniques already reported and existing in the community, to see if we were able to propose any other technique. So we came across this tool that we call AXLS. First, we get a netlist generation, very traditional to what we do in an ASIC flow, but we define a custom netlist representation, in this case based in AXML, to perform then the transformations that were defined by the different techniques. So basically we get something that looks like this, and what it represents is a type of representation, in this case as a direct acyclic graph from the netlist description. But this XML representation provide us, so to say, a flexible way to perform transformation, to, for instance, perform some gate pruning and rewire the netlist, and then generate an approximate netlist from this transformation that later on can be, of course, passed to further to the synthesis tool to get whatever sequence metrics that you are interested in. But of course, in this process, and this is something that we saw in many of the techniques as they are reported, they consider exhaustive simulations in the loop, just to consider that any transformation that is applied still meets an error or an accuracy threshold that is defined. So just to make an illustration, so by applying this into a netlist representation that is accurate, so we were able to say to define, okay, yes, these are the nodes that we need to prune according to, as I say, the technique that is reported, and then generate an approximate netlist. And we did some small evaluation with two different techniques, one based in probability pruning, some other considering some exploration from the input to the outputs, and defining what was able to transform. But the takeaway from this is that now we have a tool that we can implement techniques, that we can look at these techniques and see what else we can apply. But something that was very interesting in the process and that we are looking at is how we can, sort of say, take away as much as possible this simulation step by looking at the netlist, looking at the transformations that are applied, and using machine learning based methods, perform a first estimation of the error degradation, how this transformation of the netlist is producing errors, and these errors are represented into the output. And this is something that we are actively looking at. So with this too, I try to cover some of the techniques at the electron side, or the electron layer, or the circuit layer. And I want to talk some into the microarchitecture level. So one of the things that the community has also been looking at is to approximate accelerators. So normally we know that an accelerator can be just a piece of hardware that we use to, sort of say, offload some hotspots, some frequently executed part of a code. So that's what we do, for instance, when we use some general purpose GPUs or some specific DSP that might be available into a system on chip. But from the approximate computing perspective, the idea is to then generate an accelerator that, of course, is going to execute some frequently executed part of an application, but that is also error tolerant. So the idea is that then we can exploit also approximations at that level. of course, there is a research challenge associated, and especially when we look to this plethora of different approximate components that has been reported in the literature. And it's, if we get an application and we get a set of components, then how can we perform, so to say, the selection of those components to build our circuit, to build our accelerator that will minimize the computation effort that we have, but at the end also will satisfy a defined accuracy. So we can look at this in a diagram in that way. So we get a lot of components coming in, and we expect approximate accelerators going out, but any of this approximate accelerator will be designed accordingly to the error-tolerant application and the constraints that the process receive. And particularly the way that we have been looking at is how to do this process, because you can do it, of course, manually, but how to do it in an automated way. So for doing it, we found one challenge. The first one was, okay, how can we estimate the accuracy when we use approximate components? A little bit like similar to this from this netlist representation that I was commenting before. But in this case, if we have, for instance, one of the solved kernels, and we replace the addition with approximate ones, then the question is, what is the error of the output? Well, normally the process is you implement your circuit and you go for simulations and then you answer the question. But of course, in a process that explores a very highly dense scenario of possible solutions, this is a bottleneck. So we look at different methods, at different ways to estimate, and this is one of contributions that we have, how the errors produced by these approximate components not only interact with other approximations introduced by another approximate component, but how also interact with other accurate operations that are, so to say, beyond the point where the errors are introduced. We came across to some rules that we can apply, and the evaluation of these rules show that, of course, the estimations that we do here at the left are not 100% accurate to those that we have as, or that we can obtain with simulations, here represented by these error distributions as a PMF, as a probability mass function. But we can get very good enough estimations also in this case to be used or as a guide in the process of the exploration of the design space. Another very important component in that process that we look at is, okay, if we are doing a lot of evaluations considering different scenarios, different components, can we also reduce the need, or the exhaustive need of performing every time that we consider a new solution synthesis to then get metrics and see if actually we are reducing or not the resources that we need. So we look at that and also propose some models that are also not 100% accurate. And this reminds me one quote, very, very funny, but it's very true, that all the models are run, but some are useful. And in this case, these models that we came out turn out to be useful enough to help us also in this process, that by replacing approximate components to get a first impression of what is the impact on the different, in this case, circuit parameters, from area to dynamic and static power and to delay. And by considering these two components, the accuracy estimations from one side, the resource estimations from the other, we came across to some design space exploration using this type of analytical model. So we take a behavioral description of the application, of what we wanted to map into an accelerator, produce a data flow graph, and from this data flow graph to produce an exploration. For a given error threshold, perform an accuracy estimation and a resource estimation as well. And then for a given approximate library, so a set of approximate components, mainly adders and multipliers because of the motivation I presented early, then have an optimization solver to produce an approximate representation of this DFG. We did it, as I mentioned, taking as an input C code, extracting from an intermediate representation the structure of the circuit, so to say, and from this DFG to perform this type of exploration. We took this exploration and in the first approach by using some taboo search and defining some fitness equation. We put this into an automated way to perform the exploration. The first thing that we saw is that this design space exploration was performing good enough and helping us to find also the solutions that were in the Pareto front for, of course, a given set of approximate components, and for defining one or in a specific accuracy threshold to be able to find those that were satisfying, in this case, not only the accuracy requirement, but also lowering the resources as much as possible. And we saw that, of course, our solutions were not 100% accurate, so to say, with an exhaustive exploration, but in 90% of the cases, roughly estimating, we were achieving the Pareto optimal solutions by this design space exploration. And as I mentioned, we took this design exploration that we worked, and we put it into a high-level synthesis flow. As I was mentioning, this is also one of the ways from the logic perspective or from the synthesis perspective, how to introduce this type of approximations into the scene. And in this way, what we did is just to hack basically one open source tool, in this case, LegUp for high-level synthesis, and introduce or approximate or the approximations, in this case, by this design space exploration, that was able to introduce approximate components into the design. Of course, further stages into the, so to say, canonical process of the high-level synthesis needed to be modified in order to pass information regarding the approximations, but at the end, in the RTL generation, take these approximate components that were used in the design space exploration and then generate an approximate version of the accelerator, and in this case, at the RTL level. And some results that we obtained and that we were able to look at is that even for a small degradation, in this case considering an accuracy metric called mean error distance of just 5, we were able to lower up to 30% the energy requirements. So this is something that shows that even for simple changes into the design, of course, performing the exploration in a faster way than it will be by just using the traditional method with simulations and synthesis all the time that we were exploring a different case, we were able to, in a fast way, as I say, obtain approximate results that we were reducing significantly the energy. Of course, and our tool was open to then define different accuracy constraints and then produce, so to say, the accelerator that was, in this case, minimizing the energy consumption for that case of that accuracy. And of course, as we were reducing accuracy, we were achieving higher savings, in this case of energy represented as a power delay product. But of course, this has an impact into the accuracy that we achieve. Which of the solutions is the one that I will pick? As I mentioned earlier, it will depend on the application requirements, how much degradation can you tolerate, and in some cases, and this is very important, or in many cases actually, and ours was not one out of the case, we were targeting for accuracy metrics that has an impact, of course, into a quality metric. So in this case, so to say, the impact in the quality is a byproduct of the definition of what accuracy we were targeting. But this is something that is also very important to look at, that in many cases, we need to look the other way around, and by defining an accuracy, a quality metric, because normally it's what we expect from the application as an output, we can sort of say draw back the degradations that we can apply to then define, for instance, what is going to be the accuracy that we need to target into our design. That was one work that we had been looking, so to say, into this microarchitecture level, how to use approximate accelerators and how to design them. But recently, some different works has been or still proposed, and recently this one at least got my attention because it was a very interesting one in which value similarity, which is one particular case in many applications that they present similar values, and by having similar values, then we can skip computations and then just reuse previously calculated results. So they propose, for instance, to modify and extend the instruction set architecture to then have this possibility to monitor the information that's being processed and then decide just to skip some computations according to some similarity. Of course, it's not 100% equal values that are being calculated, but similar. And then, of course, you expect that the results for similar computations, similar operations will be the same. So it's a very interesting way to also come into this abstraction level and introduce different techniques of approximations. What it was interesting to me at this were the speed up numbers that they were achieving for a very low degradation into the classification that they were achieving, because they were applying this to machine learning applications. So as I mentioned earlier, at different level of abstraction, different works have been proposed. In some cases, for instance, and this is very important, and Professor Amrouch mentioned it early, approximations have been applied to neural networks to, for instance, as pruning of the precision, just to make it lighter, the execution, but also from the other way around, neural networks have been used to replace error tolerant sections, trying to exploit the actual inexact nature of neural networks. So works have been also proposed to take some code, map it to a neural network, and implement this neural network as an accelerator. So for instance, taking some solver code, performing some training and defining some topology, and then just performing the replacement, so to say, not executing by code, also having then an accelerator, but this accelerator being designed particularly or inspired in this case by a neural network. And the works reported in the literature mention how they couple this and how they design this neural processing unit, how they configure, but how they exploit, and this is what it's interesting, this idea of applying or using a neural network for approximations, where the most things that we see nowadays, it's how we apply approximations to the actual neural networks. And very interesting speed up and energy savings are also reported in that sense, even achieving application speed ups up to 30, which is significantly important for some applications, where in some others, of course, it's more modest, the savings achieved. But also, and this is something very important, and Professor Amrouch mentioned earlier in his talk, we already have some specific computing circuits already designed and already commercialized to perform this type of deep learning applications, neural network applications in an ASIC. And many techniques have been proposed and introduced to this type of applications, as mentioned, quantization and pruning. But in the case of an actual chip, we are reduced a little bit into the possibilities that we have to introduce approximations. So this is a small case study that we did, a master student of mine and myself, using a Movidius Myriad X, these platforms from this Movidio company of Intel, and trying to exploit what type of approximations, in this case limited to the software level, can we apply to still gain from the inherent error tolerant nature of this type of applications when using this combination, a Raspberry Pi connected to this core. And something that we saw particularly for this scene classification application is that, yes, from a baseline perspective, it was achieving up to 20% improvement, just taking the application, not running it using TensorFlow into the Raspberry Pi, but just moving and using the accelerator. So we were just, by doing that, achieving a 20x improvement. But by using a combination of different techniques, and that's what we were exploring here, we were able to increase this performance and measure as inference per second, and 20x more, or a little bit more. So still, by using this type of applications or this type of implementation that we could consider a little bit fixed, that we can, or the degrees of freedom that we have to apply approximations it's well reduced just to the software, still we can get very interesting numbers. And what was also interesting for us is that from the baseline accuracy that we were achieving, but even performing these transformations and these approximations, we were able to increase a little bit, couple of percentage points, the accuracy of what we were using, and as I mentioned, increasing significantly the performance that we were achieving. And moving further into the abstraction level, software techniques have been proposed, mainly loop transformations that have been extensively studied in the community. More recently, some other techniques also considering the value similarity have been exploited, for instance, to perform replacements or from variables to variables to present similar values, or by performing also some statistical analysis for one application and one particular input data to see, well, what it's going to be the replacement that I can do. Can I change this variable for a fixed value, for a constant, and then reduce also the amount of computations that I need to do? And at least in my case, I have a small study looking also at this combination of, well, there is some pixel correlation and many, it makes, of course, total sense. And in images, we have a lot of correlation in terms of the values of pixels that are close by. And by applying this and performing some variable to variable replacement and applying also some loop perforation to look at the savings that we still at the software level can achieve. So very interestingly, by applying or by doing some combination of techniques, which was, for instance, this case here, by applying loop perforation and by applying some one variable to variable transformation, we were able to reduce, for instance, the execution time to a half and still maintain higher quality numbers, depending, of course, on the metric. But from the SSMI perspective or from the PSNR, still producing images with errors that normally to the naked eye are not perceptible, but still reducing, as I mentioned, the execution time here normalized about the half of the original one. And there are many, many, many more techniques that go also up into this abstraction level, applying minimization, reusing then values that have been pre-calculated, considering multi-thread applications, for instance, relaxing the synchronization, performing data type replacement. High performance communities looking a lot into these techniques, or also in the high performance community, but probably where we can afford to have custom hardware, looking at non-conventional floating point formats that can provide also a good enough accuracy for specific applications where, so to say, the dynamic range of the information is well known, and we can reduce the representation. And this is also what has been performed in the community and in the industry with the newer platforms, for instance, from NVIDIA, that now they support operations down to the level of 8-bit integers, and showing, as Professor Amrouch mentioned in his talk, that even by moving from 64, 32 bit floating point representations to this 8-bit representation, still good results are being achieved by these type of platforms and for a lot of deep learning applications. So I don't want to cover too much about that, but I want to probably share with you what it's the vision that I have, or the perspective I see for further into the approximate computing. One that I was mentioning is this gap that there is between accuracy and quality. I recognize myself that I have been working more towards an accuracy constraint and using the quality as a byproduct. But what is accuracy, what is quality needs to be redefined, and especially this particular case that we need to design for a particular quality and then draw back what is going to be the accuracy requirements that we need. One that I find that is very interesting is this cross-layer conceptualization and how we can apply approximate computing not just to one level, just to one part, but to different ones. For instance, not just into an approximate accelerator, but considering approximations at the software, the memory, or at the bus. And recent work, it's looking towards this, applying different approximations at different levels and trying to find what is going to be the best match, so to say, of the different techniques that are applying at the different levels, at the different components, different parts, and find, so to say, what is going to be the merge approximation that will produce higher savings. So I think this is something that is very important. Something that is missing in this process is how to model the errors that are being propagated through the different stages, through the different layers. And this is something that I'm very interested to look at. And the other one is that we need to look at the application level and try to design quality-driven implementations, but into an end-to-end consideration. So an application, a specific metric, it's needed to guide the overall design. And in this sense, there are also some works, probably I'm going to show this, where an approximate inference system is proposed, but different techniques are applied at different stages of the processing of the information. And this is also something that we need to look at, not just, as I mentioned, to one layer, but also to the different stages, and trying to use quality constraints to guide this process. So I really appreciate the time. Sorry if I was talking a little bit fast at the end, but I wanted to meet the time. But I think approximate computing, it's reaching some level in the community. Still, there is a road ahead to make it a more, or to bring it really to the mainstream of the design in the many different computing systems, and especially in the industry. But I think the work that has been done, it's very exciting, and it's very promising, the different venues, the different opportunities to look forward into this topic. And once again, I thank for the invitation, and for me it's a pleasure to have this opportunity to share with you about this very exciting topic.
Thank you, Professor Castro-Godínez, for this excellent talk. Now, the audience, do you have any question? Meanwhile, I would like to ask a question, specifically about, we have great opportunities to explore approximate computing, even considering the emerging applications, like applications related to Internet of Things. And we have lots of work and findings showing the benefits of using approximate computing. I would like that you explain your opinion about the big challenges you bring to us in the last slide, and explain how to bring a bridge, how to bridge the gap between the cross-layer accuracy and quality estimations, specifically, because how to bring this together and convey this in a product, for example.
Thank you very much for the questions. I will say, well, I don't have a definite answer. This is actually one of the questions I'm looking at currently, because at least by keeping the sort of the approximations at a single layer, I mean, there is already work reported how to do it. I mean, if you're doing something at the circuit level, there are different propositions how to perform these average estimations. Me, myself, I have proposed something. There are some other contributions. Also from the software perspective, not long ago, I learned from the high performance community, also how they perform this by changing, sort of say, the format or the precision that they were using, how they sort of say take this back to perform an analysis and define, okay, these approximations or this, in this case, precision scaling that we are doing is still producing good enough results. But this is still, as I mentioned, remaining into a single layer. Moving cross layer, this is something that we need to still look at. I'm not quite sure what is going to be the solution. By now, what people is doing, and in this case, I was sharing a little bit of this, that it's work from Professor Benjamin Carrion Schaefer in University of Texas and his group. It's something that are also not yet quite there. I mean, most of what they do is to perform simulations, to run the system, and then see if the approximation that they are applying and the combination of such approximations is still meeting any maximum error that they can tolerate. So these, at this point, still cross-layer is focusing into simulations at any of the levels that can be performed, probably still from the C perspective, in this case, that they use high-level synthesis to, so to say, to generate all of these components that later on are approximated. So this is also the philosophy that they follow. But the errors estimations are still remaining, so to say, to a single layer, and then let's see how they behave. This is something I'm looking at, as I mentioned, trying to see if there is possible in a way to abstract the way that each of the layers is contributing to an accuracy degradation or to a quality degradation, looking at the actual accuracy or quality output requirements that you have, and to see if it's possible, so to say, to make a backwards map, so to say. And this is very important because something that it's possible to explore here and has been explored into the circuit level with generating, so to say, approximate accelerators, is that you can have, so to say, a path producing certain errors that can be compensated by another path producing errors with similar magnitude but opposite, so to say, sign. And then that at the end you can compensate this type of errors. So this is something also that by having this type of estimations at a cross-layer perspective, we can see if we, for instance, can introduce some approximations, for instance, at a hardware level, in this case, at some accelerator level, that then can be compensated by approximations that we can introduce at CPU. So then we can go more aggressive in terms of the approximations, knowing that we can compensate and then meet accuracy or quality constraints, but by being free to go more aggressive, of course, achieve more savings. So I think it's, as I say at the beginning, it's a very open question. I do not have an answer yet. And this is something actually I'm looking at, because I think it's important to have it in order, as everything in the site space exploration, to reduce the time that we need to spend, and then to have a better knowledge of what we are doing, and then look at these possibilities of going more aggressive into approximations by knowing that we can compensate other errors produced by different layers. Yeah.
Okay, thank you. We have time for one more question from the audience. Professor Sergio Bump, he thanks for your talk, and the question is based on the leg up high-level synthesis software, and its first generations were heavily biased towards FPGA implementations. And his question is, how did you direct the leg up explorations with pragmas for the data flow architectures in which you exercise DSA?
Thank you very much for the question, Professor Bumpy, and greetings from Costa Rica. Yes, actually, the leg up tool is meant more for FPGA in that sense. And actually, the number of, so to say, of pragmas that they support, we were not, so to say, touching those pragmas. And actually, it's part of what we did. For instance, we were not reusing functional units. By reusing functional units, you got to take into consideration with more, with more care, so to say, the error propagation and so on, because you will be reusing components, and of course this limits also not only the savings that you can achieve depending on the approximations that you apply, but also the error that you will be producing. In our case, even though we were hacking, the leg up tool meant more for an FPGA flow, we were looking at the ASIC flow, because we were using this type of approximate components that have been reported in the literature more for this type of implementations. Because this is also a challenge we saw at the beginning where we were exploring, that most of the components that have been, and approximate ones, in this case adders and multipliers, that have been proposed in the community, when you, so to say, do the FPGA flow, you don't really get the savings in the same proportion that you can get in comparison to an ASIC flow. And this is why in recent years, probably in the last 2 or 3 years, there are some research groups that have been proposing a specific approximate adders, a specific approximate multipliers that can be implemented into an FPGA, and then they can produce like really the savings that you expect in the FPGA by achieving the same sort of say accuracy degradation that the counterparts for the ASIC flow. So this is something I haven't looked yet at, but it's something that is also interesting to look if the methodologies and the proposal that we have into the LegUp tool, we can use it but for these components that have been designed specifically for FPGA to take advantage of the savings that can be achieved of the FPGA because of this mapping process, right? But in our case, and the results that we reported and our ICCAD paper last year are meant, so to say, for an ASIC flow. So we keep the utilization of the tool, but once we were, so to say, targeting our system was more into an ASIC rather than, or thinking into an ASIC flow rather to the FPGA because of these limitations that we first experienced, and then later on by looking at the literature, we saw that other groups were proposing components as specific for FPGA platforms.
Okay, thank you, Professor Castro-Godínez. I would like to thank you again for this excellent talk and excellent topic about approximate computing. So before I close this session, I would like to inform you have a short break, about 4 minutes, to start the next section. And it was a pleasure to me to coordinate this section with Professor Castro-Godínez. See you.
Thank you very much.
Hello, everyone. Let's turn to our event scheduling. The next talk is Jimmy Tarrillo. I would like to invite the Professor Fernanda Castellmin to introduce the next talk. Hi, Fernanda. Your mic, yeah, okay.
Yes, okay, yes, sorry. Yeah, so good afternoon. It's a pleasure for me to be here to introduce Professor Jimmy Tarrillo. Professor Jimmy Tarrillo is a professor at the Electrical Engineering Department in the Universidad de Ingeniería y Tecnológica from Peru. He received the Electrical Engineer degree from Pontifícia Universidade Católica do Peru in 2002, and the Master degree in Electrical Engineer in Pontifícia Universidade Católica do Rio Grande do Sul, Brazil, in 2009, and the PhD degree in Computer Science in the Federal University of Rio Grande do Sul in 2014. He was my PhD student, so it's a special pleasure to be here introducing him today. Additionally, he worked in Antwerp space in Belgium, developing a soft error injection platform for soft errors in SRAM FPGAs. His research interests include embedded systems, software error mitigation techniques, and low power consumption on FPGAs. And he's going to be talking today about critical embedded systems for the Andean areas application. So thank you, Jimmy.
Hello, Fernanda. Hi. It's nice to see you and to hear you and to be here. Thanks for the presentation. Thanks for the organizations to invite me. Yes, I will present today the development of critical embedded system and Andean applications. This is a review of some of the works that I am working here in Peru with my undergraduate students. And I'm going to introduce first something about my place to work, where I work. This is a building of the university. It's a small university, but it's a beautiful university too, I think, the architecture, at least. This is a private university, and we start a few years ago in 2012. And this architecture will be interesting because it received some prize for a world-based building. So we are very proud about that. These universities, now there are 3,500 students around, and we have 12 undergraduate programs. We just have 2 graduate programs on computer science and civil engineering. As I said, this is a new university, so we are starting to build up. And this is a challenge, interest challenge, and very good point to start with the development of engineers and science here in Peru. We are around 78 full-time professors, and we have also international faculty. The female faculty is 30%. This is a challenge too in Peru because I think as other places, there are not many female faculties or researchers, so we are trying to increase this. The university also have some research centers. CITA is related to research of water in Peru, also in bioengineering and other areas. And in Peru, we have also students from everywhere. And one of the goals of the university is to have many scholarship students with scholarships. So this is a way to see different parts of the Peru, because Peru is a small country that it's very different places according to the geography. So this is the start point of the presentation about the Andes. As you know, maybe Andes is a mountain chain across many countries in Peru, in South America. Andes, sometimes when we think about Andes, we think about mountains, beautiful landscapes, and some cities, but also of mining, because as you know, in Andes there are many mining activities and many people. But also it's so far places from the city, so they have this involves some challenge. Andes, the length of Andes is 7,000 kilometers. It's about 500 kilometers of the width, and there are many high mountain. The highest mountain is Aconcagua. It's in Argentina, and cross, as I said, 7 countries: Venezuela, Colombia, Ecuador, Peru, Bolivia, Chile, and Argentina. All these lines Andes. So as you can see, Peru, the coast, it's a very thin line. Lima is situated in the coast, in the river of the Pacific Ocean, and around 24% to 21% of the territory is Andes, is mountains. So we have a lot of populations. So the topic of this presentation starts with a brief Andes location description, because we will see that some particular conditions will define the technology that we must use. After that, I will explain some technological challenge in remote Andes area, because Andean is not only cities, but also is mountains and really difficult places to work. And then I will present 3 projects. This is a graduate thesis project, and also some projects that I involved now. So, in the case of Peru, in Peruvian Andes, as I said, it's 28% of the territory. All the brown part is the Cordillera de los Andes mountains. And we have many cities here, not only mountains, also cities and small populations, communities. The population is around 28%. It's around more than 8 million people living here in mountains, in highest part. If you are, for example, driving from the sea here, from the coast, and goes to the Cordillera, it's like in 40 kilometers you will start to climbing the mountains. And so you have many cities, not only in the highest places in brown, also in the yellow part. According to if we talk about the snowy mountains, we have around 30 snowy mountains above 6,000 meters above sea level. So 6,000 is very high, but as we will see, this is a special condition. But also we have more than 1,000 snow mountains above 5,000 meters above sea level. So for Peru, 5,000 is relatively close. I mean, there are many places populated with in this area, and also we have more than 2,000. No, we have more than 2,079 glaciers. This is the block of ice, water ice. So we will start to check some conditions. We'll describe the conditions of working in these places. In the highest part, in the top of the mountains, we have snowy mountain glacier like this. These in general are unpopulated areas, but there are some people living here. Not too much, but you can find people living with small communities. And for example, one of the big problems that we have is that greenhouse effects makes that the increase in the water sea. For example, here in this mountain, In these glaciers, we have a lake here. So when you have increasing the level of this lake, this could generate floods. And huaicos. Huaicos is a kind of flood that we call here in Peru. That is, the difference is that it's a flood, but with a very, very small rocks, and they destroy everything. So it's the consequence when you have greenhouse effects. We have the problems that water will increase, and the water increase could generate the flood on huaicos. And if you think about this, that these places are around 5,000 meters, 4,000 meters, 6,000 meters. So the energy would decrease or goes the rocks and water is very high. So it's very dangerous, and the catastrophic effects for population field in general. So rivers are also rivers that you can find here in the sea level. Many sea rivers start in these high altitudes. For example, Bandero River starts in 4,000 meters. As I said, there are many places with people here. So, of course, they are monitored by sensors, but this is real remote places, so that the sensor must be very careful. We have some experience, for example, the glacier lake this glacier lake that is 4,000 meters had that kind of problem. And one of the problems here is that, of course, you don't have any Wi-Fi or wireless communication or network. You must develop this kind of links. Energy, of course, you don't have energy, or you don't have grid energy. You must to take, for example, with solar panels. And if you think about this, that is to climb to that place and install all of this is not so easy. So give maintenance of this is not easy too. It's very costly, personal costly, and money of costly to go here continuously. Obviously, it's not all about mountains. We have also human activities at high altitude. Not only snow mountains, yeah. So when you are, for example, in 4,000 meters, 3,000 meters, you have many population, but the population mainly are they have agricultural activities. And when sometimes we think about agricultural activities, we think about very small, very big field places, very flat places. But in the case of the mountains, that's not true. We can see some photos here, for example, that you have all of these are field for agricultural activities. There are small places. There are many small places. So to go to for example, to put big machines, big trucks, is not possible. So most of these activities are by hand. All these places are surrounded by mountains, so communication is also difficult. The access, for example, to internet here is very difficult. You have some cities and some places, but it's not in whatever place. So the agriculture is one place, also one activity that is affected for that technology development. And remember also that these places are around 4,000 meters above the sea level. So also communications are a problem for these places. Other human activities in high altitude are mining activities. Mining activities is one of the most important activities in Peru. We have mines with copper, for example, the second main in the world. This is some photos in these places. For example, the first photo is in La Oroya. It's a place around 5,000 meters, 4,000 meters, 4,000 meters. We have buildings and we have all the mine. But this is not the highest. The highest is the highest mine in the world is La Rinconada, that is in Peru also, and it's located at 5,400 meters above sea level. Here are the mountains, and here are the mines, and here are the buildings. So it's a city mining. We have many people living here. In the Andes in general, if we check the highest mines in the world, we can see that in the top 5 we have the Rinconada in Peru, 5,400 meters. Cerro de Pasco, also the second world highest is in Peru. Cerro de Pasco, this is the first photo. The third one is El Alto in Bolivia. The fourth one is in Potosí, 4,000 meters, also in Bolivia. And fifth is in San Carlos de Puno in Peru. So this is a point to think about this. Mining is usually think about high-level technology. Yeah. But high-level technology usually is used for all other kind of places. For example, many of these technologies think about mines that is not so high. And I have reported from mining professionals that they have several problems with that, not only for the pressure, because you have different pressure there, but also for the electronic devices. So in good part, in some way, this is related to the altitude, because as I said, these kind of machines are designed for not for so high altitude. And since the more quantity of mining is not in altitudes, so companies don't develop technology for this, or it's very expensive, to design something for this. An ecological side effect, as we know, we have a contamination of the air, but also and mainly the contamination of the water. So there are some techniques to avoid this, but also we don't have only mining from companies, but also from illegal or no controlled mining activities. So the contamination of the water and the air is a really, really big problem in Peru, in this part of the Andes. So also we need to monitor these kind of parameters, like pollution in the water and the air, and also developing technologies. Of course, we don't have only mountains, we don't have only fields, we have normal activities, and whatever normal activities in whatever city. For example, we have hospitals, transportation, and these are critical activities because if some error happens in this kind of machines, people can die. So these equipment also need to work at high altitudes. And sincerely, if you go to these cities very, very high, for example, 4,000, 5,000 meters, you will not see maybe so well equipped hospitals. We don't have many hospitals in that place, so people must go to, for example, to Lima, to other places. So I consider that also we need to develop some technology, but thinking about special conditions. This is not remote, that's true. This is not a remote place because these places are in the middle of the city. But as we will see, to have activities in high altitudes, we could have some problems. Checking, reviewing technologies in mountains, mining, agricultural activities, we have some common challenges in these places. First is they usually are very difficult access places. So to install something, for example, in a mountain, a high mountain, it's not easy to go every day, for example, to review, to check the status. Other problem is that we have data places usually have a lack of GPS network, so you don't have phone calls, we don't have internet, or it's very, very difficult to access to this. Another point is that we have a lack of energy in the sense of that we don't have a place to plug your equipment. You have to harvest the energy, maybe by solar panels, and accumulate in batteries. But solar panels is also a bit difficult to go to there. When you have a lot of rain, for example, or dust, the solar panel can be covered and will not work properly. Finally, as we will check in some slides, we have an impact of the neutral radiation from the cosmic particles. So if we don't have, if the place is difficult to access, so we need long energy autonomy. In general, maintainability must be high, must be low, in the sense that we don't have to go. It's difficult to go every day, as I said, to review, or every month, for example. So we need 2 points in here: energy autonomy and high reliability. And this, for me, is very close to maybe some aerospace applications. Of course, in aerospace applications is that, for example, for aerospace, for the space applications, the radiation levels are very high. We have different particles and so on. It's more difficult, yes. But also we have a radiation effect. And also, of course, if you have a satellite, for example, you will not go to repair that whatever moment. It's not so easy. You don't do that. So this is the closest thing that I see here in the Earth, in the ground level, because some mountains are very difficult to access and very risky to go. So the idea is to develop technologies and maybe later there to work for 1 year, for 2 years, for 5 years, for 1 month, but not for a week. There are some applications now, for example, that people need to go there to see the measurement of the equipment, or to go to implement to do the measurement process. So that's not a problem. The consequence of that is that in general, in the Peruvian Andes, and I could see maybe in other places, not only in Peru, to take information from these places is not so easy, because we don't have technology there. Because also common technologies are not prepared to these conditions. So this is the motivation, this is the point of this presentation, to talk about this challenge, for a common challenge for developing technology for high altitudes in the Andes. And of course, I hope that someday we can, in South America, can develop a technology to develop all these areas that as I shown, are not small. There are many people living there, and there are many places and activities happening there. So the first point, in the third requirement, energy autonomy. We know that energy autonomy is a power that you use, the power consumption of your component in a time. And we can split this equation, and the energy is very important because, as we know, energy will depend on the autonomy of your battery. For example, your battery have a limited energy. Of course, you can use solar panel, but as I said, you have two problems with solar panels. Of some points, issues in solar panels. The first one is that solar panel sometimes is covered by dust, and you need also to go to clean that, or rain, or whatever. The other point is you must to carry out that solar panel and climb the mountain to put that. And it's real that you don't have many people living there, but in some places you can have some problem with vandalism to the solar panel. So of course we need that. We use, in fact, solar panels, but the idea is also to reduce the size of the use of this kind of technology. So our work is to reduce the energy consumption. So we need lower batteries or lighter batteries, and maybe not solar panels, or a very small solar panel. So we split the formula into parts, the power and the time. So power is, you have two parts also, the static power and dynamic power. So static power depends on what? The transistor technology. So many words you will find about how technology are developing to reduce the power consumption. So we need to use that kind of component, but not depends only the total power of the transistor technology, also depends on the dynamic part. So in the dynamic part, we have the capacitance, the supply voltage, the coefficient of the factor of transition of the flip-flops, and the frequency. From this part, we can take the strategy of reducing the supply voltage, for example. So this is also part of the technology. If we reduce the voltage, the problem is that your transistor will be more sensible to some faults, for example, for neutron radiation. But it's an option. The other option is to reduce the frequency. And if you reduce the frequency, you will have a less power consumption, but also your system, your performance will be decreased. So the idea is to not decrease the performance. So how we can get that? A possibility is to, for example, use parallelism or a pipeline, some kind of parallelism of the system, or modifying your algorithm. So the idea is to to have very short power consumption in short time. So in that line, you will decrease the energy. On the other hand, you have the time, the other argument, and also the time. You can reduce the time if you want to reduce the energy, maybe by means of algorithm or the architecture. One more time, this means use parallelism, some kind of pipeline, for example, or multiple cores. And that's an interesting strategy. So we will reduce both the frequency and the time. If we reduce both, we will reduce the consumption. The other point is the reliability. Of course, we have a problem, for example, with rain, but we can protect that with some roof or some materials that is possible. But other point that we must check in the case of Andes is a non-ionizing radiation effect in circuits. Radiation effects, non-ionization, radiation effects is that it's not permanent faults. You have transient effects. So that transient effect means that maybe your application will stop, and you must to restart the system in order to return to your the first part of the process. But of course, you cannot go to climb to the mountain and just push the rest button. So this is a problem. These effects, what generate this kind of effect of radiation will generate a single event offset in register, for example, in flip-flops, in memories, in the control path. So if you have your system based in RAM, it's RAM memory, for example, you could have a problem there. So in ground level, we have neutrons. Yes, we have. In fact, in the Van Allen belts protect Earth from whatever cosmic or galactic cosmic rays, for example, some problems. Protons, electrons, but the particle that cross the Van Allen belt is a neutron. So this neutron that cross the Van Allen belt and arrive to the ground level will have a energy of the speed of the particle, and will be higher when you are in higher altitudes. This problem, it's worse when you have a smaller transistor. And we know we have new technology. New technology involves smaller transistors. I know that there are efforts, and there are new technology that are more reliable transistors than some years before, but the effect is the same. The trend is that if you have slower transistors, that's mean new technology, you will be more sensible to neutrons effects. So this could limit the technological development of these kind of cities, of these kind of places, and limit also the capacity of monitoring places, monitoring all the highest altitude places. I would like to share some this word that is not new. It's 2013, but you can have in the literature different publications about radiation effects in transistors and in ground level tests with environment neutrons. In this paper, the author found some effects in Israel memories placed in Puno. Puno is a city in Peru, in the south part of Peru, the mountains, and an altitude of 3,889 meters above sea level. I don't know if you know or you heard about the Titicaca Lake. Titicaca Lake is placed in Puno. Also, moreover, these experiments were implemented very close to the Titicaca Lake. And Titicaca Lake, if you know, you will see a lot of people living there. And the other point was in Puy-de-Dôme in France. It was 2,800 meters above sea level, so lower level. And they count the neutron flux, and they compare to New York City, that is a place, a ground level place. So of course, Puno, it's very high compared to New York City. It's 9 times. This is the kind of experiments, equipment of the experiments, and this is the results. So these experiments were performed in 2011 and 2012. At the right side of the slides, we can see the normalized integrated fail in number. They used different technologies. They used 90 nanometers technology in these experiments in France, and also 90 nanometers in Puno, and other technologies 130 nanometers in Puno. So this technology now is very old. I mean, you have now common use of 12 nanometers transistors. So what is expected is that the radiation effect will be higher than this. And in that time, the results say that, for example, in Puno, you start to find faults in the first 100 days. This means less than 3 months. So maybe you put some application there, you will have some faults. It's possible to have faults. I repeat, this is with an old technology fabrication transistor. Right now, I was looking for information, the new experiments in that place. Unfortunately, we don't have yet, but we are working on that. And this is the comparison with New York City and Puno. So in the internal part of the experiment, I mean, they put the experiment inside a room and outside. So what option we have? I repeat, this is just for neutrons. I'm not talking about other kind of problems or reliability related to rain and some others, because that kind of problems you can find in other places. But what is particularly interesting in Andes is the high levels neutron flux. So what option we have? We may to implement fault tolerant techniques, so we can implement tolerant techniques in different levels. One option is to have a device redundancy level, and this means that I will reply 3 times, for example, TMR. Replay the device and have a voter, so we will decide, the system will decide which is the correct answer if some of them are wrong. So this technique will mitigate the fault. If you have microprocessor, for example, you can protect the memory, for example, inside of the microcontrollers. If you have microcontrollers, you can protect the memory with techniques like ham and Solomon. In these years, it's common to find memories with that techniques implemented by hardware. So it's more reliable, but also you can find faults in the control pad. So in the register, for example, of your flags of your CPU, your ALU, for example. So exists some techniques for microprocessor by coding. But all these techniques are just to mitigate the problem, not to eliminate the problem. Other possibility is to use FPGAs, field programmable gate array. These components, you can define the circuit inside of the chip. So this is very good because you can use implement a TMR but inside of the chip, not only the device. So there are several techniques and still existing new techniques to increase the robustness of the circuit inside of the FPGA. And all this you work in RTL level redundancy. This means with architecture, not the construction of the FPGA. There are other words trying to looking for have a robust, high robust FPGA. But also in RTL level, this means with architecture you can develop it too. So let's talk about some minutes about the FPGAs. We have a requirements of high reliability. Let's remember a bit of digital circuits. If you have a digital circuit system, you will have some combinational circuits, sequential circuits, and so on. So the circuit is composed by combinational circuit and flip-flops. But the point is, in FPGA, this circuit is described in VHDL, for example, or Verilog, and implemented in configuration bits. You define to the FPGAs in configuration bits. The question is, where is the configuration bits allocated? So these configuration bits can be located, depending on the technology of the FPGA, in fuses, for example. It's like a fuse, like lines, fixed lines. Can be also implemented in flash cells, depending if you have a flash-based FPGA or SRAM cells. Commonly, we will find more power or more resources technologies in SRAM cells, SRAM-based FPGAs. Flash cells are good because in that case, we don't have problem to protect the configuration bits. You have anti-fuse-based FPGA or flash-based FPGA, the risk of your fault will be maybe in the flip-flops and memory, in the registers of your system and the memory of the systems in general. So you can implement at the RTL level. Something is to replay or replicate, the circuits, and it's good. If you have SRAM-based FPGA systems, this is you have a plus another problem, that your configuration bits are susceptible also to these faults. These faults are a bit flip. This means that if you value, the real value is 1, for example, flip to 0, or from 0 to 1. So if you have these faults in your circuit, in some flip-flop, maybe you will have problem. Because maybe in that moment, that flip-flop will not used. If that flip-flop is not used, no problem, because the bit flip will occur, but your output will not be involved in that problem. But if, of course, you can propagate the faults and have a problem in the final of your circuit. But the problem with the SRAM-based FPGAs is that not only you will have in that kind of flip-flop, of course, this technology is the probability to have a problem in a flip-flop is lower than a configurable cell. So if your information cell is affected by the neutron, for example, for a single event upset, you will lose or damage your circuit, to design circuit. What do we have to do? We have to reconfigure the FPGA. That is not so easy, or it's not good. The idea is to avoid that, but it's possible. So also in SRAM-based FPGAs, we need to protect both, but priority is to protect the bit configuration bits. Well, now I will present in the minutes that rest some Android thesis projects. I put 3. I have many other projects that are very interesting. That was thinking about this application, this problem, but of course it's an Android thesis. They are Android thesis, so we will see that we have many work to do in this kind of projects to increase the reliability or also to reduce the power consumption. My student Makasana, he finished his career the last year. The proposal of him was to use a LoRa system and for transmission of the Hobo information. What is Hobo? Hobo hues are not interconnected. These are equipment to measure a pluviometer. It measure the rain. So scientific people or the people in charge of the security put this kind of equipment in the mountain. So if you are constantly measuring the mountain, you can see if it's possible to have a white, as I said, or fruit. So this is an alert system. this part of the solar system, and also to understand the process of atmosphere in Andes. Always important to have a modeling, a mathematical model. So in order to have mathematical model, you need data. The problem is that these systems, it's not common to have interconnected communication, wireless communication. So people usually climb to the mountain once a week or once a month and check the information. And sometimes they don't have information because maybe a raid hit the equipment and destroy it, for example. So the condition of working of this is, as I shown in the beginning of the presentation, remote places. The proposal was to develop a data acquisition from this equipment, make a reliable transmission, and look for a low energy consumption. LoRa is a protocol, is a technology, low range, low power, low range, that allows to transmit information very, very far away, like 1 kilometer, 2 kilometers, 10 kilometers, depending on the conditions, and with a very small power consumption. And so this is optimal for the kind of application. We are working with LoRa in many projects. The proposal was to develop a router, some kind of routers. It was developed by that student, and also develop a gateway to implement this kind of network. LoRa is not designed for mesh networks, but since LoRa is open source, you can change some stuff of the protocol and connect these routes in a mesh way. He uses an algorithm applied to Warshaw in the gateway, so he calculates the best transmission path based on the weights in the network. The RSSI signal is like the intensity of the communication, the link communication. So, for example, if some router was with no energy and it's not working at the moment, the system will detect that it is a not valid path and reorganize the information. So the path. So it increased the reliability of the network. He implemented this system, I think 2,000 meters above level, 1,000. It's close to Lima. The problem with this implementation was that it was in the pandemic moment, and pandemic moment closed everything, and it was not possible to implement it in other places. But he implemented around Lima, the higher part of Lima. The developed mode is with a microprocessor STM32. This is a low power microprocessor. He used a lithium battery, and he worked properly. The strategy of energy was to put in sleep mode most of the time. All these parameters were configurable from the cloud. So the gateway received information and put to the cloud, and from the cloud you can monitoring this equipment, the sensors in whatever place. This is a time of sleep mode. They wake up, send a message, and sleep again. And the nodes and the router wake up in sequential time. So the estimated average current of the node was 2 milliamperes with a very small battery. It's expected to have an autonomous energy of 2 months. It's not so much, 2 months and a half, but of course we are considering a very small battery. If we increase the battery, we increase the autonomy energy, and also we can work on and reduce the energy of the system. One of the part always we will have a high energy will be in the communication. We use LoRa, but it's obviously more energy consumption than the node, than the microprocessor. Other work is the portable concentration acquisition system in rivers using voltammetry. We had two thesis projects. Lama is the first one, Perez, and they developed a system that able to measure the lead in the river. They can measure whatever or some kind of heavy metals, but we start with lead. And this is necessary because in this system, the idea is to measure continuously the contamination process on the river, for example, for mining activities. Whatever rate, but mining activities is one of the main source of heavy metals. He used also a microcontroller STM32. They developed a potentiostat. This system, what makes this system is to inject some current in the water and measure. This measurement, the concentration will depend on the pH, temperature and pH, but mainly the pH. So they correct the measure with a pH meter. And they validate the system. Sorry, this is in Spanish. I will translate. The supply voltage is 7.4 voltage, and they use a current of the 145 milliamperes. It's not so low, but that's what requires the system to inject current to the water. The precision was the resolution was 1 part per billion. That's very sensitive. It's very good range, and the error of the measurement it was 2 ppb. So we need to reduce the energy consumption, of course. With a small battery also, the autonomy is just for 6 hours. But this is maybe one of the most interesting projects because we don't have in the state of the art some kind of this equipment. Usually people goes to a portable place to make the measurements, but no automatic. This is automatic. The other ones are not automatic, and the other ones requires a specialist. This equipment, since it's automatic, the idea is to put in the river and start to measure and check continuously the contamination of the river. The last one presentation project, here is a BCI based on FPGA, BCI brain-computer interface. The brain-computer interface reads with electrodes the electricity of your brain and analyze the signals. The problem is that this analysis system is usually implemented in a CPU, in a laptop, for example, a computer. So think about implement this kind of technology in a portable system is not possible right now, or very, very difficult. So this project, in this project, we start to develop a platform completely analysis in FPGA, and application and communication, allocation, and motor recovery. And there are many possible future applications that they are still studying in the medical area. For example, to prevent some kind of sickness with this kind of equipment. So the proposal was to develop a platform based on FPGA. The first part of this system was acquisition of the data. One more time, this is in Spanish, sorry, because it was from the thesis presentation. It was the acquisition of the data. We used an OpenBCI site, and that is a well-known acquisition block. And the analysis of the signal is in the Arctic 7. The FPGA is from Xilinx. The second part was the processing of the data. After that, extract the characteristics, the features of the signal, and then they classify. In BCI, you have different ways to work. The first way, or one of the basic ways, is detecting an open eyes and closed eyes. There are other paradigms. There are many paradigms in BCI, but this work starts with the basic one, that is open eyes and closed eyes. The classification was based in LDA, the linear discriminant analysis, so it was not implemented on any more intelligent system. Some interesting work that was that we were not working with float pointing. We are working with 6-pointed, and the result was very good. This is part of the experiment. Implement or perform this experiment, this is a bit difficult because that electrodes can be contaminated by the electromagnetic signals in the Earth. So we performed these experiments, and the precision of the closed eye was 79% and open eyes 83%. That is in the standard levels. After this, I am not presenting this because of time, because after this work, another student, Cortés, implemented a classifier based on a more complex a deep learning system. And also he implemented in FPGA. Finally, we are now, we have many other applications, critical applications that can be or think about to work in Andes locations. So now we are starting to studying or performing or implementing our capacities of analysis of radiation or radiation effects. So I have a student, Minaya is his last name. He implemented simulate a fault injector platform. We are working with PGRTX7. It's not so new, but it's working. So we extract the information. We use the Acme system to extract where in the FPGA where we will inject the fault. We check the sensitive configuration bits. After that, we use the SEN, that is an IP core of the Xilinx. We inject in that address and we check the application. So the idea is to all the other, for example, system that I shown, implement now in FPGA and test different kind of fault tolerant systems. And also in this year, right now, in this ongoing projects, we are developing a setup for a terrestrial radiation effect. The idea is to put in Cusco, for example, in a high altitude place, and later the experiments running automatically and check remotely from Lima, for example, now Lima, to check the experiment. So the idea is to have like a laboratory, a natural fault injector, something like that, with natural neutrons. So this is what I have to present. I have, I think, on time. Thanks so much for your time. I'm ready to questions.
Hi, so we have some questions in the chat. Let's wait. But before, so I would like to ask you some questions about, for example, the first work that you have shown with the routers. What happened if a single router actually failed and it's not working properly, or I mean, can be totally out of the connection? Do you have a methodology to bypass this router? Is it possible?
Yes, the gateway is checking the signals of each router with RSSI. It's from that is the LoRa parameter. So LoRa parameter will show, for example, to the gateway that the router 1 is out, for example. If gateway detects that router 1 is out, the cost of the path increase. So you don't use that router, and the gateway will check or look for another route.
Mm-hmm. Okay.
And also, this system allows to know if the energy of the router is low. I mean, if you have a lower energy, your LoRa transmission will be lower too, and again we can see, this is almost ending the battery life. So can select other routes for example.
Yeah, I don't know the cost of these routers, but if it's not so expensive, you can also have a code spare that actually turns on if you need it or something like that. Yes, and then it's not using any battery while it's totally down.
Well, yeah, it depends on the cost of. It's not so cost. It's not so cost, but the cost also always depends on the money that people have. It's very high or not so high. But it's not costly, I mean, because it was developed with common components. All the router was developed by the student, not only the algorithm. So it's possible to let there the router, and if something is wrong, you can enter maybe.
And about the fault, for example, the fault injection in the FPGA and the work with the FPGA. So, for example, what do you think are the main challenges of using FPGAs in the Andes applications? Do you see the people looking for FPGAs, or they still think that's very costly in terms of power?
Yeah, one of the interesting development technology of FPGA that right now you can find new FPGAs, different factories. So you have very low cost FPGAs, not only Xilinx. You have very low cost, and you have very low power energy. No, like Xilinx, because Xilinx is think for huge process. But I think that this is interesting development process, because the idea is to put, for example, the system with some technique, some fault tolerance technique with a low cost and with a low energy too. So we're starting with Xilinx, because we have now Xilinx. We are buying other FPGAs. But the idea is to put all the logic, all the digital circuit in other FPGAs. Another point and other word that I didn't present, but we are working on analysis of image, for example, to analyze the caudal, the flow of the river. Because sometimes you don't have no water in the river, you don't find the river too. Also, and after some months, you will find a big river. So how we can detect that with image? Yeah, but the problem is that image is high power consumption. So now, for example, people use a laptop with a camera. The idea is to put all this stuff in a FPGA, because, for example, to transmit now all the video to a center is not allowed for that kind of places. The idea is to make all the computation of the image processing in the FPGA and put it in the mountain, for example. It just transmits a parameter. So the good part is that we don't have a huge bandwidth. We don't have bandwidth there. We will use less energy than a laptop. And of course, we will need to implement some kind of fault tolerance techniques in this kind of FPGAs. That these FPGAs maybe will be Xilinx, because it have more resources for that.
Yes, it's interesting. For example, for some of these remote applications, we can think a little bit similar as a nano satellite or something like that, because you have a short bandwidth also, because you don't want to be communicating all the time, because it spends a lot of, but you have solar panels and so on that can help you and so on. So it's the issue is a little bit different, sometimes depends about each application.
Yes.
Thank you very much, Jimmy. I don't see any other questions in the chat. If someone has still a question, can write. But from my part, yes, thank you very much for your talk. Excellent talk. It was very interesting to learn all these new experiments and work that you have been doing.
Thank you, Fernanda. And I expect that we can work with you and your
we can collaborate more, yes.
Of course, we have a lot of projects to do. Thank you, Fernanda.
Yes, thank you.
See you, everyone.
See you.
Many thanks to Professor Jimmy Tarrillo for his valuable presentation. Thanks, Professor Fernanda, for presenting the session. Today, that was the last talk. Now let's move to the poster session that begins at 16 p.m. Let's do a little break up to 16 p.m. to wait the poster section. Hello, everyone. This section will be present in Portuguese. Then, vamos shiftar aqui para o português. Tudo bem, pessoal? Eu vou convidar aqui para a sessão o professor Alan, da UFPEL. Então, que vai conduzir a sessão. Tudo bem, professor Alan?
Olá, Guilherme. Tudo bom? Tudo bom, pessoal? Ok, então, pessoal. Então, agora nós temos a primeira sessão de pôster da conferência, né? Então, essa primeira sessão, que começa agora, ela vai abordar os tópicos de Approximate Computing, Machine Learning Circuits, Logic Synthesis, System on Chips, and FPGA Designs. Então, como que vai funcionar? Os vídeos que vocês nos submeteram serão rodados, então, para a nossa audiência, né? E, eventualmente, ao longo dos vídeos, o pessoal vai formulando as suas perguntas, vai submetendo, então, pelo chat aqui da nossa transmissão ao vivo, né? E, ao final dessa sessão, então, os corresponding authors de cada trabalho estão convidados, então, para se juntar a gente aqui nesse estúdio, a fim de, então, responder essas perguntas. A gente solicita que o pessoal, então, entre naquele link que foi fornecido via e-mail com 10 minutos de antecedência, né? E, eventualmente, se a sala estiver lotada no momento que algum autor solicitar permissão para entrar, não se preocupe, no momento que um outro autor responde a pergunta, a gente, então, remove ele para que outros possam entrar e responder as suas perguntas, então.
Ok, então vamos iniciar ali as apresentações. Ok, pessoal, estamos com um problema aqui no vídeo. Vou ter que resolver aqui. Um minuto.
Olá, pessoal. Então, a gente está com um pequeno probleminha técnico, mas a gente está trabalhando para consertar isso. Então, logo, logo a gente vai começar apresentações. Enquanto isso, né, eu vou só lembrar para vocês, né, que nós temos mais amanhã e sexta-feira para o nosso evento, né? Nós temos mais uma sessão de posters amanhã à tarde. Nós temos mais palestras bastante interessantes durante o dia amanhã e na manhã de sexta-feira. Lembrando também a vocês que na sexta-feira à tarde nós vamos ter o workshop do Young Professionals, que eu recomendo fortemente a todos participarem, porque é algo bastante importante ter esse feedback de pessoas que já estiveram, já passaram às vezes por mestrado, doutorado, estão hoje na indústria. Esse feedback é bastante importante, né, para a gente ver um pouco o que a gente, às vezes, na academia acaba não desenvolvendo, algumas skills que a gente acaba não desenvolvendo na academia, né. Então, nos próximos minutos a gente vai começar. Só lembrando, né, que conforme a gente for apresentar, ao final da apresentação, nós vamos vamos convidando os corresponding authors, né, as pessoas que gravaram os vídeos, para que elas acessem a sala e respondam eventuais perguntas de vocês, né. A gente sugere que vocês façam essa interação, não precisam ter medo de fazer perguntas, tá? É legal para vocês praticarem essa situação onde vocês têm que fazer perguntas e responder perguntas, certo? Enquanto isso, eu vou deixar de novo a nossa marca. Acho que estamos quase pronto aqui.
Hello everyone, my name is Bruno. I'm from Federal University of Rio Grande do Sul, and I'm going to briefly present our work, which is entitled On the Constant Parameter Approximation for Boosting the Efficiency of Random Forest Inference Engines. So first of all, power dissipation is a major problem when considering machine learning applications running in embedded devices because they have battery constraints. For that reason, we can use simple machine learning models that are suitable for embedded devices, such as decision trees or random forests. So talking about the specific motivations of our work, random forest kernels, they're composed of comparators between features and constants. These are defined in the training stage. Paths that lead to decision nodes, and majority gates that merge the partial decisions of each tree. Some analysis we performed show that most of the power dissipation, like about 65% of a random forest kernel, is dissipated in the comparators, because there are many of them. Also, we found that the area of each comparator highly depends on the constant which is being compared with the feature. Based on these considerations, our goal is to approximate the constant parameters of the comparators based on the offline circuit characterization to reduce area and power and consequently the energy. So our proposal is to synthesize all possible comparators between a generic input and a specific constant, considering every possible constant value for a specific width. With that, we obtain a list of areas of all standalone comparators, and after that, we perform parameter adjustment of each comparator in the random forest that is going to be approximated. This approximation is performed according to a step value that indicates the maximum distance from the initial constant to search for one with a smaller area. So in this example, we have an initial comparator between a feature and the constant 361 in this image here. Considering a step of 2, we search in a pre-synthesized list of comparators for the one with the smallest area with a distance up to 2 of the initial constant. In this case, the best one is defined as 359. So this is the design flow of our work. The first step is the training stage, performed with scikit-learn, and it generates the random forest models and the constants of every comparator, and these are defined as the precise models in our work. Then the offline synthesis is performed, as mentioned in the previous slide. With that, we adjust the parameters of every comparator, and with the adjusted models, we insert them in our scikit-learn to RTL framework that automatically generates the very large descriptions of the random forests. Then the architectures are synthesized using cadence skewness at 50 MHz, considering 3 datasets. To obtain the results, we evaluate our proposal for several step values, as presented here in this slide. We compare a proposal with a technique, an approximate technique that applied don't care signals to the least significant bits of the features. And what we can see here in this chart is that our proposal allows for a more fine-grained trade-off. Our proposal is the one in orange here. And it has a more fine-grained trade-off when compared to DC, given that the amount of steps, the possible steps that we can apply in our proposal is only limited by the possible number of constants for a specific width. Our technique also outperforms the DC technique in terms of Pareto front and is better overall for the area accuracy chart here. Our proposal was also analyzed for different maximum tree depth values. In these charts, the points marked with a star are the precise configurations, and the baseline here is the precise configuration with a tree depth of 10. As we can see here, some configurations obtain significant energy savings when using our proposal for the same tree depth and for negligible accuracy drops, as we can see here. In the specific case, in the wireless dataset, we obtain significant energy savings of about 35% before the accuracy starts to drop more significantly. Also, our step technique, it presents superior energy accuracy trade-offs compared to a variation in tree depth with only the precise cases. So this is indicated here in 2 specific cases in the wearable dataset where the approximate configuration of step 10, for example, beats the precise configuration of step 9, meaning that our technique is better than only applying tree depth. So, concluding, our proposal presents a new Pareto front that is more optimal than the other approximation techniques such as DC, and it presents significant savings in area, power, energy, with negligible accuracy drops. And finally, there's significant room for improvement for these accelerators. And this is it. Thank you very much.
Olá a todos, meu nome é Vinícius Geraldo e hoje apresentarei para vocês meu trabalho intitulado como Experimental Evaluations of FPGA Countermeasures Against Side-Channel Attacks. Agora, uma breve sumário descrevendo como será dividida a apresentação desse trabalho, contendo introdução, separada em motivação, ataques por canais laterais e padrão de criptografia avançada, uma metodologia envolvida para o desenvolvimento do trabalho, resultados e discussões e uma breve conclusão. Com a grande evolução de tecnologias e o acelerado caminho em direção à indústria 4.0, a quantidade de dispositivos carregando informações privadas conectadas à internet tem tido um aumento exponencial. Para o sucesso desse tipo de desenvolvimento, é essencial que os dispositivos que participam desse sistema de comunicação sejam seguros, assim, mantendo a integridade e confiabilidade do dado. Através da figura desse slide, vemos a segurança envolvida nesse escopo, onde seria entre as trocas de informações do cartão magnético com as máquinas de cartões, onde se torna necessário uma segurança entre os dispositivos. Para isso, vemos a importância de implementações de algoritmos criptográficos para proporcionar uma comunicação segura entre os participantes. Contudo, diferentes métodos de ataques aos dispositivos criptográficos foram desenvolvidos para conseguir invadir sistemas e quebrá-los. Esses ataques, os quais têm como objetivo de conseguir esses dados, são chamados de ataques por canelas laterais, onde realizam estratégias através de propriedades físicas dos sistemas, como consumo de energia, emissão eletromagnética e tempo de processamento do dado, para adquirir as informações sigilosas sem deixar rastros na invasão. Dentre os ataques baseados no consumo de energia, podemos destacar dois, como análise diferencial de potência e análise da correlação de potência, de tal forma que esses métodos estabelecem relações estatísticas entre a potência consumida durante a execução do algoritmo e a chave secreta deste. O CPA se mostrou ultimamente mais eficiente no ponto de obter esse resultado com menos quantidade de traços. Para essa comunicação não ser afetada com esses ataques, algoritmos criptográficos como o AES é amplamente empregado nesses dispositivos. O AES é baseado em rodadas de 10, 12 e 14 etapas, cada uma delas passando por um bloco conhecido como S-Box, onde se realiza a encriptação da mensagem baseada na chave secreta. Como todo algoritmo criptográfico, o AES pode sofrer com ataques por canelas laterais, de tal forma que são implementadas estratégias para diminuir o vazamento de informações, conhecidas como contramedidas. Dessa forma, adotamos diferentes implementações de FPGA como metodologia. Neste trabalho, temos como objetivo a exploração do algoritmo AES voltado para FPGAs, avaliando diferentes técnicas de síntese de projeto em arquiteturas com e sem contramedidas, analisando assim o seu impacto a nível de segurança de sistemas para esse estilo de projeto. Foram desenvolvidas 3 versões do AES para serem feitas as explorações, tais quais são implementações baseadas em lookup table, implementação baseada em lógica combinacional e uma contramedida baseada na implementação de lógica de pré-carga em trilha dupla. Podemos observar como é feita essa lógica através da figura abaixo, onde vemos a adoção da técnica de pré-carga quando o circuito está na fase de carregamento e uma fase de validação quando seus sinais estão sendo transportados ao longo do circuito. Vale destacar que esse tipo de implementação utiliza portas lógicas da biblioteca de células. Para o desenvolvimento dos testes nas arquiteturas prototipadas, utilizamos a placa Chip Whisper apresentada nesse slide através do nosso setup de aquisição no sistema desejado. Assim, foram desenvolvidos testes com o propósito de avaliar a segurança das arquiteturas empregando diferentes modelos de vazamento para comparação. Dessa forma, utilizamos uma métrica para impor os resultados, onde empregamos a desviação parcial de entropia, tal qual utiliza o parâmetro de entropia de cada chave para realizar seu ranqueamento para a provável chave correta encriptada. Valores indicados com 0 mostram o sucesso do ataque. Apresentada toda a metodologia envolvida nesse trabalho e partindo para os resultados, avaliamos cada estratégia empregada para a síntese do FPGA, empregando ataques do tipo CPA através de diferentes modelos de vazamento. Notamos que para a estratégia de redução de área, apresentou resultados melhores para técnicas sem contramedidas, pois notamos que os estilos combinacional e LUT apenas quebrou com um modelo de vazamento. Porém, quando aplicamos a estratégia de otimização de consumo, notamos que os modelos de vazamento apresentam diferenças para a WDL, apresentando valores mais elevados para determinados ataques, mas ainda continuam sendo quebrados pelos mesmos modelos. Na estratégia de performance em atraso, apenas 2 implementações foram possíveis de realizar, das quais foram sem contramedidas, pois a WDL, quando aplicadas na ferramenta, não foi sintetizada por conta da área do FPGA. O melhor modelo de vazamento para os ataques ficou como sendo na última rodada da S-Box a ser quebrada. Como conclusão, notamos a eficiência dos ataques por canelas laterais em sistemas de FPGA, contendo algoritmos criptográficos sem contramedidas e com contramedidas. Vemos que o tipo de análise de vazamento para a execução do ataque é importante. As estratégias de síntese adotadas mostram impactos em relação à segurança. Como trabalhos futuros, serão realizados diferentes ataques para avaliação dos mesmos, desenvolvimento de novas contramedidas baseadas na literatura e analisar diferentes frequências de operação do algoritmo. Aqui estão minhas referências. Muito obrigado.
Olá a todos, meu nome é Gabriel Ames, eu já meu trabalho, que leva Approximate Logic Synthesis Combine Keep, Insertion and Remove. Esse trabalho foi desenvolvido junto com Walter Lau, os professores Paulo Bussi, Pierre Manuel Gallardon e Renato. Bom, o circuito aproximado é um circuito que não é logicamente equivalente à especificação, mas ele consegue otimizações em área, desempenho e consumo energético. A síntese lógica aproximada ela consiste em sintetizar de forma automática um circuito aproximado que satisfaça uma dada restrição de erro. Então, o problema que a gente aborda aqui é, para uma dada cobertura dos níveis e uma restrição, pode ser tanto no número de erros quanto na frequência de erros, gerar uma cobertura dos níveis aproximada que reduza o número de literais e que satisfaça a restrição de erro. Então, existem 2 formas principais de aproximar uma cobertura dos níveis. A primeira é complementando a saída do interno de 0 para 1. Quando isso é feito, é possível inserir novos cubos na solução que não era possível anteriormente, remover cubos que não são mais necessários e assim otimizar o número de iterais. Essa técnica é chamada de inserção de cubos. A outra forma é complementar as saídas internas de 1 para 0. Quando isso é feito, é possível remover diretamente cubos da solução, otimizando assim o número de iterais. Essa técnica é chamada de remoção de cubos. Em 2010, Xin e Gupta apresentaram alguns experimentos que sugeriam que a inserção de cubos levava a resultados melhores do que a remoção de cubos. E desde então, a maioria dos métodos de síntese lógica aproximada 2 níveis focaram na inserção de cubos. O mais recente deles é o do Sul, do ano passado, que ele apresenta uma técnica de busca heurística para resolver esse problema e que a gente vai considerar aqui como standard. A ideia principal dele é, por uma dada solução inicial, ele aproxima ela de forma iterativa. Então, a solução inicial aqui custa 0 com 0 erros, ele gera mais duas soluções, com erro 1 e com erro 2. Em seguida, ele aproxima a solução com erro 1, gerando mais duas, uma convertidora com erro 2 e uma convertidora com erro 3. Ou seja, a cada passo ele cria mais duas coberturas, com um erro a mais e com 2 erros a mais. E assim sucessivamente. Quando ele tem mais do que duas soluções com dado erro, ele utiliza só as duas melhores. Isso acontece para evitar que tenha um número muito grande de soluções intermediárias e que acabe impactando no tempo de execução. Então, por fim, a gente tem 4 soluções com o erro máximo. Aqui a gente representa um método que explora tanto a inserção de cubos quanto a remoção de cubos e que consegue suportar um número alto de erros durante a execução. Então, a principal motivação aqui é que quando tu permite que a aproximação seja feita, tanto complementando as saídas internas de 0 para 1 quanto de 1 para 0, consegue um resultado que é melhor do que quando utiliza só a inserção de cubos ou só a remoção de cubos individualmente. A ideia principal é a mesma do Sul, então a gente gera duas soluções para uma das opções inicial, utilizando a inserção de cubos, só que a gente também gera uma técnica de remoção de cubos que pode inserir todos os erros disponíveis. Então, por C0, a gente pode inserir mais 5 erros, então a gente usa a técnica de remoção de cubos com 5 erros. Em seguida, a gente passa por C1, gera soluções gerando a inserção de cubos, e depois, com a remoção de cubos, a gente insere 4 erros. E assim por diante. Por fim, a gente vai ter 14 soluções com erro 5, que antes eram só 4. Os algoritmos propostos aqui no implementado em C++ e estão disponíveis no GitHub. E os resultados experimentais foram feitos considerando os benchmarks do IEEE 93. Então, primeiro a gente compara com o Sul, onde o Sul limita o número de erros durante a aproximação em 16. Então, aqui a gente deve estar limitado a 16 erros. Então, a gente tem os circuitos originais, o número de iterais desses circuitos, qual o número de iterais após a aproximação do Sul, qual o número de iterais após a nossa aproximação, a redução de literais do nosso em relação ao original e a redução do nosso em relação ao Sul. Todos os valores em negrito são valores onde a gente tem um resultado melhor que o Sul, que é todos, com exceção do B12, onde nenhum dos dois métodos conseguiu aproximar. Em relação ao tempo de execução, a gente tem um tempo de execução melhor que o do Sul em todos os casos, e principalmente em circuitos maiores, a gente tem uma redução bastante significativa. Agora a gente considera, a gente deixa de lado esse número de erros de 16 e a gente define que uma frequência de erro, onde o número de erro é sempre proporcional ao tamanho do circuito. Então aqui a gente tem os circuitos utilizados, a frequência de erro e o número de erro proporcional. A gente vai ter então os literais originais, os literais após a nossa aproximação e a redução. Então, é possível notar agora que o B12, que antes não era aproximado, agora a gente consegue realizar aproximações nele. Isso acontece porque a gente pode inserir todo o erro possível na etapa de remoção de cubos. Então aqui quando a gente tem um número maior de erros disponíveis, a gente consegue realizar a aproximação. Interessante notar também que nesses 3 casos com 5% de erro, a gente conseguiu uma redução de mais de 93% no número de iterais. Em relação ao tempo de execução, a gente conseguiu manter todas as execuções abaixo de 5 minutos. Bom, esse foi o nosso trabalho, espero que tenham gostado. Muito obrigado.
Oi, eu sou o Guilherme Mansky e eu vou apresentar o trabalho A Fast Approximate Function Generation Methods to ATM Architecture. O avanço tecnológico tem proporcionado a produção de circuitos com uma maior densidade de transistores e que podem operar em uma maior frequência e com maior eficiência também. Porém, os circuitos têm se tornado mais suscetíveis a falhas, que pode ocorrer, por exemplo, por causa da radiação. Uma técnica utilizada para mascarar esses erros é o TMR, que consiste em criar dois módulos iguais ao original e ligar as saídas em um rotador majoritário. Essa técnica ela apresenta 100% de cobertura a falhas únicas que ocorram nos módulos. Ela é bem simples de ser criada, porém ela apresenta 200% de overhead de área, sem contar o rotador. Para reduzir esse aumento de área, é utilizado o ATMR, que utiliza computação aproximada para criar os módulos. Essa técnica ela também reduz a cobertura a falhas, então é necessário procurar o melhor trade-off entre overhead de área e cobertura de falhas. E ela é difícil de ser criada, pois normalmente é utilizado uma aproximação que cria um módulo menor, que protege as saídas que eram zero na original, e um módulo maior, que protege todas as saídas que eram 1 na original, fazendo com que o rotador, mas é necessário criar esses circuitos fazendo com que o rotador tenha a saída correta na ausência de falhas. Para criar as funções aproximadas, a gente analisou a correlação das variáveis de entrada com a saída. Nesse caso aqui, a função que a gente pegou é representada pelo hexa 78, e aí a gente viu quando a variável era 1 e a saída era 1, e viu qual variável tinha maior impacto, que no caso aqui é o A. Aí para criar a função maior, a gente faz o A ou o S. E aí criou a função só com 3 literais, a original tinha 7. De maneira análoga, a gente faz para quando a variável é 0 e a saída é 0. Aqui no caso o A também foi o que aconteceu mais vezes isso. E agora, para criar a função menor, a gente faz o A AND S, que também reduziu agora para 4 literais do 7. E cada uma das funções aproximadas, ela deixou um interno descoberto. Nesse caso aqui foi o último, e nesse caso aqui foi o quarto. Bom, na nossa implementação, ela usa como entrada um PLA. Aí a gente usa o PLA para transformar ele, para criar um valor em hexa que representa a saída da função. E quando existe mais de uma saída no PLA, são criado um hexa para cada saída. Aí depois cada saída é aproximada separadamente. Aí depois transforma as funções aproximadas também são representadas em hexa e depois são transformadas em PLA novamente. Aí a gente junta os PLAs de cada aproximação para juntar as saídas tudo no mesmo PLA. Aí é utilizado o expresso para simplificar o circuito. Aí a gente faz um mapeamento tecnológico utilizando a ferramenta ABC, que já nos dá a área do circuito de cada módulo. E a gente cria o Verilog do ATMR para utilizar uma ferramenta de injeção de falhas e ter o error rate do circuito. A gente utilizou alguns circuitos da biblioteca LXSynth 93 e o overhead de área que a gente conseguiu está variando entre 114,29% até 135,32%. E o error rate foi reduzido em mais ou menos pela metade. Essa comparação aqui é quantas vezes maior o error rate do original em comparação ao error rate do ATMR. A gente conseguiu o error rate e o overhead de área são similares aos seus dados apresentados no trabalho 1 do Yuri. Porém, o tempo que foi utilizado para aproximar esses circuitos foi reduzido de horas para os maiores circuitos para menos de 1 segundo com o nosso método. Ele também é bem escalável já por causa desse tempo, mas é necessário conseguir um error rate menor. E a gente também precisa de um método que a gente consiga colocar um threshold para ter um melhor trade-off entre o overhead de área e o error rate. Muito obrigado.
Oi, meu nome é Luiz Antônio, eu sou da Universidade Federal de Santa Catarina, estudante de graduação, e hoje eu vou apresentar um trabalho desenvolvido sobre diferentes implementações do modelo neural Perceptron, analisando a área e potência para análise do custo computacional. O codificador de vídeo AV1 apresenta melhores resultados de compressão comparado à maioria de seus competidores, porém isso é o custo de até 3.000 vezes mais complexidade. Devido ao uso de redes neurais no algoritmo do codificador de vídeo AV1, soluções em hardware podem ser uma solução para melhor eficiência da codificação. Um exemplo de rede neural pode ser visto nessa imagem ilustrativa, onde podemos ver cada bolinha seria um neurônio. O modelo de neurônio nesse trabalho implementado é o Perceptron. E as redes neurais elas se diferem pelo seu tamanho, número de neurônios, modo e número de conexões entre cada neurônio e os tipos de implementação da arquitetura. O objetivo desse trabalho é implementar diferentes arquiteturas de neurônio para comparar o consumo de potência e área estimada. E seu funcionamento se baseia em multiplicar cada entrada pelo seu respectivo peso, somar ainda ao bias, ou viés, e toda essa soma aplicar uma função de ativação. Nesse caso, no trabalho, a função de ativação escolhida é a função sigmoide. O objetivo desse trabalho é implementar diferentes arquiteturas de Perceptron numa placa FPGA, variando o número de entradas, pesos e a representação de bits. Nessa imagem, a gente pode ver a lógica de funcionamento que foi descrita em linguagem de programação VHDL. Podemos ver aqui que seriam o número de entradas e pesos variável, a soma ponderada seria salvo no registrador, onde na implementação seria escolhido entre pegar o valor da função de ativação respectivo ao valor de entrada, ou, dependendo para certos valores limite, pegar o próprio valor do resultado da somatória e aplicar na saída. Resultados. Aqui nessa tabela, podemos ver os 3 tipos de bits escolhidos para a representação de cada Perceptron, o número de entradas e pesos variável e o número de elementos lógicos, assim como a potência para cada modelo de arquitetura. Conclusões. Para o tipo de implementação utilizada, a dissipação de potência mostrou um crescimento linear conforme o aumento de número de pesos e entradas. A área total estimada, com o número total de elementos lógicos na placa FPGA, demonstrou um crescimento agressivo com o aumento de número de entradas e pesos. Isso se deve ao tipo de implementação, onde foi utilizada um multiplicador e um somador para cada entrada e peso. Em próximas implementações, serão utilizados modelos recursivos. Testes práticos de implementação, ligando os vários neurônios para a implementação da rede neural completa, precisam ser feitos ainda para testar a melhor viabilidade de cada modelo. Obrigado.
Olá, meu nome é Leonardo, sou graduando em Engenharia de Computação pela URGS e hoje eu vou falar um pouco mais sobre o impacto de designs paralelos em uma arquitetura de virtualização de switches. Até bem pouco tempo atrás, a gente só tinha dispositivos fixos muito engessados. Isso é, uma vez que a gente definia o comportamento deles, eles sempre iam fazer a mesma coisa. Com o desenvolvimento dos planos de dados programáveis, surgiu a possibilidade de a gente colocar vários switches em um único dispositivo de hardware, e damos a isso o nome de virtualização. O nosso projeto, o PVS, Programmable Virtual Switches, ele busca aplicar esse conceito para a área de redes, com a virtualização de switches programáveis. Aqui a gente pode ver a nossa arquitetura, à esquerda as portas de entrada, com uma interface de entrada para todos os virtual switches, que são os VS, uma interface de saída, uma interface de controle e depois todas as portas de saída. A nossa arquitetura, desde o início, ela já buscava paralelizar os switches internamente. Na figura são os VS em azul e verde. Então, agora a nossa proposta para esse trabalho é paralelizar cada vez mais essa arquitetura. Nesse primeiro momento, vamos começar reduzindo um dos principais gargalos dela, que é a interface de entrada. Nessa figura a gente chama de Input VS Interface, ou IVSI. O objetivo do trabalho é avaliar os impactos dessas mudanças e buscar identificar a melhor arquitetura para diferentes quantidades de switches. Aqui à esquerda a gente pode ver a nossa arquitetura original, com uma interface de entrada para todos os switches, e à direita a gente tem a nova arquitetura, uma interface de entrada para cada um dos virtual switches. Agora, falar mais um pouquinho de detalhes de implementação. Para fazer essa implementação, a gente usou várias tecnologias, entre elas o Verilog, Python e Vivado. Pegando as modificações que a gente fez nos códigos em Verilog e ajustando com algumas cargas de teste em Python, a gente pode usar o Vivado para validar essas modificações que a gente fez, mantinha a arquitetura funcionando conforme ela já vinha antes dessas mudanças. Para comparar nossas arquiteturas e ver a diferença da performance com e sem paralelismo, a gente gerou o bitstream de cada uma, e uma por vez a gente implementou elas na nossa placa SAM, e pegou uma quantidade muito grande de dados e ficou injetando na placa por um período de tempo para validar o máximo throughput que a nossa arquitetura conseguiria atingir. E fez isso tanto para a versão com paralelismo e tanto para sem, usando 2 virtual switches. Agora vamos aos resultados. À esquerda a gente pode ver o gráfico de throughput por tempo das nossas duas arquiteturas, sendo a linha vermelha representando a arquitetura paralelizada e a linha azul a arquitetura original. Como resultado, tivemos cerca de 30 megabits por segundo de ganho paralelizando somente 2 interfaces de entrada para 2 switches. Isso pode parecer pouco, mas isso se justifica porque é apenas a primeira fase de um grande projeto, que serviu mais para a gente validar a hipótese de que o paralelismo ia melhorar o desempenho da nossa arquitetura. Agora, no gráfico da direita, a gente pode ver a ocupação na placa, comparando a versão com uma interface de entrada e a com 2. A gente pode ver que a ocupação na placa chegou perto de dobrar, mas ainda assim não foi muito expressiva. Apesar disso, a gente percebeu que a gente precisa otimizar o uso de BRAM a partir das interfaces de entrada, já que a BRAM é um recurso muito escasso nas FPGAs. Nossas principais conclusões e ideias de trabalhos futuros. A gente percebeu que a paralelização na interface de entrada pode incrementar o throughput sem ocupar tanta área da placa, e já que a gente obteve 30 megabits por segundo como sendo só o primeiro passo, a gente acredita que quanto mais paralela for a nossa arquitetura, mais ganho a gente vai conseguir. Por enquanto, a gente tem apenas esses 30 megabits por segundo de aumento. Porém, a gente espera que adicionando mais estruturas em paralelo, podemos ter um aumento similar de cerca de 30 megabits por segundo para cada interface de entrada que a gente adicionar, e depois também para cada interface de saída, que a gente também pretende paralelizar no futuro. E, além disso, os próximos trabalhos são os que vão justificar essas hipóteses que eu levantei anteriormente. Muito obrigado.
Hello, my name is Ron Dick. I'm an undergraduate research assistant and student at Federal University of Rio Grande do Sul. And in this video, I'm going to present an overview of the paper Quality and Complexity Assessment of Learning-Based Image Compression Solutions. As reported by the Cisco Global IP Traffic Forecast, the demand for multimedia services has experienced a significant growth in the latest years, making image and video content account for most of the web's data traffic. Therefore, image compression solutions play an important role in supporting efficient multimedia transmission and storage. To address this issue, several models with different characteristics have been developed in the past, combining transform and operations with hand-tuned parameters. In the past few years, a new paradigm has been proposed, learning-based image compression. Opposed to the pre-existing models referred here as classical, learning-based models apply convolutional neural networks to image compression. The majority of parameters is no longer hand-tuned, but learned in a training process that aims to minimize a rate distortion trade-off. This new approach is possible due to abundant training data, hardware computational advances, and new CNN architectures. Neural image compression has different architectural approaches. Nevertheless, most learning-based models can be abstracted to a standard scheme with E, P, and D representing neural networks. In this autoencoder-based approach, the encoder E transforms the input image X into the latent representation Y. The latent Y then follows two paths, being quantized by Q into the discrete representation and fed into the entropy model P. Since Y is now made from discrete values and P has produced the entropy parameters, Y's entropy encoded into Y hat, reaching the most compressed representation for storage and transmission. For decoding, a mirrored process is performed by entropy decoding Y hat and a subsequent reconstruction achieved by the decoder D, generating X prime. The process just described implies a visual quality penalty between the original and reconstructed images. Different visual quality metrics can be used to quantify this penalty. Also, a complexity penalty inherited from the model's architecture is expressed in compression and reconstruction execution times. When designing an image compression model, a trade-off is established between the overall visual quality and overall execution time performances. Therefore, studying this trade-off is of great importance for developing time-efficient codecs. Therefore, this paper proposes to analyze multiple classical and learning-based models, addressing the trade-off between visual quality and model complexity. Also, easy access, low-cost hardware is utilized to run experiments on both GPU and CPU. The experimental methodology applied is the following. The codec dataset composed of 24,768 by 512 8-bit RGB images is utilized. Therefore, the extracted metrics are averaged between different images. The classical models addressed are JPEG 2000 and BPG, an image codec based on AGVC Intra standard. Also, 8 pre-trained learning-based models available at the TensorFlow compression are considered. When addressing complexity, model size, compression, and reconstruction times for both GPU and CPU are considered. For visual quality measurement, PSNR and MS-SSIM are computed in the luminance channel, and the deep visual representation metric, LPIPS, across RGB. When addressing LPIPS, Hi-Fi-C outperforms all other models by a great margin, being the model to have the best ambient performance in a single visual quality metric. In the remaining models, BPG and VA have the best performance for low and medium BPPs, but are outperformed by JPEG 2000 in higher bits per pixel. Since image compression model performance varies according to different metrics and bit rates, analyzing the mean performance across a common bitrate interval with cubic interpolation helps us compare model performance. For this comparison, Hi-Fi-C was not considered due to its limited bits per pixel operation range. And this plot shows that BPG presents the best overall PSNR performance and the second best overall MS-SSIM performance. VA min has the best overall MS-SSIM performance and second best PSNR values. BLR and BGDN architectures present the lowest PSNR values, but overall competitive performance in MS-SSIM. Among classical models, JPEG 2000 is outperformed by a significant margin by BPG. This plot represents compression and decompression time values displayed in a relative axis, demonstrating that learning-based compression and decompression time values can increase over 10 and 14 times depending on the chosen architecture. After analyzing the experimental results, we conclude that learning-based solutions are promising methods with great potential for evolution in the next years. On the downside, a considerable complexity penalty is still present when comparing learning-based models to classical ones. Accelerators, parallelism, and low-complexity architectures are possible paths to reduce execution times. I reached the end of the presentation. Thanks for watching.
Olá, eu sou o João Vitor. Eu sou um aluno do curso de Sistemas para a Internet do IFSU Campus Charqueadas.
E eu sou Gustavo Luiz Grefo, aluno do curso de Engenharia de Controle e Automação do IFSU Campus Charqueadas. E este trabalho se trata do uso de FPGAs para simular algoritmos quânticos e adicionar a Qiskit o suporte à execução em FPGA. E está sob orientação do Caleb Conceição, coordenador do curso de Sistemas para a Internet do Campus de Charqueadas. Por que computação quântica? Atualmente, gigantes da tecnologia como Google, Intel, Microsoft e IBM vêm investindo pesado no desenvolvimento de computadores quânticos, visando atingir a supremacia quântica, termo este que representa o potencial dos computadores quânticos de resolver problemas que computadores clássicos não resolveriam em tempo razoável. Apesar dos grandes investimentos, fenômenos como decoerência quântica e a dificuldade de emaranhar grandes conjuntos de qubits se colocam como obstáculos a serem superados para que a supremacia quântica seja atingida. Mesmo assim, experimentos demonstram que mesmo um número reduzido de qubits em condições não ideais já são suficientes para que algumas aplicações possam ser realizadas com uma eficiência muito maior do que as soluções clássicas equivalentes. Devido a isto, pesquisadores do mundo todo vêm investindo em hardware clássico para simular sistemas quânticos, com o objetivo de fornecer um ambiente mais acessível para a criação e aprimoramento de algoritmos quânticos. O problema é que a natureza paralela e exponencial da computação quântica torna impossível uma simulação eficiente no tempo utilizando máquinas sequenciais clássicas. Para lidar com este problema, a literatura está cheia de trabalhos que utilizam de arquiteturas paralelas como GPU e FPGA para transferir a complexidade do domínio do tempo para o domínio do espaço.
É neste contexto que surge o nosso projeto, com o objetivo de implementar em FPGA uma solução arquitetural de hardware a ser integrada com a API Open Source Qiskit para a simulação de algoritmos quânticos remotamente em nosso servidor web. A API Qiskit possibilita que circuitos quânticos sejam executados em simuladores e em dispositivos quânticos reais. A API possui um ecossistema com módulos responsáveis pela criação de circuitos, redução de ruídos, simulação e aplicação da computação quântica em problemas da vida real. A execução dos circuitos quânticos pode ser feita em simuladores utilizando CPU e GPU. E este projeto tem como objetivo modificar o módulo de simulação da API para suportar a execução dos circuitos quânticos em chips FPGA, disponibilizados remotamente em nosso servidor. Em um primeiro momento, será utilizado um servidor web disponível em nosso instituto e, posteriormente, escalando para uma solução em nuvem da AWS. Em Qiskit, AIR é o componente responsável pela execução dos circuitos. O componente faz a comunicação com os provedores e dispositivos disponíveis para execução. O primeiro trecho de código do slide demonstra a implementação de um circuito quântico de 2 qubits, onde é aplicada a porta Hadamard no qubit 0 e feita a medição dos estados do circuito. O segundo trecho de código demonstra a execução do circuito em um simulador local utilizando o CPU. E o terceiro trecho de código demonstra a execução do mesmo circuito em um computador quântico real fornecido pelo IBM-Q. O componente AIR possui providers e backends. Backend é o dispositivo que vai executar o circuito e provider é o responsável por disponibilizar os backends.
As vantagens de se trabalhar com FPGA derivam de sua natureza programável e paralela. As FPGAs são ótimas em atividades que necessitam de paralelismo, podendo ser criado múltiplas unidades de processamento dentro do chip, para que diferentes dados sejam processados ao mesmo tempo, transferindo assim a complexidade do domínio do tempo para o domínio do espaço. Com isto, é possível realizar as somas e multiplicações dos vetores e matrizes necessárias para a realização da computação quântica de maneira paralela, acelerando assim a simulação dos algoritmos. Serão feitos estudos sobre modelos já existentes de simuladores, com a intenção de adaptar os algoritmos e as estruturas de dados para que seja possível realizar paralelização em FPGA. Os modelos serão criados utilizando a linguagem de descrição de hardware Verilog e serão estudados aspectos como complexidade, eficiência e escalabilidade, visando a escolha do modelo que mais se adequa a uma futura implementação em ASIC. Além da implementação do modelo, também é necessário garantir que não haja gargalo de comunicação entre o web server e a placa FPGA. Para isso, conexões como a serial RS-232, USB e PCI Express serão usadas e avaliadas. Este projeto ainda se encontra em fase inicial, porém demonstra grande potencial para o uso do paralelismo e de FPGAs para acelerar a emulação de algoritmos quânticos e integrar a solução a uma API de código aberto. O desafio, no entanto, está em encontrar um modelo escalável que permita a flexibilização dos números de qubits simulados, a precisão de representação numérica, entre outros parâmetros. A API Qiskit vai simplificar muito o uso de nossa solução e será essencial para validar as soluções testadas, pois podemos usar os frameworks já disponíveis para acesso público pela IBM como referência.
Olá, eu sou o Pedro, estudante de Ciência da Computação na UFSC e vou apresentar este trabalho com exploração de comparadores aproximados em aplicações de árvores de decisão. Árvores de decisão, ou DTs, são modelos de machine learning bastante propício para uso em aplicações que requerem baixo consumo energético. Elas podem ser empregadas em diversas soluções mais simples, que não requerem redes neurais, enquanto possuem o benefício de serem menos custosas em energia e mais simples de compreender e implementar. Atualmente, o projeto de sistemas de machine learning de baixo consumo foca principalmente em melhorar a eficiência empregando de redes neurais, empregando técnicas em software ou hardware dedicado. Contudo, ainda há muito espaço para avaliar a redução de consumo energético em aplicações de DTs, especialmente no que diz respeito à utilização de computação aproximada em blocos aritméticos. Em DTs, comparadores são utilizados em todos os nodos de teste de atributo, sendo blocos críticos para aproximação. Houve pouca investigação na aproximação de circuitos comparadores, em particular em nível de circuito e portas lógicas e em ambientes de machine learning. Neste contexto, este trabalho busca propor e avaliar um conjunto de comparadores aproximados e estudar seu comportamento em aplicações de classificação com árvores de decisão. Foram utilizados dois métodos no projeto de comparadores aproximados, focados na operação de menor ou igual, que é a operação utilizada no classificador C5.0, que serviu de estudo de caso. Primeiramente, desenvolvemos comparadores dedicados, reduzindo um circuito comparador tradicional para que ele realize somente a operação de menor ou igual, e removemos depois portas lógicas ou utilizamos buffers para aplicar a aproximação em 25% ou 50% dos bits de entrada. Neste experimento, nós consideramos somente 4 bits em cada entrada. A segunda abordagem é utilizar comparadores baseados em full adders. No comparador apresentado, o carry-out do full adder no bit mais significativo é o resultado da operação A menor ou igual a B. Neste método, a aproximação é obtida substituindo as células de full adder por versões aproximadas extraídas da literatura. Incluímos também os dois full adders exatos que inspiraram os desafios aproximados para efeito de comparação. O experimento consistiu de duas partes. Iniciamos pela caracterização elétrica e análise de erro dos comparadores. Os circuitos foram descritos em FinFET de 7 nanômetros e simulados no Synopsys HSpice. Avaliamos então a dissipação média de potência, o atraso crítico, o PDP e as métricas de erro, distância de erro e taxa de erro. Na segunda parte do experimento, o classificador C5.0 foi empregado como estudo de caso. Os comparadores foram emulados em funções C, que substituíram as operações de menor ou igual na classificação de atributos categóricos do código-fonte do C5.0. 5 datasets foram utilizados para a construção de TTs e rodamos cada classificador aproximado, avaliando a taxa de erro em dados de treino e de teste. Quanto à análise de erro dos comparadores, vemos que as arquiteturas com FAs AXA2 e AXA3 não apresentam nenhum erro em relação à versão exata. Os comparadores com somente um bit de aproximação, a XDC1 e 2, apresentam as melhores taxas de erro entre os demais comparadores, enquanto os demais comparadores dedicados apresentam altas taxas de erro de mais de 30%. Contudo, considerando os resultados da caracterização elétrica, nós vemos que os resultados do AXA2 e 3 tiveram o pior PDP, apesar dos bons resultados na distância de erro. O AXDC2, em particular, teve os melhores resultados na relação entre PDP e ED. Por fim, o AM2 obteve os melhores resultados elétricos apesar das altas distâncias de erro. Analisando a média dos ganhos obtidos em cada comparador para dados de treino e teste, vemos que as arquiteturas AXDC2, SMA e AMA2 não apresentaram mudança em relação ao classificador exato. Notamos que o AXDC1 e a AMA2 obtiveram uma pequena melhora nos dados de teste, enquanto os AXDCs 3 a 6 tiveram um desempenho significativamente pior do que o classificador exato. O AXA2 e o AXA3 não sofreram alterações em sua acurácia, uma vez que os comparadores em que eles foram utilizados não produziram erro. Em detalhe, o aumento da taxa de erro do modelo usando os classificadores aproximados foi variado. Em certas versões, a utilização da aproximação resultou em melhora da acurácia em dados de teste em relação ao comparador exato. Notavelmente, é o caso do AXDC3 e AXDC5, que apresentaram melhora de até 32% no dataset de tic-tac-toe. O AXDC2 se confirmou como uma ótima opção, sem piora na acurácia do modelo e bons resultados elétricos, enquanto o AMA2 obteve bom desempenho em muitos datasets, com a contrapartida de maiores taxas de erro em certos dados de treino. Em conclusão, houve melhora das características elétricas da maior parte dos comparadores propostos. Os melhores resultados foram encontrados no AMA2 e no AXDC2, sendo que no C5.0 a maior parte dos comparadores também obteve desempenho próximo à versão exata. Algumas arquiteturas até apresentaram melhora na acurácia para alguns dados de teste, possivelmente reduzindo o impacto do overfitting. O projeto seguirá com a avaliação dos comparadores em datasets mistos e contínuos. Obrigado pela atenção.
Hola, mi nombre es Laura García Luciano y soy estudiante de la Universidad Autónoma de Zacatecas y el nombre de mi póster es Interconnection System for System on Chip. El objetivo de este trabajo es identificar los elementos de interconexión en los últimos años que se han utilizado para conectar ahí cores. Sabemos que ya ahorita los transistores están en el orden de los billones en los circuitos integrados. Esos circuitos integrados que están en un chip, pues es lo que conocemos como un sistema en chip. Esos sistemas en chip están conformados ya sea por elementos de procesamiento, de memoria, de entrada o salida, o cores que tienen distintas tareas a hacer, así también como el elemento de interconexión, que es muy importante. Se hizo un estudio del estado del arte para identificar esas interconexiones en los últimos años y se encontró que las necesidades de los sistemas digitales van en incremento y como requieren más de un core, pues necesitan saberlo conectar para que no, para que tenga la misma eficiencia y no disminuya al hacer esa conexión. Así como también una de las ventajas de hacer estas conexiones es que se disminuye el tiempo de desarrollo. Se disminuye el tiempo de desarrollo y también se evita modificar los cores a nivel de hardware. Entonces, esa es una de las cosas que se encontraron ahí. Los sistemas chip han crecido en tamaño y en complejidad y por lo tanto también la comunicación se hace compleja. La parte que interconecta a todos los elementos pues también representa una parte considerable del consumo de energía y entonces a la hora de diseñar estos circuitos, estas interconexiones, pues lo hace un verdadero reto. Estos fueron los 3 elementos que nos encontramos. Uno es el punto a punto, que tiene una conexión fija y por lo tanto, pues por esta naturaleza no es escalable. Está libre de arbitraje, pero también la desventaja es que tiene una topología irregular y que el grado del nodo no es constante. El que es más usado, comúnmente más usado, es el bus, que los elementos están unidos mediante un solo medio. Y este bus, pues tiene una topología modular simple, no es escalable, trabaja bien hasta 8 elementos, eso lo podemos ver en la referencia número 2, solamente trabaja hasta 8 elementos bien, no tiene capacidad de explotar el paralelismo, a diferencia de la red en chip, que depende también de la topología que esté implementando. Este sí es escalable. Y una de sus desventajas es que si el diseño se torna complejo, pues entonces la administración de todos estos miles de elementos, pues también, de igual manera. Los puntos que hacen o que influyen en el rendimiento, ya sea de usar el enfoque bus o el enfoque NOC, bueno, pues es que el bus escala bien en términos de área, pero sufre en términos de energía y rendimiento, mientras que en el ancho de banda, bueno, el ancho de banda se distribuye entre todos los elementos del bus. En cambio, la NOC, bueno, pues tenemos que cuidar, como depende de la topología, pues tenemos que cuidar el diámetro, el ancho de la bisección y también el grado, así como los tamaños de los cables y el área y que las estructuras sean regulares. También tenemos que saber identificar los cores que vamos a conectar en nuestra red, porque si identificamos, no sé, que sea un elemento de procesamiento, podemos ubicarlo estratégicamente en algún nodo de nuestra red para tener cierto resultado. También esta desventaja que tiene de la red en chip, bueno, también se puede solucionar con reconfigurabilidad. Por ejemplo, aquí, para mejorar la latencia en una network on chip, pues vamos a reconfigurar en topología y eso la va a mejorar porque es posible que tome un camino más corto y entonces el tiempo que se tarde la información de un nodo fuente a un nodo destino, pues va a ser menor. Las conclusiones parciales, porque esta investigación aún sigue, es que la modularidad de una NOC pues ofrece un gran potencial porque te permite reusar elementos. El enfoque que se use también es que depende de la aplicación. Aquí pongo un ejemplo de la referencia 5, donde se utiliza un bus para hacer un control de arbitraje. Y también otro de los detalles de que nosotros podemos utilizar la reconfigurabilidad para poder mejorar nuestra red NOC, porque podemos actualizar tablas de ruteo o, como lo mencioné antes, pues hacer una reconfiguración de topología. Muchas gracias. Esto fue todo.
Então, olá a todos.
Olá, pessoal.
Deixa eu pausar a apresentação. Ok. Ok.
Eu acho, Leandro, que a gente pode prosseguir, então, com a apresentação do chair da sessão, professor Jorge Castro-Godínez. I suppose, Jorge, that Portuguese won't be a problem for you, right?
Eu não tenho problema.
Ok, tudo certo, então.
Ótimo.
Então, pessoal... Opa, desculpa, Alan.
Isso, então, o professor Jorge, como chair da sessão, ele pode, então, assumir o controle da sessão, fazer aqui nós temos algumas perguntas da audiência, né? Então, eventualmente, professor, muito obrigado por se dispor a participar como chair dessa sessão de pôster. Então, pode ficar com a posse da palavra, ok? A gente vai ficar no backstage para lhe ajudar, então, com qualquer outra coisa que seja necessária.
Então, obrigado por la oportunidad de participar también acá con la sesión de posters, ¿ok? Entonces, quizás, sí, esperamos poder ver sus preguntas en el chat, particularmente para el primer autor.
Podemos colocar aqui, acho que o primeiro autor já está aqui no chat. Vamos pela ordem de apresentação, acho que fica mais fácil, né?
Isso.
Aí, então, a gente faz isso, e daí eu já vi que tem algumas pessoas que estão querendo entrar e a sala está cheia. Então, a gente só espera a gente vai respondendo, e conforme o pessoal for respondendo, já vai saindo. Então, olá, Bruno, tudo bem?
Olá, tudo bem? Oi, pessoal.
Então, pessoal, o Bruno apresentou o trabalho on the Constant Parameter Approximation for Boosting Efficiency of Random Forest Inference Engines. Então, se alguém tiver alguma pergunta, pode colocar uma pergunta aí no chat e a gente vai passando para ele. Enquanto o pessoal perde um pouco do medo de perguntar, eu tenho uma pergunta para você. Eu vi que o teu trabalho é bem interessante, tá? Eu já trabalhei um pouquinho com machine learning, então eu acho esses trabalhos de machine learning bem interessantes. Aqui eu vi que tu fez a síntese para a ZIC. Tu já pensou em fazer essa síntese para FPGA, alguma coisa assim?
Então, nós tínhamos alguns planos, eu já conversei com alguns dos coautores ali do trabalho, em fazer um trabalho ou algumas análises focando na síntese para FPGA, porque como a gente não sabe exatamente como isso ia se comportar com todos os comparadores com constantes explícitas mapeados com LUT, como que isso ia ser, como que ia ser as relações entre os comparadores, se o comparador com 60 ia ser melhor que com 59, por exemplo, alguma coisa do tipo, se essa relação ela ia ser diferente do que fazendo com a ZIC e dessa forma ia gerar resultados de eficiência e de redução diferentes com os diferentes parâmetros de step que eu utilizei ali no trabalho. Então, é um plano a gente fazer isso com a ZIC, sim, porque é um paradigma diferente. Ele vai mapear com as LUTs ali, então os comparadores com constantes vão gerar sínteses diferentes.
E qual seria a vantagem? Assim, eu vejo que vocês já estão no caminho, e na tua visão, qual que tu vê como vantagem utilizar um FPGA para esse tipo de síntese?
No quesito de reprogramabilidade, principalmente, a gente tem uns trabalhos na fila aí em relação a fazer comparadores que não estejam totalmente abertos no pipeline dele ali. E ao invés de ter todos os comparadores disponíveis, tipo uma árvore de depth ter 1000 e alguma coisa de comparadores disponíveis, a gente fazer um módulo, esse módulo aqui tem só 5 comparadores, tem só 7 comparadores. E aí isso está no esquema de pipeline, alguma coisa do tipo, rodando em mais ciclos com comparadores genéricos e não comparadores com constantes explícitas. E isso é um trabalho que a gente está para fazer ainda, está planejando, a gente só tem que ajustar alguns esquemas de como fazer para endereçar a busca desses dados na memória de forma eficiente, com prefetch, alguma coisa do tipo. Então, isso é um trabalho que ainda está... O uso da reprogramabilidade para o ASIC, fazendo um módulo genérico, ou a reprogramabilidade usando FPGA também para... O fato de eu poder reprogramar o mesmo módulo com constantes explícitas para o FPGA daí.
Excelente, excelente. O senhor Jorge tem alguma pergunta para o Bruno, já que o pessoal está um pouco tímido no chat?
Hola Bruno, obrigado
Hola,
por tu trabajo. En el slide 7 presentabas todo tu framework para la generación de los circuitos. Tal vez quisieras saber si puedes comentar un poco cómo haces la generación del modelo que ya obtenés a alto nivel para generar la parte de Verilog. Esa parte tal vez no fue clara y si pudieras comentar.
Essa parte é uma parte mais... Ela foi detalhada no artigo que a gente foi submetido já, que é uma parte de... a gente fez um framework que, a partir da estrutura de Decision Tree Classifiers e Random Forest Classifiers do Scikit-learn, ela gera uma arquitetura em hardware que roda em um ciclo, porque a gente está focando em aplicações que não requerem uma frequência muito alta, nesse caso. Então, a gente consegue fazer com que tudo caiba e rode numa frequência não muito alta assim. E essa geração ela é feita basicamente pegando a árvore e percorrendo recursivamente ela, instanciando todos os comparadores que tem na estrutura, que são utilizados na estrutura ou de Random Forest ou de Decision Tree Classifier, e fazendo cadeias de ANDs e ORs para todos os caminhos das folhas. Então, a gente, é um esquema um pouco bem detalhado, eu tenho essa implementação disponível no GitHub, inclusive, que a gente utiliza esses esquemas de AND e OR chains para todas as decisões, ou para todas as decisões de cada árvore de uma Random Forest, ou para uma só árvore da Decision Tree Classifier, e junta elas com Majority Gates, no caso. E basicamente, de forma um pouco básica, é isso. E aí, junto com tudo isso, a gente faz parsers para pegar essas junções de comparadores, de AND OR chains, para a linguagem de Verilog, para poder automatizar todo esse processo.
Ok, muito bem.
Basicamente é isso. Certo.
Então, agradecemos, Bruno, o teu trabalho, tua presença, né? E que continue um bom trabalho.
Certo, muito obrigado, pessoal. Valeu.
Muy bien. Ahora tenemos el autor del segundo postscript presentado, Experimental Evaluation of FPGA Countermeasures Against SCA. Tenemos a Vinicius.
Olá.
Olá, olá.
Pessoal.
Esperamos ver si hay alguna pregunta del público. Tal vez una pequeña pregunta que tengo, no lo vi en tu presentación, de lo que entiendo a la hora de hacer este tipo de evaluaciones para Side Channel Attack. Normalmente la evaluación con equipo y todo se vuelve muy compleja. En tu caso, los resultados que mostraste, ¿cuál es tu setup de evaluación para poder ver esa información, ¿no? tan sensible y poder entonces detectar si se están dando los ataques?
Claro, claro. Eu utilizei basicamente no FPGA da Spartan 6, Xilinx, né? Para fazer todas as minhas avaliações. E através do algoritmo do ES 128 bits, modelados na placa da Chip Whisper, que é um setup para fazer avaliações criptográficas de baixo custo. Então, em comparação de você utilizar osciloscópios de altas resoluções para você verificar exatamente o traço que está acontecendo ou a execução do algoritmo, tu consegue ter com baixo custo de um setup e fazer toda a verificação. Ela contém de duas partes de uma placa. Tem uma placa que é alvo, que ela simula todo o ambiente de avaliação, de fazer o algoritmo, rodar a chave, rodar o texto, fazer a encriptação. e tem um ambiente que fica na captura das informações. Então, através de um cabo coaxial, ele faz uma medição de traço de consumo em cima do resistor shunt do circuito. Daí, ele consegue pegar exatamente a partir do FPGA descrito em conjunto da placa de captura, ele consegue pegar exatamente onde está havendo a execução do algoritmo de criptografia, né? Que é as 10 rodadas subsequentes do AES, e dessa forma tu consegue adquirir os traços a partir de parâmetros que tu vai setar dentro do framework da placa, que é um framework Python. Então tu consegue diferenciar ganho de traço, tu consegue colocar frequências maiores ou menores e diferentes casos de teste. E com esse conjunto de traços adquiridos, tu consegue fazer essa avaliação de side channel attacks através de algoritmos CPA, que tem no framework já da placa, que essa placa já tem uma comunidade bem forte trabalhando em cima dela. Então, tu consegue tanto fazer para CPA quanto para DPA. E no caso de CPA, que é do nosso trabalho aí, que avaliamos, a gente quis utilizar diferentes liquid models. Então, para diferentes tipos de vazamentos, é que a gente quis analisar como que o algoritmo iria se comportar. Além de avaliar também diferentes sínteses de projeto, né? Que quando a gente está descrevendo o FPGA, a gente pode determinar diferentes constraints para síntese, né? Então, ter foco totalmente para redução de área ou para redução de consumo. Então, teve todo esse escopo ali de análise.
Muy bien, muchas gracias. Sí, normalmente cuando veo estos trabajos siempre me interesa mucho esa parte del setup, porque no es tan trivial, no es tan fácil,
Sí.
Involucra muchas cosas, pero es muy, muy interesante desde ese punto de vista. Gracias.
Ok, então vamos para o nosso terceiro paper de hoje. Acho que o Gabriel já está aí.
Boa tarde.
Boa tarde. Então, o título do trabalho é a Two-Level Approximation Logic Synthesis Method Combining Cube Insertion and Removal. Então, primeiramente, obrigado, Gabriel, por ter submetido o trabalho, por estar aqui. Tenho boas e más lembranças da época que eu fazia os mapas de Carnot na mão, então eu acho interessante isso. Cara, mais uma pergunta, assim, digamos, porque eu não conheço muito da área, então eu vi que tem alguns circuitos ali que vocês usam bastante específicos, né, para comparação, que é o que faz sentido, né, tu comparar com como que a proposta de vocês se faz se comporta em relação às outras propostas, né, de aproximação em circuitos específicos. Existe digamos assim, algum trabalho, alguma tendência de avaliar isso em circuitos, digamos assim, em grandes circuitos para ver a diferença ou impacto em alguns outros sentidos, assim, vou dar um exemplo bem trivial, assim, bem tem uma rede, uma CNN mapeada em um hardware, que é um circuito bem mais complexo e tudo mais. Existe alguma tendência, algum trabalho, alguma coisa que usa esse tipo de circuito como teste?
Eu acredito que para 2 níveis não, até porque a escalabilidade é bem limitada. Mas se tu for olhar para outras técnicas, principalmente multinível, né, tu tem todos aqueles benchmarks padrão do Riscas e VCDC, coisa do tipo, todos usam como teste esse tipo de benchmark. E tem um trabalho que eu acho que era ali do Lab também, no colega nosso do laboratório que está lá no Augusto, que ele fazia síntese de uma CNN. Acho que era daquele de Wide Education, faziam a aproximação da rede, do que era um EG, eles aproximavam o EG considerando que tinha uma certa limitação de erro ali, dependendo de como que era a rede neural. Então, eu acho que existem técnicas que têm maior capacidade em relação ao número de entradas, técnicas específicas também para CNN, como tu falou, Mas para 2 níveis eu acho que é relativamente limitado. Seria possível se cortasse, né? Se pegasse uma rede maior e dividisse ela em porções menores. Não sei se foi bem essa a pergunta.
Não, foi mais ou menos isso. É porque isso é uma coisa que eu comecei eu tive mais uma discussão com uma professora sobre isso, que às vezes ver como que isso se comportaria, né, num sistema maior, mas eu entendo que não é algo trivial, assim, de tu avaliar os pontos.
Até um problema, eu acho, também do grande é como é que tu calcula o erro e coisa do tipo, né? Acho que o professor falou antes também que um desafio era como é que tu via o erro do que estava aproximando, e quando tu vai aumentando o circuito, provavelmente ele vai tornando cada vez mais difícil de tu controlar o erro dele.
E agora, acho que isso aqui não é uma pergunta, assim, como é que te dizer, fica à vontade, eu não sei se já trabalhou com isso, mas tem algum estudo de ver como que seria a parte de por exemplo, verificação formal nesse tipo, verificação formal no sentido de eu ter, por exemplo, eu tenho meu RTL aqui e eu aplico, sei lá, o Conforma ou alguma outra técnica, alguma outra ferramenta assim, e eu faço uma comparação se a minha síntese e o meu Golden, né, eles são equivalentes. Existe alguma coisa desse sentido, assim, voltada para essa aproximação?
Eu sei que tem trabalhos que eles chamam de relaxed equivalência, que seria que tu tem a equivalência considerando que tu tem essa certa disponibilidade de erro, digamos assim. Mas em relação a formal, tem técnicas que usam SAT, BTD, acho que SCA também, para tentar calcular de forma formal o erro, né, quanto erro que você está inserindo. Que usam, por exemplo, tipo o meter e coisa do tipo, mas considerando que tu tem essa variação, essa possibilidade de inserir erros.
Excelente. Deixa eu só ver se
no nosso caso, só para terminar, ali como a gente está em 2 níveis, tu tem a tabela verdade, então basicamente ela é formal.
Sim. Não, faz sentido. Só ver se tem alguma pergunta no chat. Não, ainda, o pessoal ainda está um pouco tímido. Então, muito obrigado, Gabriel, pela apresentação pelos comentários.
Muito obrigado.
Muy bien. Entonces, pasemos a la siguiente presentación siguiente autor del trabajo titulado An Approximate Functions Generation Method to ATMR Architecture. So here we have Guilherme. Gracias por tu trabajo y tu presentación y por contribuir al workshop.
Muito obrigado.
Muy bien. Bueno, del chat no tenemos preguntas para ti. Tal vez una pregunta que yo tengo es, ¿cómo consideras que estas mismas nociones se podrían aplicar en sistemas que, no están basados en hardware, sino software, pero donde también se hace triple modular redundancy? En el sentido, por ejemplo, en aviónica, sé que hay muchos sistemas donde se utiliza doble o triple redundancia, pero con procesador. ¿De qué manera vislumbrarías que también se podría utilizar algo aproximado en este tipo de sistemas, donde la redundancia no es un bloque de hardware, sino el procesador como tal?
Pois é, eu vi uma vez, mais focado em software, que ele executava o software 3 vezes, aí pegava o software aproximado também e tentava, e aí via o resultado e comparava eles um com os outros. E aí pegava o resultado e utilizava ele.
Ok, muy bien, gracias. ¿Alguna otra pregunta del público? O Leandro, si tienes una.
Estava tentando falar aqui com parte fechada. Eu conheço um pouquinho só dessa parte de TMRs, né? Conheço bem simples. Eu acho que eu vou fazer mais ou menos a pergunta, mais ou menos no mesmo sentido do que eu fiz antes para o outro participante, que eu vejo que tem esses circuitos assim de benchmark, né, que são normalmente circuitos, nem sempre são circuitos extremamente complexos, assim, ou com lá, algum desses circuitos tem algum laço de realimentação, digamos assim, tem meu Deus, me fugiu o nome agora, tipo uma memória, um flip-flop interno, alguma coisa assim?
Não, os circuitos que eu trabalho, eles são todos combinacionais.
Ah, tá. Não, beleza. Mas na literatura existe algum, digamos assim, benchmark ou circuito de comparação que tenha esse tipo de coisa?
Eu acho que para o TMR em si, não. Eu acho que daí ele separa a parte combinacional mesmo e aplica outra técnica para a parte sequencial.
Ah, beleza. Beleza, então. Era essa a minha pergunta. Isso, então, muito obrigado, Guilherme. Obrigado pela presença.
Obrigado.
Então, vamos para a próxima apresentação, que era do Luiz Antônio Simon. Ver se o Luiz está por aí. O Luiz acho que ainda não entrou. Deixa eu ver. Ou não, eu não sei se tem algum outro dos autores do artigo, que é o Matheus Grelert e o Bruno Abreu. Deixa eu ver aqui se ele já entrou. Não. Não entrou. Então eu acho... Jorge, o que tu acha de a gente passar para o próximo? E depois a gente volta ali?
Sí, podríamos pasar al próximo. Suena bien.
Tá. Tudo bem. Então vamos para o próximo. Do Leonardo.
Leonardo Cobato con el paper The Impact of Parallel Designs on FPGA Switching Virtualization Architecture. Y primero, muchas gracias por tu participación, Leonardo. Tenemos una pregunta del chat para ti. La pregunta es, ¿qué justifica el incremento de los VRAMs en la versión paralela de PVS, en arquitectura paralela de PVS? Entonces, no sé si puedes comentar un poco a qué se debe ese incremento de la utilización de VRAMs.
Primeiramente, boa tarde. Para entender isso, a gente tinha que pensar primeiro como funcionava a arquitetura originalmente, com apenas um módulo de entrada. Ele meio que recebe todos os pacotes e direciona eles para os switches correspondentes de cada um. E para isso, a gente usa um buffer para evitar a perda de pacote quando o tráfego estiver muito alto. Daí, para fazer, na hora que a gente paralelizou, a ideia era para início do projeto apenas duplicar o módulo. Então, cada um dos módulos de entrada, agora paralelizados, continuam com o mesmo tamanho de buffer que tinha antes. E isso justifica o porquê o número de BRAMs aumentou, por causa dos buffers. Mas isso também é uma ideia que a gente está de otimizar essas estruturas.
Muy bien, muchas gracias por tu respuesta. No sé si tenemos alguna otra, si no, igual estamos un poco cortos de tiempo y podríamos pasar a los siguientes autores.
Ok, então muito obrigado, Leonardo, agradecemos a presença e eu envio do paper.
Yeah.
Bom, vamos voltar ao paper anterior que a gente pulou, acho que o Matheus Grelert está aqui, que vai apresentar. Olá, Matheus, tudo bem?
Olá a todos, boa tarde, gente. Desculpa, eu esqueci de lembrar o aluno que era hoje a apresentação dele. Aí eu acho que ele acabou esquecendo, desculpem.
Tudo bem.
Então, estou pronto para as perguntas, vamos lá.
Não, eu estava olhando aqui que vocês fizeram a avaliação foi feita em um neurônio isolado, certo?
Uhum.
Eu entendi, tá, beleza. E
Exato.
qual, eu não sei se eu não vi, tá, eu ia te perguntar qual que era o dispositivo qual que era o FPGA, mas agora que eu vi o, o nome do dispositivo ali, então eu vi que ele...
Por enquanto a gente está mais com FPGA mesmo, Leandro. O aluno ainda não conhecia o fluxo ASIC, né? Porque é todo um processo, né? Até aprender o DHDL, dominar, depois FPGA, fluxo FPGA, depois fluxo ASIC de síntese. Mas agora a gente já está evoluindo o trabalho para uma etapa de fluxo para ASIC também.
Tu sabe me dizer, não sei se tu chegou a entrar nesse nível, né, com ele, qual que é o tamanho das LUTs que estão usando, se é 4, 6?
Não, a gente não olhou a análise detalhada das FPGAs ainda, mas realmente é um passo interessante, né? E claro, dependendo da FPGA, elas têm várias opções ali de otimização das lookup tables, né? Mas realmente é uma etapa interessante, eu acho, ainda nessa etapa de análise de FPGA. Acho que eu vou recomendar que a gente faça uma coleta desses dados. Gostei da ideia.
E uma última pergunta minha, depois acho que se o Jorge tiver alguma pergunta, como que vocês fizeram essa escolha de bits, 6, 8, 10, foi empírico ou foi alguma...
São alguns testes, porque a gente não tem uma aplicação alvo definida, né? O que a gente pôde avaliar é pela literatura que a gente consegue utilizar poucos bits para representar as redes neurais. Amanhã a gente vai ter uma palestra, inclusive, falando que talvez nem precise de pesos, né? Então, tem várias formas de quantizar essas redes, deixá-las mais simples, né? Mas ainda não avaliamos o efeito disso em uma aplicação alvo. A ideia é a gente propor diferentes possibilidades de largura de bits, né? E aí, dependendo da aplicação alvo, teria que, né, executar uma avaliação para ver qual é a perda de desempenho nessa aplicação, né? E isso aí talvez para um trabalho mais à frente, assim, né, que a gente consiga fechar um loop de treina uma rede neural, gera o verilog ali correspondente, quantiza ele, né, e aí avalia tanto o desempenho em área quanto na predição, como a gente faz com o Bruno agora, por exemplo, né? Com certeza é uma coisa que a gente vai avaliar. Mas por enquanto a gente só quer ver, para essas possibilidades, para cada tipo de quantização possível, esse é o impacto.
Certo. Então, muito obrigado, Matheus. Agradecemos e desculpa aí pela confusãozinha que tem para acessar. Certo?
Tudo certo.
Obrigado. Até
Eu que
mais.
agradeço. Obrigado.
Então, acho que vamos para o próximo, né?
Sí. El siguiente fue la presentación de Joao Dick, Quality and Complexity Assessment of Learning-Based Image Compression Solutions. Muchas gracias por tu presentación, Joao. Boa tarde.
Boa tarde, Leandro. Boa tarde, Jorge.
Boa tarde, boa tarde.
Bueno, por ahora no tenemos preguntas en el chat. Tal vez la única pregunta que tengo, porque no soy un experto en la parte de imágenes, pero la decisión de aplicar la evaluación de ciertas métricas solo para el canal de luminosidad, ¿por qué esa razón, no? Y únicamente dejar LPIPs para la parte completa de RGB. Não sei se poderias elaborar um pouco.
Sim, sim. Então, a gente decidiu fazer análise somente na luminância em todas as métricas que a gente pôde, né? Justamente por, às vezes, alguns canais, a visão humana tem mais sensibilidade, como, por exemplo, a diferença do canal do verde para o vermelho, né? A gente tem uma sensibilidade diferente a esses sinais. E o LPIPS, como ele é uma métrica que na verdade, é uma métrica dada por uma rede neural, né? Que é treinada para efetuar essa medida em RGB. Então, por isso a gente não pode utilizar ela somente na luminância, porque seria contraindicado, né, por esse treinamento.
Ok, muito bem, graças.
João, tem só uma perguntinha. Eu vi ali que, né, basicamente, os algoritmos que vocês estão como target são algoritmos de imagens estáticas, né?
Sim, sim.
Tem alguma perspectiva de trabalho futuro voltado para vídeos em si?
Então, nossa perspectiva agora seria, depois dessa análise, né, ainda focar em imagens, mas propondo uma arquitetura nova ou uma modificação de arquitetura existente mais eficiente, né, para atacar essa complexidade. Eu sei que existem coisas com vídeos nessa área, mas a gente ainda não estudou muito isso, né? A nossa pesquisa está mais na área de imagens, por enquanto.
Certo, então. Obrigado, João. Obrigado por ter enviado o trabalho.
Nada, obrigado aí.
Ok. Então, deixa eu ver aqui quem que é o nosso próximo trabalho. É do João Vitor da Silveira e do Gustavo Greff. Isso?
Olá, boa tarde.
Isto. Boa noite. Boa tarde.
Então, o nome do trabalho é Adding a Qiskit Support to Simulate Quantum Algorithms in FPGA. Então, deixa eu ver se tem alguma pergunta, né, no chat. Ainda não temos. Eu confesso que eu conheço muito pouco eu acho legal a parte de Quantum Computing, mas eu conheço bastante... Eu conheço muito pouco, né, do como é a implementação. Então, vou fazer uma pergunta um pouco mais filosófica, assim, né, para vocês. No desenvolvimento do trabalho de vocês, qual que foi a parte que vocês acharam mais complexa ou mais trabalhosa de ser resolvida?
Eu acho que, assim, foi um pouquinho começar a compreender como é que funcionava, por exemplo, os cálculos feitos de vetores e matrizes, e começar a compreender que um qubit, na verdade, como tu falou, né, num sentido filosófico, ele está num sentido de superposição, ele está sendo 1 e 0 ao mesmo tempo, só que tendo uma probabilidade. Daí, dependendo das operações que você faz, muda. Então, é difícil, às vezes, tu colocar isso na tua cabeça e tentar compreender o que é isso no mundo real, porque é uma coisa diferente, né?
Para mim, eu acho que é mais compreender essa parte da física quântica, sobre como funciona... compreender essa parte da física quântica dos qubits e tal, mas também como é feito para incorporar isso no algoritmo. Para mim, essa foi a parte mais complexa, assim, até agora.
E uma pergunta, assim, sobre um pouquinho mais de implementação. Essa comunicação do local run, external run que vocês têm com o Qiskit, vocês usam alguma linguagem específica ali para essa comunicação, ou é padrão, assim, envia um pacote, sabe, JSON, alguma coisa assim, para fazer essa comunicação?
Então, atualmente a gente se encontra bem no início do desenvolvimento.
Uhum.
Mas, assim, a gente acredita que a comunicação vai ser padrão feita por JSON mesmo.
Certo, então. Muito obrigado, João e Gustavo. Obrigado pela apresentação, por estarem aqui.
Eu que agradeço. Uma boa tarde e uma boa noite a todos.
Obrigado, realmente.
Obrigado. Ok, la siguiente presentación fue por Pedro Silva, An Exploration of Approximate Computing Comparators in Decision Tree Algorithms.
Olá.
Hola, Pedro.
Olá, tudo bom?
Tudo bom, gracias por tu trabajo. Tal vez mi primera pregunta, porque noté que utilizaste un cierto conjunto de versiones de sumadores aproximados. Entonces, igual por los que vi que seleccionaste, imagino que tu trabajo está de un nivel de abstracción de circuito para abajo, o sea que hiciste toda la implementación a nivel de transistores. ¿Cómo crees que se comportaría, tal vez escalando a nivel de RTL y considerando otras versiones de las muchas versiones aproximadas para sumadores que hay?
Sim. nós utilizamos duas abordagens, né, para o desenvolvimento de comparadores, e uma delas é usando full aders aproximados. E esses somadores realmente precisam... a aproximação deles é feita realmente a nível de circuito, então passar eles para um nível de abstração um pouco mais alto, né, em nível de RTL, por exemplo, requeriria que a gente tivesse acesso às células desses full aders, né, tipo, ao layout desses full aders e toda a caracterização deles. Mas a outra parte do projeto já consta em um nível de projeto de portas lógicas mesmo, então já é uma abstração um pouquinho mais alta, apesar que a gente ainda se manteve na simulação elétrica.
Ok, muy bien. Leandro, no sé si tienes alguna pregunta.
Não, eu só tava olhando aqui um pouquinho, né, todos esses circuitos são baseados, todos eles são CMOS, né?
Alguns...
Digo, estático, não é com lógica dinâmica, né?
Não.
Só por curiosidade, pensar em algum dia fazer um teste de circuito aproximado usando lógica dinâmica? Então, já que tu está aproximando tudo, aproximar a parte dinâmica também. Talvez seria... Porque tu come uma parte inteira da rede, né? Essa que é
Sim. Alguns full aders aproximados que nós estamos usando são baseados em PTL. Eu ainda sou da graduação, sou da ciência da computação, não tenho muito...
não, tudo bem. É que você deve ter visto que é o seguinte, normalmente a tua saída, tu tem uma parte em cima,
Sim.
É uma parte, digamos assim, inversa do que tem embaixo, né?
Uhum.
Na dinâmica, tu corta, seja normalmente a parte de cima, ou a parte de baixo, depende, tu corta inteiro aquilo ali, e tu deixa ela, tu pré-carrega, tu bota um valor, tipo, eu digo que a saída é 1 ou é 0, tô dizendo. E aí, só que esse resultado tu ignora. Então eu carrego, venho o clock, carrego, daí eu falo assim, bom, a partir de agora tu avalia se a minha saída vai se permanecer 1 ou se ela vai para 0. Então tu tem que ficar fazendo esses ciclos, assim. Mas é uma pergunta um pouco avançada, então.
Acho que poderia ser bastante interessante explorar também.
Certo, então.
Sugestão.
Muito obrigado, Pedro. Obrigado pelo trabalho.
Eu que agradeço.
Aqui. E para o último trabalho, nós temos o trabalho da Laura. Vou adicionar a Laura aqui. Hola, Laura.
Hola, buenas tardes.
Buenas tardes. Creo que Jorge es más acostumbrado a hablar español.
Un poco,
Mi
solo un
español
poco.
no es el mejor del mundo, entonces...
No, está muy bien. Muchas gracias, Laura, por tu trabajo. Tenemos una pregunta, bueno, yo tengo una y tenemos una del chat, y bueno, en parte están muy relacionadas. Tal vez por ahí la puedes estar viendo. La pregunta es, ¿cuál sería el siguiente paso en el estado del arte para los Network Chip como una solución de interconexión en MPSoC? Entonces, no sé si en parte de tu trabajo has podido considerar o ver qué es lo que en la literatura se propone como el siguiente paso al respecto de Network Chips.
Sí, lo que sigue o lo que seguiría es ahora ahondar en el estado del arte de la reconfigurabilidad en redes en chip. O bueno, en general en cualquier interconexión entre chip. Entonces, bueno, ahí ya toca pasar a tocar qué tipo de reconfigurabilidad voy a tocar. Aparte de, la idea se tiene de implementar un dispositivo de interconexión a nivel hardware, entonces también me va a tocar hacer eso. Y luego en el equipo de trabajo en el que estoy, bueno, también tocaría la parte de, se va a tocar SDN, la parte de administración de la interconexión reconfigurable por software, pero bueno, ese ya no es mi tema. Entonces se supone que eso es lo que sigue, ahondar en la parte de reconfigurabilidad en interconexiones en chip.
Cuando hablas de reconfigurabilidad, es más la parte del ruteo, ¿no? De la interconexión entre los diferentes dispositivos o de algún tipo también de reconfigurabilidad en, no sé, en la forma de priorizar la transferencia de datos o algo por el estilo.
Ok, sí, bueno, como lo toqué un poquitito en la presentación, pues no solamente es en topología, sino puede ser en arbitraje, puede ser en ancho de banda, puede ser también en enrutamiento y también tal vez en el tamaño de paquetes. Entonces, estoy armándome como una tablita, pero es así para saber más o menos en dónde se están enfocando en reconfigurar y en dónde tal vez todavía hace falta trabajo, y ahí es donde entraría yo.
Muy bien, sí, porque resulta interesante ver en dónde tenés más beneficios, más ganancias, o dónde vale realmente la pena invertir los esfuerzos en esa parte de configurabilidad.
Sí, todavía falta ahí reunir más trabajo para saber en dónde.
Bueno, muchos éxitos. Muchas gracias por tu participación, Laura.
Gracias.
Então, pessoal, aqui com a apresentação da Laura, nós encerramos essa sessão de posters, né? E nos encaminharemos então para a próxima sessão. Deixa eu só não me perder aqui. Sim.
Muito obrigado, Leandro. Muito obrigado, Jorge, por fazerem as vias de chair dessa sessão. E então agora a gente começa no mesmo roteiro dessa primeira, né? A gente começa a segunda sessão de posters com, primeiramente, os vídeos. Então, o pessoal que ficou meio tímido nessa primeira sessão, então esperamos que nessa segunda o pessoal poste mais perguntas aqui no chat. E aí, em seguida, a gente continua com a sessão de perguntas e respostas ao final dessa sessão. Muito obrigado, Leandro. Muito obrigado, Jorge, pela participação de vocês.
Prazer.
Eu agradeço.
Então, pessoal, enquanto a gente prepara aqui o vídeo da próxima apresentação de posters, a gente continua com esse banner aqui da primeira apresentação, e logo em seguidinha a gente já começa a apresentação, então, em sequência dos vídeos da segunda sessão. Então, a segunda sessão vai versar sobre também alguns outros trabalhos remanescentes de computação aproximada, Approximate Computing, design digital, projeto digital para circuitos low power, aplicações de processamento digital de sinais e codificação de vídeo. Então, a gente vai ter para essa sessão, então, os chairs, professor Daniel Palomino, da UFPEL, e Felipe Bortolom. Perfeito, então, pessoal, ficamos com a sessão 2, com os posters, então, na sequência. Nos vemos em 50 minutos para, então, a sessão perguntas e respostas. Muito obrigado.
Muito obrigado, pessoal.
Olá, eu sou Patrícia da Costa, estudante de doutorado do PG Micro da Universidade Federal do Rio Grande do Sul. Eu vou apresentar o trabalho intitulado Boosting the Efficiency of the Harmonics Elimination VLSI Architecture by Arithmetic Approximation. Este trabalho é uma parceria entre a Universidade Federal do Rio Grande do Sul e a Universidade Católica de Pelotas. Essa apresentação está dividida em introdução, proposta, metodologia, resultados e conclusão. Os sistemas para aquisição de sinais bioelétricos são facilmente contaminados por sinais externos, que modificam seu comportamento. Um exemplo de sinais externos são as linhas de energia e suas harmônicas, que adiciona comportamento sinusoidal indesejado ao sinal bioelétrico aquisitado. Uma solução para o cancelamento das linhas de energia é a eliminação de harmônicas, que é baseada em filtros adaptativos e gerador de harmônica. A arquitetura de eliminação de harmônicas utiliza muitos operadores aritméticos, e um trabalho apresentado em na literatura já utiliza somadores aproximados na arquitetura HE, usando o filtro adaptativo NLMS. A proposta deste trabalho é utilizar a mesma arquitetura proposta em entretanto, além de utilizar somadores aproximados, explorar o uso de multiplicadores aproximados na arquitetura, impulsionando ainda mais a eficiência energética da arquitetura HE. Bom, então qual é a nossa proposta? Nós utilizamos somadores aproximados e utilizamos multiplicadores aproximados. Os multiplicadores utilizados foram o Drump, o Roba e o Loba, e os somadores foram o LOA e o COP. Nós escolhemos apenas esses porque o trabalho 1 indica que esses são os 2 melhores somadores para a arquitetura. Nós também executamos uma otimização do filtro NLMS, que a arquitetura proposta em utiliza 4 ciclos de clock, e a nossa utiliza apenas 3. O que nós fizemos? Em vez de utilizar Mi como entrada do filtro, nós utilizamos Mi como um deslocamento por 2. Assim, ele é feito a cada nova entrada de E, não precisando de um ciclo para executar essa multiplicação. Para avaliar nosso bloco de eliminação de harmônicas, nós utilizamos uma entrada X de N de uma linha de energia de 60 Hz, contaminamos um sinal de EEG com 60 Hz e as suas primeiras 3 harmônicas. Esse sinal de EEG foi retirado de um banco de dados reais, amostrados a 1 kHz, e o objetivo deste bloco é eliminar a contribuição dessas amostras, ou seja, das linhas de energia e das 3 primeiras harmônicas, deixando o sinal de EEG limpo. Para avaliar a extração das interferências de linhas de energia, nós utilizamos como referência o sinal de EEG do banco de dados e a saída do nosso filtro, e calculamos a métrica NSE. Então, aqui nós apresentamos os resultados, onde o gráfico mostra a qualidade do sinal medida em NSE e o total de potência salva. No primeiro gráfico, nós avaliamos os multiplicadores, ou seja, o Loba, o Roba e o Drum. O que vemos nesse gráfico é que o Drum K igual a 3 já não serve para a nossa aplicação, pois existe um limite de NC e acima deste limite, a saída da arquitetura apresenta mais ruído do que o próprio sinal desejado. Olhando a curva de Pareto, percebe-se que o Loba igual a 0 é o que apresenta a melhor redução de potência, comparado com todos os outros avaliados. Nós fizemos outra exploração, utilizando o Loba igual a 0, somadores exatos, o LOA e o COP, e observando a curva de Pareto, percebe-se que o LOA igual a 6 apresenta o melhor resultado de potência salva, apresentando uma redução de praticamente 45%, um pouco mais de 45%, comparado a um somador exato. Comparando o nosso resultado com o trabalho anterior da literatura, nós temos uma redução significativa em área, de quase 30%. Nós reduzimos os ciclos de clock, como anteriormente mencionado. Então, nós reduzimos a nossa frequência de síntese, porque a gente fez a síntese do menor esforço, como o que foi proposto em E comparando energia por operação, nós temos um ganho extremamente significativo de 60%. Esse trabalho explorou multiplicadores aproximados e somadores aproximados na arquitetura de eliminação de harmônicas para melhorar ainda mais a eficiência energética, apresentando como resultado uma redução de 60% em energia comparado com o artigo da literatura.
Olá, me chamo Morgana. O meu trabalho é intitulado Arquiteturas de Baixo Consumo Energético para Transformar do Wavelet RAR no Processamento de Sinais Respiratórios. Bom, Atualmente, a incidência de doenças respiratórias na população é muito alta, né? Portanto, distinguir entre sons respiratórios normais e os ditos anormais, como as estretores e sibilos, é crucial para o diagnóstico médico preciso, né? Então, a frequência respiratória dita normal, ela varia de 63 a 125 Hz, já a crepitação de 100 a 200 Hz e o sibilo de 200 a 400 Hz, podendo se estender até 2.000 Hz, de acordo com a literatura. Bom, esse trabalho ele tem como objetivo analisar os sinais, as doenças, né, vinculadas aos sinais respiratórios. De 0 até 62,5, nós temos os componentes ruidosos que afetam esses sinais respiratórios e as patologias de 63 a 2.000 Hz, onde a wavelet HAR com nível de decomposição 5 obtém, né, essas faixas de possíveis patologias pelos níveis de decomposição de D1 a D5. E o nível de aproximação A5, então, nos dá esse ruído, essa frequência ruidosa, né? Todos os sinais respiratórios, eles são reais, obtidos, né, do banco de dados da Fisionet. Aqui, então, temos uma figura demonstrando o processo de processamento dos sinais respiratórios, né? Então, aqui as possíveis patologias, né? Então, dos níveis de decomposição D1 até D5, e aqui na figura G, então, nós temos como ocorre, né, o acréscimo dos componentes ruidosos, né? E aqui na figura H, então, o tempo de amostragem, né, de 80 vezes 10 na menos 5 segundos, né, pela frequência alcançada no processo de co-simulação do hardware, né, que foi de 500 MHz. Então, aqui nós temos, né, as arquiteturas propostas. Foram propostas 5 tipos de arquiteturas, né, de wavelet HAR 5, com a ideia de obter os melhores resultados em termos de dissipação de potência, né? Elas foram feitas com esquema hierárquico, através de módulos de processamento de wavelet HAR com nível de decomposição 1, níveis de decomposição 2 ou nível de decomposição 3. E os multiplicadores foram, então, introduzidos o esquema de multiplicação MCM. Bom, em termos de resultados, nós temos os melhores resultados em termos de área para a wavelet HAR 5 com a arquitetura 4, bem como em termos de dissipação de potência e energia, também para esse esquema wavelet HAR nível de decomposição 5, arquitetura 4. Bom, em termos de comparativo com o estado da arte, nós obtivemos os melhores resultados com a wavelet HAR 5, arquitetura 4, né? Então, notavelmente, nossa proposta de arquitetura ela foi mais eficiente em termos de energia do que as soluções, né? Alcançando um EPO de 75,64 femtojoules por operação, né? O que representa uma redução de 1.150 vezes comparado, né, com então, o estado da arte, que é a proposta de Shen 2015. Bom, justificamos, né, esses resultados impressionantes frente à literatura, né, porque nós tentamos reduzir a presença de blocos desnecessários para aplicação, né, e, além de a nossa wavelet HAR 5, o componente de aproximação nos dá exatamente a componente ruidosa que afeta os sinais respiratórios. Além disso, né, o Shen ele não faz nenhum esforço, né, para otimizar a arquitetura de hardware para o módulo, né, da wavelet HAR. Bom, como trabalhos futuros, né, a gente poderia usar um algoritmo de classificação para os sinais respiratórios, ao invés, né, de analisar as faixas de frequência. Bom, agradeço pela oportunidade de apresentar tal trabalho, né, no evento deste ano.
Hello everybody, my name is Tulio and I'm here today to present about our architecture, which is a high throughput architecture for the AV1 arithmetic encoder using open source CDA tools. So let's first understand what AV1 is. Well, we all know how much we rely on videos nowadays, from YouTube and Netflix all the way to Zoom and Instagram. We are in touch with videos every day, every time. But videos are quite tricky to be transmitted on the internet because they are very, very sizable. So in order to make the user experience smoother, we can use video codecs or video coding standards to reduce the overall size of videos. And AV1 is very effective on that. AV1 was released in 2018 by the Alliance for Open Media, and it is royalties free. Okay, but why do we need to accelerate the AV1 codec? Well, in order to effectively reduce the overall sizes of videos, AV1 uses several different tools and algorithms that are very complex, and therefore they are quite slow to be executed in a software-only solution. Sometimes we do have time. Like, imagine you just uploaded a video to YouTube. You have some time before the video needs to be available to everybody to watch. So YouTube has more time to work on the video and to encode the video, but sometimes we just don't have that time. Imagine you are in a live streaming event or you are in a video conference. A certain number of frames needs to be ready in 1 second. And so for solutions such as that latter, we can use a hardware architecture as a great option to accelerate the AV1 codec. And for this presentation, I will focus on some analysis we made using only open source tools and PDK. The first tool we use is OpenRoad, then OpenLane, and then the SkyWater 130 nanometers PDK. But let's first understand the difference between OpenRoad and OpenLane. Well, OpenRoad started as an ASIC flow tool. So you have for planning, ASIC placement, global routing, clock tree, and some other steps, but it doesn't have the synthesizer. The developers, however, they decided to suggest a synthesizer, which is YOSYS. So OpenLane came as an option to put everything together, several different tools, and put everything together and just run one ASIC flow that goes all the way from the Verilog file to the GDS2 file. And this is the architecture we analyzed. This is a 4-stage pipeline we published on the SBCCI 2021 event. And the first stage is responsible for some pre-calculations, the second for the range updating process, the third for the low updating process, and the fourth for the carrier propagation process. Okay, moving ahead to the results, we can see here a very unfair comparison. We took a 65 nanometers PDK using paid tools against a full open source solution using the SkyWater 130 nanometers PDK. Here you can see a huge difference in frequency and area. Also here on this slide, you can see a table where we use the exploration part of OpenLane. So OpenLane uses YOSYS in an exploration mode, and it tries to find different possibilities for area and delay. And this is the table that they give as a result. And also you can see here the layout view from the GDS2 file we took at the end of the process. And to conclude this presentation, I just would like to highlight how important it is for us to have open source EDA tools. We all know how expensive EDA tools are, and sometimes it's quite hard for people to join our beautiful area because of lack of tools or because they are not enrolled in some university that has EDA tools and everything. So it's great to have open source options. And that's it. Thank you very much for your attention and have a good day.
Olá, meu nome é Bruna Nagai, eu sou estudante de graduação em Engenharia Eletrônica na Universidade Federal de Santa Catarina e atualmente eu sou bolsista de iniciação científica no Laboratório de Computação Embarcada da UFSC. Hoje eu vou apresentar o meu pôster intitulado Interpolation Filter Design Using Multipliers Constant Multiplication. Bom, A área de compressão de vídeo vem aumentando muito por conta dos serviços de streaming, redes sociais, serviços de comunicação, e isso vem acelerando muito por conta do Covid-19. E gravar e reproduzir vídeo, hoje em dia, passou a ser uma coisa muito comum. O vídeo que vocês estão vendo agora é um exemplo disso. Então, os codificadores e os decodificadores são uma série de algoritmos que fazem justamente isso. Eles permitem a compressão dos vídeos para possibilitar menor gasto com o armazenamento e também para garantir uma transmissão de dados maior. E o AV1 foi desenvolvido em 2015 com esse propósito. Ele é um projeto open source que foi criado pela Alliance for Open Media, que é composto por grandes empresas de tecnologia, como a Google, Nvidia, Intel, Netflix e outras empresas nesse ramo. A questão é que o AV1, especialmente, foi desenvolvido com a possibilidade de recursos muito grande. Isso acaba sendo computacionalmente muito complexo e acaba gastando maior tempo de codificação do que os outros padrões. Aqui no gráfico ao lado está sendo feita uma comparação relativa entre o HEVC, o AV1 e o VTM, sendo o HEVC utilizado como base. Então, a gente vê que o AV1, que é essa barra em verde, precisa de aproximadamente 10 vezes mais tempo para processar um vídeo HD do que o HEVC, e cerca de 14,5 vezes mais tempo para processar um vídeo HD. Esse e outros estudos mostraram que a parte que mais consome tempo é a predição interquadros. E é por causa dessa grande quantidade de tempo gasta que é importante elaborar módulos de hardware que possam acelerar esse processo. Como eu acabei de mencionar, a predição interquadros é uma das etapas que mais são demoradas na compressão de vídeo, mas é uma das partes mais importantes também. Temos aqui dois processos de predição, a parte de intraquadro, que explora as redundâncias espaciais dentro de um mesmo quadro, e a predição interquadro, que vai explorar as redundâncias temporais, ou seja, entre quadros. E o trabalho feito para o pôster está na parte de predição interquadros, onde é feita a estimação de movimento de um bloco de um quadro para o outro, através da utilização de um vetor de movimento que vai apontar para onde o bloco foi deslocado. E como essa precisão do vetor de movimento é fracionária, então é preciso gerar os pixels fracionários utilizando o filtro de interpolação. Então, a arquitetura proposta para a família de filtros de interpolação Smooth está representada nesse diagrama, que foi colocado assim no pôster, mas ele pode ser mais claro se for representado dessa outra maneira. Aqui, a ideia é que a gente tem uma linha de pixels entrando e ela vai ser processada por todos os 15 filtros da família Smooth. Esse outro diagrama mostra melhor como cada um dos 15 filtros é composto. O filtro é uma série de multiplicações por constantes. Então, ao invés de utilizar multiplicadores convencionais, foi utilizado o algoritmo Edcub para otimizar a arquitetura e implementar deslocamentos e somas. Então, o diagrama está mostrando que os coeficientes foram colocados como entrada no Edcub e foram colocados de forma transposta. E então, como saída, a gente obtém as multiplicações. Portanto, com a multiplicação feita, o valor resultante é somado às outras parcelas computadas por outros blocos, que são representados por A0 e vão até A5. E é feito como está mostrado nessa equação abaixo, que está representando o filtro 7. Então, os resultados eles estão sendo mostrados nessa tabela e eles foram obtidos pela síntese feita para uma FPGA Altera do modelo ARIA10. A gente vê que a maior taxa de bits foi de 302 megamostras por segundo, obtendo uma resolução de 1.600 pixels a 45 fps. Bom, então o trabalho contribuiu para o desenvolvimento de um módulo acelerador de hardware para os filtros de interpolação do Smooth para o AV1. Bom, é isso então. Qualquer coisa, podem entrar em contato comigo. Muito obrigada.
Bom dia a todos, meu nome é Pedro Tauan, Sou estudante de doutorado pela Universidade Federal do Rio Grande do Sul e venho apresentar hoje meu trabalho intitulado como Architectural Exploration for Energy Efficient Fixed Point Kalman Filter VLSI Design. Esse trabalho foi desenvolvido em parceria entre a Universidade Federal do Rio Grande do Sul e a Universidade Católica de Pelotas. O filtro de Kalman foi apresentado como uma solução para problemas lineares quadráticos, que tem como função principal estimar vetores de estados de sistemas dinâmicos lineares corrompidos por ruído branco. Com o sistema, é possível estimar, filtrar e simular variáveis de sistemas corrompidos e até mesmo desconhecidos. Em sua vasta aplicabilidade, é observado o uso do filtro de Kalman em áreas como navegação, posicionamento de GPS, reconhecimento de imagens e entre outros. Entretanto, dada sua elevada complexidade de cálculo, o desenvolvimento de arquiteturas dedicadas para o filtro de Kalman que consuma baixa potência em uma reduzida área do circuito se tornou um desafio tecnológico. Sendo assim, esse trabalho tem como objetivo explorar soluções arquiteturais para a aplicação do sistema do filtro de Kalman completo, buscando sempre observar as melhores soluções em relação à área do circuito, potência dissipada, energia consumida por operação e velocidade de processamento. O filtro de Kalman é caracterizado por 8 diferentes equações matriciais, nas quais aplicam multiplicação, soma e inversão matricial. Destaca-se a equação do ganho de Kalman, no qual realiza inversões matriciais a cada interação do filtro, elevando assim a complexidade do sistema. Para este trabalho, foram desenvolvidas diferentes arquiteturas para cada equação do filtro de Kalman em diferentes formas de aplicação, como na sua forma totalmente sequencial, na forma semiparalela e na forma totalmente paralela. Todas as arquiteturas foram desenvolvidas utilizando sinais de entrada com precisão de 20 bits, representando um ponto fixo. As sínteses aqui realizadas foram realizadas utilizando a ferramenta Genus da Cadence, com uma tecnologia de 65 nanômetros e uma frequência de operação de 100 MHz. Frequência esta a frequência máxima da equação mais complexa do sistema, no qual seria o ganho de Kalman. Uma primeira rodada de síntese foi realizada para cada equação do filtro de Kalman em suas diferentes formas, para que assim a gente pudesse observar os melhores resultados e escolher as arquiteturas mais apropriadas para a implementação de um sistema completo. Sendo assim, observando os resultados de área, velocidade de processamento e consumo de potência, definimos 8 arquiteturas em suas diferentes formas, sendo elas sequenciais e semiparalelas, para que assim a gente possa aplicar o sistema completo. Nesse slide estão apresentadas todas as arquiteturas utilizadas no sistema completo do filtro de Kalman com suas respectivas equações. Assim, foi realizada uma segunda rodada de teste para poder observar os resultados de síntese para o sistema completo do filtro de Kalman, obtendo um sistema com área de 4,46 mm², utilizando 34 ciclos de relógio para todo o seu processamento, consumindo então uma potência de 1.305 microbytes. Além disso, também foi observado a energia consumida por operação, no qual encontramos o valor de 27,74 picojoules. Para concluir, nesse trabalho foi apresentado diferentes arquiteturas dedicadas para a implementação completa do filtro de Kalman. Para cada equação foram desenvolvidas diferentes arquiteturas em suas formas totalmente sequenciais, semiparalelas e totalmente paralelas, totalizando assim um montante de 24 arquiteturas desenvolvidas. Buscando sempre a melhor combinação entre área do circuito, situação de potência e velocidade de processamento, foram escolhidas 8 diferentes arquiteturas em suas respectivas formas que apresentaram os melhores resultados para a implementação do circuito completo do filtro de Kalman. Comparações foram realizadas com a literatura e foi possível observar que a arquitetura aqui proposta nomeada como Balanced Common Filter, apresentou os melhores resultados em relação ao número de operadores aritméticos utilizados, potência dissipada e energia consumida por operação e velocidade de processamento. Muito obrigado pela atenção de todos. Fico aberto a perguntas.
Meu nome é Thalita, irei apresentar a vocês o meu pôster sobre Explorando Computação Aproximada para um Filtro Gaussiano 2D com Precisão Configurável em Tempo de Execução. Eu faço parte do programa PG Micro da URGS. Os meus orientadores são os professores Paulo, Leonardo e a colaboradora Cristina. Irei apresentar a introdução do tema, comentar sobre a proposta do trabalho, apresentar a arquitetura do filtro gaussiano, comentarei dos resultados obtidos através da análise e, por fim, as considerações finais. Introdução. Em nosso dia a dia, utilizamos vários aplicativos através dos smartphones e isso gera um alto esforço computacional, fazendo com que nós, projetistas, busquemos abordagens para obter eficiência energética desses dispositivos digitais. Nesse âmbito, então, o filtro gaussiano surge como atenuador de ruídos indesejáveis em bordas de imagens digitais. Como técnica para aumento de desempenho, redução de área e dissipação de energia, emerge o conceito de computação aproximada. A proposta deste estudo é explorar a computação aproximada através de uma granularidade fina, para o projeto de um filtro gaussiano 2D configurável em tempo de execução. A arquitetura do filtro gaussiano opera em diferentes perfis de configurabilidade, sendo de 3 a 8 bits. Ela pode ser gerenciada pelo sistema ou usuário, para atender requisitos de maior desempenho ou qualidade. A técnica de clock gating é aplicada nos 5 bits menos significativos do registrador, onde o sinal de reset será avaliado para se observar o efeito de resetar ou não esses bits. A implementação foi feita em ASIC e sintetizada para o PDK de 65 nanômetros. As frequências de operação utilizadas foram de 63 MHz para processar vídeos Full HD, 249 MHz para processar vídeos Ultra HD. Sobre os resultados, a imagem da letra A mostra um filtro preciso, ou seja, de 8 bits. Na letra B, temos uma configuração do filtro em 3 bits de redução, com PSNR de 37,2 decibéis, em comparação com o filtro preciso. E na letra C é mostrado um mapa de calor para melhor observar as diferenças entre ambas as imagens A e B. O gráfico à esquerda apresenta a relação entre o consumo de potência e o PSNR para as configurações de 7 a 3 bits da arquitetura. Observa-se que quanto menos redução na quantidade dos bits das imagens testadas, mais alto o valor de PSNR, obtendo-se então uma melhor qualidade. O gráfico da direita mostra uma análise combinatória para as 32 combinações das 10 imagens do benchmark BSD, a partir da versão de redução de 5 bits da arquitetura do filtro. Os pontos indicam o valor médio de PSNR, enquanto que as barras indicam o 3 sigma desvio padrão. Os resultados indicaram que, ao se utilizar o sinal reset, isso impõe um ciclo extra de clock para a configuração, não resultando em melhor qualidade. Logo, deve-se evitar usar o sinal de reset nos bits menos significativos, preservando assim a qualidade da aplicação. A tabela apresenta os valores de potência dinâmica, desde a versão precisa, de 8 bits, até todas as versões aproximadas, observando-se que a potência diminui, conforme reduz o número de bits na configuração da arquitetura. Ocorreu um overhead de 15% na área devido à adição de circuitos extras da técnica de clock gating aplicada nos bits menos significativos da arquitetura. Bom, por fim, então, o trabalho encontra-se inserido no projeto de aceleradores de hardware do filtro gaussiano. Ele buscou por explorar o trade-off entre eficiência energética e qualidade da aplicação. Os resultados mostraram que a redução de energia foi de 9,87% a 58,96%, e também houveram avaliações no quesito da qualidade ali do sinal de reset, o que torna a arquitetura viável para gerenciar energia e qualidade da aplicação. Muito obrigada.
Olá, eu sou Patrícia da Costa, estudante de doutorado do PG Micro da Universidade Federal do Rio Grande do Sul. E hoje vou apresentar o trabalho intitulado Fixed Point and LMS and IP and LMS VLSI Architectures for Accurate FCG and FHR Processing. Este trabalho é uma parceria da URGS com a UCPEL. Essa apresentação está dividida em introdução, proposta, resultados e conclusão. O eletrocardiograma fetal, retirado do abdômen materno, fornece informações importantes da saúde do feto, como o batimento cardíaco fetal. E esse monitoramento pode ser realizado por longas horas, propiciando assim a implementação de equipamentos médicos de monitoramento remoto. Para executar a extração do FCG do abdômen materno, algumas estratégias são propostas na literatura, baseadas principalmente em redes neurais ou filtros adaptativos. A proposta do nosso trabalho é explorar dois filtros adaptativos, o NLMS e o IPNLMS, para a extração do sinal do FCG. E também nós vamos utilizar o algoritmo de Point-Tompkins, proposto na literatura, para a extração do batimento cardíaco fetal. Bom, qual é a nossa proposta? Para o NLMS, a nossa proposta é reduzir o número de ciclos de clock da arquitetura proposta em 1. Essa redução pode ser vista em azul no fluxograma. Para o PNLMS, nós propomos uma arquitetura totalmente sequencial, semelhante à do NLMS. Através do fluxograma é possível perceber que ele necessita de um maior número de operações para extrair o sinal fetal, ou seja, ele é mais complexo. Apesar de ser mais complexo, ele é mais preciso na extração do FCG, como nós veremos ao decorrer deste trabalho. Então, sublinhado em azul escuro também, todas as operações estão dependentes da largura do filtro. Por isso, inicialmente nós fizemos uma avaliação em software para decidir qual a largura do filtro necessária e qual é o passo de adaptação do filtro. Então, a gente avaliou as métricas de RNC, SNR e PRD e utilizamos um banco de dados sintéticos. Assim, nós tínhamos a saída desejada e podíamos comparar com a saída do nosso sistema. O que nós percebemos através desses gráficos é que o melhor valor de passo de adaptação é 0,05 e que existe um ponto máximo em 140 coeficientes para o NLMS e 120 coeficientes para o IPNLMS. E nós optamos por utilizar 140 coeficientes no NLMS e 120 coeficientes no IPNLMS. Percebe-se que o IPNLMS ele precisa de mais operações, só que ele precisa de um menor número de coeficientes. Essas duas arquiteturas, tanto o NLMS quanto o IPNLMS, elas necessitam de operação de divisão. Assim, nós exploramos três algoritmos de divisão, são eles o Restore, o Newton Raphson e o Goldschmidt, os três respondendo em um ciclo de clock. O que a gente percebe com a avaliação das métricas é que o Restore apresenta o melhor resultado de precisão e o Goldschmidt e o Newton Raphson apresentam resultados muito similares. Nesse gráfico, a gente também avalia a quantidade de bits, sendo que a gente utilizou uma estratégia de ponto fixo, sendo que a vírgula está no meio dos bits. E avaliando a quantidade de bits, a gente percebe que existe um ponto ótimo em 34 bits. Bom, nosso resultado de síntese, então, primeiro avaliando os divisores, então aqui a gente tem os resultados Restore, Goldschmidt e Newton Raphson, para ambas as arquiteturas. O que a gente percebeu é que o Goldschmidt, em ambas as arquiteturas, apresenta os melhores resultados. Percebe-se que a energia por operação tem 3 valores, porque o algoritmo de Point-Tompkins proposto na literatura é dependente da entrada. Avaliando a nossa melhor arquitetura, ou seja, com Goldschmidt, e a arquitetura proposta na literatura, percebe-se que a proposta na literatura ainda tem ganhos em área e potência total. Entretanto, como a nossa arquitetura do NLMS reduziu o número de ciclos de clock, nós temos um ganho significativo em energia por operação, cerca de 13,3%, comparado à literatura. Já o IPNLMS, como ele é uma arquitetura que necessita de muitos ciclos de clock, ele tem um aumento extremamente significativo na energia por operação, de aproximadamente 42% a mais do que a arquitetura NLMS proposta. Com os resultados de precisão, percebe-se que o algoritmo IPNLMS apresenta o melhor resultado de todos os trabalhos apresentados na literatura. Já o NLMS apresenta o mesmo resultado proposto em 1. A função deste trabalho é que para arquiteturas low power, o algoritmo NLMS é melhor, e o algoritmo NLMS é mais preciso. Obrigada.
Olá a todos, o meu nome é Daiane Freitas e hoje eu vou apresentar um trabalho que propõe uma arquitetura de hardware dedicada de alto rendimento para os filtros de interpolação do codec AV1 utilizando MCMs. O trabalho é de minha autoria, juntamente com os professores Cláudio Diniz, Matheus Grelert e Guilherme Correia. Bom, contextualizando então o assunto do trabalho, a tecnologia de vídeo é um mercado em grande expansão nos últimos anos e que requer um uso intensivo de dados. Essa tendência tem motivado pesquisadores a desenvolver compressores de vídeos cada vez mais eficientes. Dentre as propostas mais recentes, o AV1, lançado em 2018, é o codec de vídeo da Media, um consórcio de empresas de tecnologia que visam o desenvolvimento de tecnologia aberta e livre de royalties. Então, quando comparado a outros codificadores, o AV1 apresenta uma alta eficiência de compressão, o que acarreta em uma maior complexidade computacional, especialmente na estimação de movimento fracionário, a FME, onde são geradas amostras através de filtros de interpolação, originando pixels fracionários. No AV1, são definidos 90 filtros de interpolação, que são divididos em 4 famílias, e em ordem de utilização são famílias regular, sharp, smooth e bilinear. Sendo assim, o trabalho propõe uma arquitetura de hardware dedicado para os filtros de interpolação, visando o codec de vídeo AV1. Sendo assim, a arquitetura de hardware proposta neste trabalho é apresentada na figura 1 e é chamada de Sharp Filter Core. Ela é composta por kernels para cada um dos 15 conjuntos de coeficientes que compõem os filtros da família Sharp, denominados de F1 a F15, onde os filtros responsáveis pela geração de amostras de luminância interpoladas são indicados em cinza, enquanto que para gerar amostras de luminância são utilizados tanto os filtros em cinza quanto os filtros em laranja. A arquitetura recebe na entrada uma linha formada por 4 mais 8 amostras, onde 4 é o número de pixels inteiros necessários em uma linha para compor o menor tamanho de bloco suportado no AV1, e 8 representa as amostras adicionais necessárias para a zona de preenchimento. Além disso, a arquitetura Sharp Filter Core implementa os 15 filtros de interpolação Sharp do AV1, que possuem 8 taps em modo transposto, utilizando o algoritmo AGCUB MCM. Então, para a implementação dos filtros, são necessários 8 MCMs. Os filtros foram projetados com entrada de 10 bits de profundidade para suportar a primeira e a segunda passagem de dados. Finalmente, a saída interpolada é o número de amostras fracionárias necessárias para compor um bloco de tamanho 4x4, que tem saídas de 11 bits de profundidade na nossa arquitetura proposta. Usando o filtro F1 como exemplo, podemos ver que o filtro é composto por uma porção de cada um dos 8 MCMs descritos. Isso é exemplificado na figura 2, que apresenta o MCM mais simples descrito na arquitetura Sharp Filter Core. Ele recebe uma única entrada, denominada A0, produzindo, assim, vários produtos parciais na sua saída. Os sinais de saída, então, desses 15 filtros foram obtidos utilizando combinações de árvores de somas e deslocamentos. Assumindo que a arquitetura proposta processa uma linha por ciclo, então são necessários 51 ciclos para processar um bloco de tamanho 4x4 para a estimação de movimento fracionário, a FME, e 16 ciclos para a compensação de movimento, que é a MC. Partindo para os resultados, a arquitetura proposta foi descrita em VHDL e sintetizada com tecnologia de 65 nanômetros. A tabela 1 apresenta uma comparação com os trabalhos relacionados. Comparando a nossa proposta com o trabalho 1, observamos que a nossa arquitetura ocupa mais área e dissipa mais potência. Isso se deve ao fato dos filtros da família Sharp do AV1 serem mais complexos e apresentarem mais taps quando comparado aos filtros da família regular, que é proposto neste trabalho. Já a proposta 2 ocupa menos área e dissipa menos potência quando comparada à nossa arquitetura e também ao trabalho 1. Isso ocorre em parte devido à tecnologia de fabricação desse trabalho. E, além disso, a área também é aumentada porque a nossa arquitetura é projetada visando um maior desempenho para suportar tanto a FME quanto a MC, enquanto o trabalho 2 foca apenas na MC. Isso pode ser visto na tabela, onde observamos que a arquitetura proposta por Domansky processa apenas um bloco de cada vez e atinge um throughput para a ME 8,39 vezes menor quando comparado à nossa proposta. Por fim, Concluímos que o trabalho apresenta uma arquitetura de hardware dedicada para os filtros de interpolação da família Sharp do AV1, e esta é a segunda família de filtros mais utilizada no codec, o que justifica a necessidade de uma implementação eficiente em hardware. A arquitetura é capaz de processar vídeos de 3.840 por 2.160 a 30 quadros por segundo para MC, e como trabalhos futuros, planejamos implementar uma arquitetura multifiltro que seja capaz de processar todos os filtros do AV1 com alto rendimento para codificação em tempo real de sequências de alta definição. Obrigada pela atenção.
Olá a todos, meu nome é Rafael da Silva, sou estudante de doutorado no programa de pós-graduação da Universidade Federal do Rio Grande do Sul. Vou apresentar nosso trabalho titulado como a Fractional Interpolation Dedicated Hardware for VVC Motion Estimation. Eu quero começar mostrando o que aconteceu em 1 minuto na internet em 2020, pegando o exemplo do TikTok, que teve 1.400 downloads, comparado com 2021, teve 5.000 downloads, são quase 3,6 vezes mais. Além desses, temos mais aplicações que fazem uso de vídeos, Netflix, YouTube, entre outros. Todos eles suportam vídeo. Então, considerando um vídeo com uma resolução Full HD com uma sequência de 30 quadros por segundo, com uma duração de 120 minutos, para armazenar esse vídeo eu preciso um espaço de 1.34 TB, e para fazer a transmissão desse vídeo precisaria então uma banda de 186 MB por segundo. Portanto, todo vídeo que é armazenado ou transmitido na internet deve ser comprimido, porque na tecnologia atual não teria como armazenar e transmitir usando essa banda internet. Isso é feito seguindo um padrão. O padrão recente é o Versatile Video Code, o VVC. É a nova geração de padrão de codificação de vídeo internacional, desenvolvido em conjunto pela ITUT e ISO. Sucessor do HEVC, foi aprovado finalmente em julho de 2020, e ele oferece uma melhor compressão, que reduz os requisitos de dados em cerca de 50% da taxa de bits em relação ao padrão anterior, sem comprometer a qualidade de vídeo. Ele é mais versátil, oferece codificação de qualidade aprimorada para vídeos HDR, bem como para aplicativos de codificação de vídeos convencionais. Semelhante aos seus predecessores, o VVC ele usa uma arquitetura de codificação híbrida baseada em blocos. Então, o foco do trabalho é na etapa da estimação de movimento, na ME. Aqui nós temos os coeficientes dos filtros de luminância e culminância extraídos do rascunho do VVC e do software de referência ao VTM. O rascunho atual ele permite um esquema de comutação entre o filtro de meia amostra com um filtro gaussiano alternativo, que ele é selecionado através de um vetor de movimento inteiro. O padrão VVC ele usa 15 filtros FIR de 8 e 7 taps diferentes para interpolação fracionária. Então, para cada pixel inteiro, ele interpola 15 meios pixels horizontais e 15 verticais, e 225 de 1/4 de pixel, que são as amostras de segunda ordem, totalizando 255 amostras fracionárias. Aqui nós temos o top level da arquitetura proposta para os filtros de interpolação de amostras de luminância, onde temos uma entrada com uma linha de pixel inteiro que passa pelo processo de interpolação, assim como os filtros possuem saídas com profundidades de bits variáveis, chegando até 10 bits. Então, por esse motivo, a arquitetura foi desenvolvida com uma entrada de largura de 10 bits para suportar a segunda passada que extrai as amostras de segunda ordem. E, por fim, as amostras vão para a próxima etapa. O mesmo acontece com as amostras Chrome. Essa arquitetura interpola blocos 4x4 para tamanhos maiores e decomposto em blocos 4x4 separadamente. E aqui nós temos um exemplo proposto para o filtro Luma de meio pixel de precisão na versão combinacional. Foi utilizado o algoritmo HHub e com ele é possível obter expressões com número reduzido de somadores para cada TEP. Por exemplo, cada bloco multiplicador MCM recebe uma entrada com um coeficiente de acordo com a tabela apresentada anteriormente, que multiplica uma única entrada com constantes múltiplas. Somadores em vermelho aqui eles representam os somadores que são compartilhados com os outros filtros. Aqui os outros são necessários para a construção final do filtro. Para os filtros Luma foram aplicados 4 estágios de pipeline, para o Chroma 3 estágios de pipeline. Os hardwares propostos foram sintetizados em ASIC com a ferramenta Cates. Eles foram sintetizados em suas frequências máximas. Podemos ver na tabela 1 as frequências alcançadas para a versão combinacional pipeline. As tabelas 2 e 3 mostram as frequências necessárias para a codificação em tempo real de diferentes resoluções para os tamanhos de bloco 4x4 para as amostras Luma e Chroma. Que o X ele representa qual versão da tabela 1 conseguiu atingir o processamento em tempo real. E para concluir esse trabalho, eu propus uma arquitetura de hardware dedicada que explora a interpolação de amostras Chroma e Luma usando um filtro alternativo, processa vídeos de 34 por segundo em tempo real com resoluções QHD no melhor caso e 406 por 250 no pior caso para as amostras Lumas e Full HD no melhor caso e 416 por 250 no pior caso para as amostras Chroma. A arquitetura também explora o paralelismo. As referências utilizadas. Muito obrigado a todos.
Olá, meu nome é Siqueira e eu vou apresentar nosso trabalho intitulado Context and Partition Analysis of the EV1 Encoder. A apresentação será dividida nos seguintes tópicos. O processo de codificação de vídeo é essencial, porque sem ele seria impossível oferecer serviços de streaming de vídeo, tanto em demanda quanto ao vivo, como ensino à distância. Esse processo usa uma série de algoritmos que deixam os codificadores de vídeos cada vez mais complexos. Comparado ao HIVC, o AV1 é 32 vezes mais complexo. Esse aumento na complexidade é preocupante principalmente em dispositivos móveis que dependem de bateria para funcionar. E por isso que é tão importante a gente buscar a origem dessa complexidade para que ela possa ser reduzida. O AV1 tem alguns tipos de partição que são mostrados nessa imagem. O primeiro e mais comum é o split, que dele pode derivar outros blocos quadrados, que pode ser particionado com outros 3 tipos de particionamentos. O retangular, tanto horizontal quanto vertical. O four-way, que são retangulares de tamanhos de 1 por 4, que podem ser 4 linhas horizontais ou verticais. O AB, que é uma fusão do retangular com o split, que são 2 blocos quadrados com um bloco retangular, que tem 4 opções. Ou, dentro do codificador, também tem a opção de não fazer um particionamento, que é conhecido como o nome. A proposta desse trabalho é analisar as fontes de maior complexidade do codificador de vídeo AV1. Essa análise foi dividida na análise dos blocos e das ferramentas do codificador. Para fazer a análise dos blocos, a gente implementou um código dentro do codificador AV1 que faz a contagem dos blocos usados e a contagem do tempo necessário para cada um desses blocos serem testados. Aqui, a gente tem uma imagem de exemplo da saída gerada pela ferramenta do próprio AV1 que a gente usou para coletar as estatísticas das ferramentas do AV1, os tempos gastos em cada uma das ferramentas do codificador. A gente usou 6 sequências de vídeos de diferentes resoluções, com CQs de 20, 32, 43 e 55. Nesses gráficos, a gente vê a separação por contagem de blocos para cada formato de bloco. A gente vê que os blocos quadrados compõem a maior parte do vídeo. Os blocos retangulares e menores são bem raramente usados, comparado aos quadrados, e que nos vídeos de CQs mais altos, os blocos maiores são usados com ainda mais frequência do que com CQs mais baixos. Aqui, nos mesmos formatos de blocos, a gente calculou o tempo, e a gente vê que o tempo gasto nos blocos menores é muito mais alto que nos blocos maiores. E esse gráfico mostra um cálculo feito usando os 2 gráficos anteriores, de tempo e contagem de blocos, que é dividindo o tempo pela contagem de blocos. E isso mostra pra gente o tempo desperdiçado em blocos que não são codificados no final, que são testados, mas não são codificados. Nesse aqui é um CQ de 43, com vídeos da classe D. A gente vê como o tempo gasto é desperdiçado em blocos menores do que comparado a blocos maiores. E aqui com o CQ mais baixo, a gente vê o mesmo resultado, com um desperdício um pouco maior. Aqui tá em 0.4, aqui passa do 0.4. Aqui um vídeo de classe C, com também o CQ 43, tem um desperdício bastante alto, sempre seguindo essa lógica dos blocos menores, tendo um desperdício maior de tempo. Aqui com o CQ mais baixo, a gente vê que tem um desperdício ainda maior. E um vídeo classe B, que são vídeos de resolução Full HD, também com blocos menores, tendo um grande desperdício de tempo, comparado com blocos maiores. E com o CQ mais baixo, a gente vê isso mais claro, onde blocos maiores têm um desperdício ainda mais baixo do que com CQ maior. Na análise das ferramentas, nós temos as 4 principais ferramentas com maior consumo de tempo, que são 3 delas do Inter e do Intra, Motion Mode RD e Handle MV do Inter e o Handle Intra. O Motion Mode RD, ele é responsável por calcular movimentos de translação. O Research, ele é responsável pela quantização. Essa análise apresentou as maiores fontes de complexidade do codificador V1, o que pode ser um bom caminho para a busca de desenvolver soluções para a complexidade desse codificador. Para um trabalho futuro, nós estamos propondo a criação de um algoritmo de otimização para reduzir a computação necessária no teste dos particionamentos, para ser implementado no codificador V1, substituindo seus algoritmos originais. Muito obrigado e estou aberto a dúvidas.
Então, estamos de volta, pessoal. Agora, para a sessão de perguntas e respostas da segunda poster section, a última do nosso dia de hoje. E nós contamos aqui, então, com os nossos chairs, o Felipe Bortolom, Senior Engineer, na Silvaco. Seja bem-vindo, Felipe.
Muito obrigado pelo convite.
E também o professor Daniel Palomino, professor da UFPEL também. Muito obrigado pela disposição em participar como chair dessa sessão de pôster, professor Daniel. Eu, então, me despeço, passo o controle da sessão para vocês e estou aqui no backstage para qualquer coisa que for necessário.
Muito obrigado, Léo. Bom, vamos lá, pessoal. Primeiro, agradecer a presença de todos aí, principalmente dos autores que submeteram seus trabalhos. Posso dizer, né, que todos os trabalhos que eu vi aqui são de excelente qualidade. E enquanto o chat vai criando coragem, então, para mandar suas perguntas, vamos seguir a mesma logística da apresentação anterior e ir por ordem de apresentação. Então, o primeiro trabalho seria com a Patrícia, né? Boosting the Efficiency of the Harmonics Elimination VLSI Architecture by Arithmetic Approximation. Boa tarde, Patrícia. Muito obrigado pelo seu trabalho.
Boa tarde.
Boa tarde. Enquanto o pessoal, então, se anima ainda, eu tenho uma pergunta para ti. Parabéns pelo trabalho, gostei bastante da tua análise. E eu queria saber se tu poderia compartilhar um pouco mais conosco uns insights de o porquê que a arquitetura do LOBA 0 apresentou resultados melhores do que as outras abordagens, né?
Tá. O LOBA tem mais algumas categorias, além do LOBA 0. Ele faz mais algumas aproximações, só que elas não apresentaram resultados bons para aplicação, nem de área, nem de potência, então elas não apareceram naqueles gráficos. O LOBA 0 que a gente utiliza apenas 4 bits nos multiplicadores, então a gente faz uma multiplicação de só 4 bits. A diferença do LOBA 0 para o DRUM K igual a 3, K igual a 4, que também está ali na mesma... Praticamente eles são muito semelhantes em resultados. O DRUM igual a 4 apenas utiliza uma aproximação no último bit igual a 1, e o LOBA não faz isso. E para a nossa aplicação, o LOBA, como ele não fez isso, ele trouxe melhores resultados. E porque ele é melhor que... Se tu for analisar, eles dois fazem a mesma coisa, utilizam 4 bits. E qual a diferença deles dois? Que são os principais que são mais parecidos, por isso que eu estou te explicando eles dois.
Claro.
O LOBA faz... a varredura para encontrar o bit mais significativo é mais simples, o que mostrou melhores resultados. É o jeito que ele faz o rounding para encontrar o bit mais significativo igual a 1.
Perfeito, muito bom. E nesses teus resultados, o que tu acredita ser a razão do DRUM ter elevado, né, o MSE dele tanto em comparação aos outros?
O K igual a 3, por exemplo, que
Exatamente.
tá lá em cima. É porque aí, como eu tô só usando 3 bits e ainda eu tô aproximando... tá dando eco meu microfone, né?
Um pouquinho.
Tá, desculpa.
Não tem problema.
Peraí. Melhorou?
Melhorou.
O K igual a 3 tá dando eco igual. K igual a 3 usa só 3 bits. Então, para aplicação, por ser poucos bits e ainda aproximar o último por ele acabou apresentando piores resultados.
Entendi, muito bem. Daniel, você também tem alguma colocação que gostaria de fazer?
Na verdade, eu tenho uma dúvida, assim, porque a gente acaba utilizando o mean squared error ali para medir a qualidade, né, do teu multiplicador, e eu queria saber se, na verdade, vocês não pensam em avaliar isso dentro de uma aplicação um pouco mais completa, onde este kernel é utilizado, né, e aí ver, de fato, qual é o impacto na qualidade de uma aplicação um pouco de mais alto nível, né, com este kernel sendo utilizado lá dentro. Não estamos te ouvindo.
Eu tava com eco, acabei desligando. Eu não entendi a tua pergunta, desculpa.
Não, é que assim, eu vi que, por exemplo, a tua medida de qualidade é o MSE. Mas, eventualmente, onde esse kernel que tu fez sua arquitetura e tal vai ser utilizado, pode ter um outro efeito, né?
Nós avaliamos mais métricas. É que no pôster eu só trouxe o NSE. A gente usou outras métricas, só que eu preferi apresentou diferenças mais significativas foi o NSE. Por exemplo, para a aplicação, a gente faz FFT, e aí a gente enxerga realmente os sinais foram eliminados.
Perfeito.
Bom, a gente tem pouquíssimo tempo para perguntas, então agradecer a Patrícia. Vamos passar para o próximo autor. Então, o próximo trabalho é da Morgana, Energy Efficient Wavelet Heart Transform Architecture for Respiratory Signal Processing. Então, boa noite agora já. Então, Morgana, muito obrigado pelo trabalho, parabéns por ele. O chat, né, repetindo, ainda continua envergonhado. Eu tenho uma pergunta que é muito impressionante esse teu resultado, né, parabéns por eles. E eu gostaria que tu comentasse um pouco sobre a economia de energia em comparação ao estado da arte, porque ela é bem expressiva, né? Algum outro trade-off que a referência tenha, vamos dizer assim, em vantagem ao teu sistema, ou realmente o outro trabalho não explorou muito a questão de consumo energético?
Vocês me escutam bem?
Sim.
Tá. Então, primeiramente, boa noite, né? A minha arquitetura, né? Então, de acordo com a literatura, né? A arquitetura da literatura utilizava uma RAR, né? Que não era da família, uma double chip, perdão, que não era da família de RAR, né? Então, ela utilizava wavelets que não eram RAR, né, com nível M igual a 5. Quando eu testei a M igual a 5, né, claro que eu fiz diversos testes, mas a M igual a 5, ela tinha tanto os níveis de decomposição que me davam, né, do D1 até o D5, me davam as frequências patológicas, né, dos sinais respiratórios, e no coeficiente de aproximação, por coincidência, né, dava faixa ruidosa, né? Assim, a gente não precisou criar uma arquitetura nova só para explorar, né, a faixa ruidosa, né, tirar essa faixa ruidosa dos sinais respiratórios, né, que era uma arquitetura bem grande, né, pro então estado da arte, né? Então, eu acredito que por isso, né, que a gente conseguiu até 1,8 vezes melhor uma dissipação de energia, né? Consumo energético, uma melhora de consumo energético.
Sim, realmente é bem expressivo o resultado de vocês. Também aproveitando, entre as arquiteturas que tu, né, tuas variações que tu explorou, tem alguma outra dessas variações que seria interessante em outra aplicação? Ou em algum outro cenário?
Tá. Então, a gente já publicou diversos papers com N utilidades para a RAR, né? A RAR, ela é uma ferramenta poderosíssima, né? Então, quando a gente explora uma RAR 3, a gente pode estar explorando sinais cardiológicos, né? De ver as frequências cardiológicas, já uma RAR 4 já consegue classificar os batimentos cardíacos, né? Uma RAR, agora eu estou trabalhando numa RAR, né, para processamento de imagens criptográficas, né? Então ela funciona em qualquer, vamos dizer assim, em qualquer meio que ela suporte, né? A RAR é extremamente poderosa e tu sabendo lidar com ela, ela se comporta extremamente bem para a tua aplicação.
Perfeito. Muito obrigado. Deixa eu conferir o chat se tem alguma pergunta aqui. O pessoal ainda não se animou muito. O tempo aqui é curto, então vou agradecer a Morgana mais uma vez. Muito obrigado, Morgana, pelo seu trabalho e parabéns pelos teus resultados.
Muito obrigada.
Percebo que no chat tem uma pergunta aqui também para a Patrícia que passou. Vou pedir que depois vocês possam entrar em contato também com os autores, né, e fazer suas perguntas. Infelizmente, nosso tempo é curto para cada autor aqui. E vamos seguir com o próximo, que é o Túlio, um trabalho de High Throughput Architecture for the AV1 Arithmetic Encoder with Open Source EDA Tools. Boa noite, Túlio, tudo bem?
Boa noite, tudo bem.
Bom, vou eu fazer mais uma pergunta novamente, né? Sou um chair curioso. Parabéns pelo seu trabalho. Eu vi que, pelo que eu entendi, o objetivo principal é explorar as ferramentas de open source no seu trabalho, correto?
Sim, exatamente.
Então, primeiro de tudo, eu queria uma pergunta bem simples e mais filosófica, que é, eu queria que tu compartilhasse teus insights sobre o uso dela, o que elas diferem na dificuldade, ou quem sabe uma facilidade, em relação às ferramentas comerciais. E também já aproveito para engaixar uma pergunta de como tu acha que seria interessante de incentivar mais o uso desse tipo de ferramenta.
Ok. Então, eu me graduei na Unipampa em Bagé e eu sentia muito a falta de mais ferramentas, porque a maioria das ferramentas que a gente tem hoje em dia são pagas e é um preço bem salgado. E para universidades menores e pequenas, isso é difícil. Então, eu aprendi na teoria, com o meu co-orientador agora, o professor Fábio Ramos. Eu aprendi muito na teoria, a parte do ASIC Flow, mas eu nunca tinha pego na prática porque eu não sabia de ferramentas open source e eu também não tinha acesso a ferramentas pagas. Então aí eu acho que as ferramentas open source vêm em grande peso porque elas ajudam a gente a realmente aprender na prática, que é o que eu gosto, e entender como as coisas funcionam melhor. E acredito que a maior facilidade, na minha opinião, sobre as ferramentas open source, principalmente OpenLane e OpenRoad, que eu expliquei a diferença na apresentação, é que eles são bem documentados. Tem um tutorial muito bom. As experiências que eu tenho com ferramentas pagas da Cadence, por exemplo, a gente escreve o script, a gente faz as coisas, tudo, e joga lá. Então, é difícil para começar. O passo inicial, uma ferramenta da Cadence, eu acho que é mais difícil. Agora, as ferramentas como o OpenLane, ele tem um script já pronto. Tudo bem que tem como modificar ele, tem como explorar e aumentar a performance do sistema, mas ele já é fácil de iniciar. E eu acho que essa facilidade já traz todo mundo para usar, para querer usar mais isso e ter acesso a isso.
Uma boa resposta.
Túlio, eu tenho uma pergunta rapidinho. Na verdade, eu quando lia o título do teu trabalho, eu imaginava alguma coisa na linha dos desafios de projetar codificador aritmético em hardware, né? Que tem aquela questão de dificuldade de paralelismo, enfim, de extrair paralelismo ali, né? Para a gente conseguir rodar, executar muita coisa em paralelo nos datapaths. E aí tu acabou indo mais para essa linha de avaliar ferramentas assim, open source, digamos assim, né, que sejam grátis. Pergunta assim, tu não acha que vai ser um desafio, eventualmente, utilizar essas ferramentas quando tu for comparar teus resultados com a literatura? Justamente porque normalmente o pessoal não utiliza esse tipo de ferramenta, né? E pelo que tu mostrou nos seus resultados, isso é bastante discrepante do que pegar uma ferramenta comercial.
Sim, eu concordo plenamente. A gente tem uma perda muito grande, inclusive a arquitetura, usando as ferramentas open source, ela não atingiu vazão mínima para 8K, para codificação em tempo real em 8K. Então, isso é um problema, realmente. É complicado, mas a ideia foi fazer uma análise das ferramentas open source em si. E em questão do paralelismo, o paralelismo sempre é o ponto que não tem muito o que fazer ali. Agora a gente está trabalhando numa proposta para vamos começar do início. No AV1 a gente tem basicamente dois tipos de operação, CDF e Boolean, e a gente está montando uma proposta para usar uma paralelização de um lado, que seria o Boolean. Então, paralelismo é sempre um desafio.
Muito obrigado, então, Túlio. Vamos
Obrigado, Túlio.
Passar para o próximo trabalho, que é o trabalho da Bruna, com o título de Interpolation Filter Design Using Multiplierless Constant Multiplication. Vamos aguardar um pouco, ver se a Bruna está aqui conosco, ou algum dos outros autores do trabalho. Ela não está com problemas técnicos, vamos tentar resolver isso, né? Com o pessoal aqui do backstage. Enquanto isso, eu vou tentar passar para a próxima pessoa, para nós aproveitarmos bem nosso tempo aqui, que é um pouco curto, e depois voltamos para a Bruna. Vamos então para o Pedro, com o trabalho titulado de Architectural Exploration for Energy Efficient Fixed Point Kalman Filter VLSI Design. Boa noite, Pedro. Tudo bom?
Boa noite a todos, tudo bem?
Primeiro, gostaria de parabenizar pelo trabalho, agradecer pela sua contribuição. Deixa eu dar uma olhada no chat para não ignorá-lo e ver se há alguma pergunta. Bom, eu sempre tenho uma pergunta aqui, né? Cara curioso. Eu vi que tu, né, na tua apresentação, tu identificou o gargalo do teu sistema, né, que é muito importante. Então, eu gostaria que tu compartilhasse conosco alguns insights do que tu poderia melhorar, né, nesse teu sistema, que até já envolveria, quem sabe, um trabalho futuro teu aí para melhorar a performance do sistema.
Sim. O gargalo que a gente observou foi como eu falei ali, né, na equação do ganho de Kalman, onde ela executa várias divisões matriciais, né, a cada iteração do filtro. Então, a principal arquitetura, o principal operador ali que torna o gargalo é o divisor. Então, esse é o principal ponto que a gente pode observar. Nesse trabalho, a gente já utilizou um divisor próprio, uma arquitetura de divisor próprio, já para tentar apresentar os melhores resultados de velocidade de processamento, certo? Mas queremos, então, implementar outros tipos de divisores mais rápidos e até mesmo aproximados, para a gente poder ver qual será a sua interferência no todo o sistema, né? Para ver se a gente consegue aumentar a velocidade de processamento e reduzir a potência.
Sim, porque no teu trabalho tu já fez uma exploração bem extensa, né, de projeto, né, explorando vários formatos, né, de semi-paralelo, paralelo sequencial. Então eu fiquei curioso para saber o que mais estaria faltando. Eu também quero aproveitar esse... Pode falar?
Desculpa.
Não, pode falar.
Nesse trabalho a gente tem um grande leque de oportunidades para variar, até porque como a gente está trabalhando em operações matriciais, então temos vários tipos de operações, né, níveis de operações. Então a própria divisão aqui a gente está usando pelo modo analítico e sim, temos várias inversões matriciais aí mais rápidas e eficientes para implementar dependendo do tamanho do sistema.
Perfeito. Exato, eu tive que passar a palavra.
Isso, eu ia fazer uma perguntinha rapidinho aqui, né? Quando a gente vê exploração no título dos trabalhos, a gente imagina que vai ter uma discussão sobre as diferentes possibilidades de implementação que eu vi que tu explorou ali, né? Por que eu resolvi escolher uma para mostrar os resultados e não, eventualmente, mostrar o resultado de várias ali para discutir, olha, neste caso onde eu preciso de latência, ou neste caso onde eu preciso de throughput, ou neste caso onde eu preciso de, enfim, de low power, eu vou escolher tal solução.
Bem colocado.
Certo. Quando a gente fez esse trabalho, a gente não tinha encontrado na literatura ainda trabalhos relacionados a isso, então, pelo que a gente observou, foi o primeiro trabalho em ASIC, que implementa o filtro de Kalman completo, e a gente, nesse primeiro momento, a gente tentou apresentar o que apresenta os melhores, a combinação dos melhores resultados. Como eu apresentei ali na tabela, né, que são vários resultados, vários valores e várias combinações possíveis, ficaria bem mais extenso e começaria aí a outras situações de implementações, certo? Então, como a gente está falando de uma implementação ASIC com baixa potência e reduzida área, em alguns momentos ter uma arquitetura totalmente paralela, como, por exemplo, em que vai ter uma elevada um elevado circuito com grande potência, não seria muito viável. Mas sim, é um próximo passo a se ver, fazer todas as combinações possíveis para a gente poder apresentar diferentes circuitos, né, para diferentes aplicabilidades.
Tá bem, obrigado.
Então tá. Muito obrigado, então, Pedro, pelo teu trabalho. Vamos voltar para a Bruna, então, que fez o trabalho Interpolation Filter Design using Multiplierless Constant Multiplication. Boa noite, Bruna.
Boa noite. Boa noite.
Tudo bem? Muito obrigado pela sua submissão e parabéns pelo teu trabalho. Eu tenho uma pergunta para o teu trabalho, que é, eu gostaria de perguntar quais são os próximos passos, primeiro, né, para o teu trabalho, e se você considera avaliar esses resultados que tu teve, também com um fluxo ASIC, né, para ver o potencial do que tu confeccionou.
Bom, para os próximos passos, na verdade, eu estou trabalhando junto com uma outra pesquisadora, né, uma doutoranda, e a gente está pensando em fazer uma arquitetura multifiltro para poder utilizar todos os filtros suportados pelo AV1. Então, a princípio, o meu trabalho é só de uma das famílias de filtros, né, mas são 4. Então, a princípio, seria para implementar todos eles. E sobre a síntese ASIC, o problema foi um pouco de aprendizado, no meu caso, né, porque eu sou da graduação ainda, então aí eu tive que aprender o fluxo todo. E esses aí também seriam um dos próximos passos que eu faria para minha arquitetura.
Legal. Bruna, rapidinho, não sei se tem mais uma pergunta, Felipe, não quero te interromper.
Não, pode, por favor, pode pegar a palavra.
Como tu está iniciando aí, não sei se tu já discutiu com a tua colega, né, que faz o doutorado aí, se vocês consideraram procurar ali naquelas equações a eventual existência de quando a gente faz multiplicações e somas, né, para as filtragens, ali, eventualmente a gente detecta algumas operações que são comuns entre os diferentes filtros e tenta fazer algum tipo de reaproveitamento. Não sei se vocês discutiram alguma coisa nessa linha.
Sim, a gente até discutiu sobre isso, só que primeiro a gente ia tentar juntar eles todos como se fossem arquiteturas independentes, né? E depois tentar reutilizar alguma parte do circuito quando for possível para paralelizar o que der, né?
Entendi. Obrigado.
Muito bom. Bruna, eu vou aproveitar e fazer uma pergunta. Eu não sou muito da área de processamento de vídeo, então quem sabe seja uma coisa mais trivial para a maioria das pessoas. Mas eu acho curioso, sempre, vários trabalhos na sequência, inclusive o teu, falam sobre, né, 30 FPS e nunca sobre 60 FPS. Saberia me explicar, né, o porquê que não é 60 FPS, ou se sim, como o teu trabalho pretende atingir essa marca de 60?
Bom, é que no meu caso, como foi feito a síntese para uma FPGA, então não deu muito para ter uma métrica muito certa, né? Então não deu para atingir os 60 FPS. Mas no geral é que 30 FPS é o básico para poder conseguir assistir algum vídeo, por exemplo, né? Alguma coisa que a gente consiga assistir que não tenha tanto, que não atrapalhe tanto na hora da gente entender o que está acontecendo no vídeo. Então, seria mais por isso.
Muito bom, muito obrigado. Muito obrigado, então, Bruna, pela presença. Vamos passar para o próximo trabalho. Bruna. Tu gostaria também, Daniel, de assumir a...
Pode deixar que eu assumo agora, a partir da metade para o final. Obrigado, Felipe. Tá, então o próximo trabalho é da Thalita, Exploring Approximate Computing for the Accuracy Configurable 2D Gaussian Filter. Thalita, está por aí?
Olá.
Oi, Thalita.
Boa noite.
Boa noite. Obrigado aí por mandar teu trabalho. Prazer em revê-la, né?
Prazer também.
Então, a gente tem, por sorte, a gente tem duas perguntas aqui do chat. O Matheus pergunta para ti, né? Deve ter visto ali se vocês pretendem testar o desempenho da proposta em alguma aplicação prática, né?
Sim.
Então, agora veio.
Assim, a ideia é, nós estamos pensando em duas aplicações
primeiramente com QR Code, né, que já era uma ideia anterior, né, conforme tu conhece o trabalho, e agora para o doutorado, então, a gente está com a ideia de alguma aplicação na parte de visão computacional, né, então eu já estou correndo atrás de pesquisar alguma coisa, assim, para aplicar o filtro gaussiano.
Perfeito. Essa pergunta estava alinhada com uma pergunta que eu tinha, então foi legal o Matheus fazer. E tem uma outra pergunta que eu sei a resposta, porque por acaso fui banca de dissertação de mestrado da Thalita, mas vou perguntar aqui, né, que não ficou claro para o Jorge se a tua arquitetura, a configurabilidade da tua arquitetura, ela é em tempo de projeto ou em tempo de execução, né?
Sim. Bom, o filtro gaussiano ele foi configurado em tempo de projeto, tá? Com observância ainda que falta a parte do módulo de controle e fazer um preditor, né? Para controlar aí o filtro.
Então é em tempo de projeto que tu configura aqueles bits ali, né? Para conseguir eventualmente ter arquiteturas diferentes. Só para complementar ali o que o Matheus falou, né? A gente discutiu isso lá na tua banca de mestrado, essa questão do PCNR ser o teu resultado, né? É um pouco complicado justamente porque o PCNR usa uma referência, né? Então fica complicado se tu não tem um baseline para comparar o PCNR que tu atinge com o teu resultado ali, né? Não sei se tu chegou a avaliar isso depois da nossa discussão na banca, né? Porque a gente tinha visto ali que a perda de qualidade é meio que linear com o número de bits ali, né, que tu vai descartando, que é o clock gating, e que o valor de PCNR ali 40 é difícil de computar se aquilo é alto ou baixo, porque a referência é infinito, né? A imagem contra ela mesma. Tá bem. Não sei se o Felipe quer comentar alguma coisa, se não...
Podemos passar para o próximo. Minha dúvida era a mesma que do Jorge.
Obrigado, Thalita. Então,
obrigada.
Responder aqui o teu trabalho. O próximo trabalho, então, é da Patrícia. Fixed Point, algumas siglas aqui, Biomedical Hardware Architectures for Fetal Signal Processing. Patrícia, novamente, com a gente aqui, para responder as perguntas. Eu não sei se tem alguma pergunta, acho que só a pergunta do trabalho anterior, né? Então, eu tenho aqui uma pergunta para ti, deixa eu me achar aqui nas minhas anotações. Então, assim, tu tem uns resultados interessantes ali, eu na verdade queria entender, assim, qual é a inovação no desenvolvimento da tua arquitetura que tu entende que proporcionou os resultados ali de redução de energia.
As siglas, vocês me escutam? Acho que não. Espera aí.
Agora tá mudo.
Isso.
Agora sim.
Tá. A diferença dos nossos resultados é exatamente as siglas estranhas. São os filtros adaptativos que a gente implementou. Eles são um pouco mais complexos em arquitetura de hardware, mas eles apresentam melhores resultados do que o LMS, que é o Last Mean Square, que é bem popular. Dos filtros adaptativos é o mais popular. Então, essas mudanças das siglas, o N, que é o normalizado, o IPNLMS, que é o Improved Proportional, oferecem melhores resultados na extração do sinal.
Sim, então dá para a gente dizer e atribuir assim, os teus bons resultados com aquela avaliação em software que tu fez com os parâmetros dos filtros e aí tu escolheu.
Exatamente, com a variação e com a escolha dos algoritmos.
Legal. Felipe, tem alguma pergunta?
Sim, eu tenho uma dúvida. Uma dúvida, quem sabe, mais prática. Na tua conclusão, tu comenta que uma das arquiteturas, né, ela é mais interessante para ser usada com a tua aplicação, né, que é o Fetal Electrocardiogram. Mas tu também comenta que a outra é mais precisa. E aí minha pergunta que fica não seria mais interessante, ou seja, não é mais crítico tu ter uma precisão maior para esse tipo de aplicação?
É que a diferença é muito pequena. Existe uma diferença, sim, só que, por exemplo, assim, a diferença em número de picos de frequência cardíaca para realmente medir a frequência cardíaca fetal, o EPNLMS pega um pico a mais. Então, se tu for...
Muito pouco.
É muito pouco. Ele tem diferença, ele deixa o sinal mais limpo, sim, ele deixa o sinal mais limpo, ou seja, o batimento cardíaco mais claro, mas pensando em... a forma de onda do FCG, mas pensando em contagem de batimentos cardíacos, a diferença é mínima, porque o sinal é muito lento. Porque o sinal, o IPNMS é muito bom, só que a aplicação, a frequência que o sinal varia é lenta, então tu não nota tanto essa melhora do algoritmo mais complexo.
E aproveitando esse teu gancho, em qual outra aplicação, então, tu acha que seria relevante usar o IPNLMS?
Por exemplo, a gente já testou ele em sinal de EEG, que são sinais que são mais rápidos do que o ECG, porque a questão dos picos, tu tem que fazer uma leitura e ele apresenta bons resultados. Só que também aumenta a complexidade computacional, porque ele é mais complexo. Então, sempre esse trade-off, exatamente.
Com certeza. Muito obrigado, Patrícia.
Obrigado, Patrícia. Patrícia, só uma última dúvida. Eu estive na tua banca de TCC? Ou eu estou confundindo?
Sim.
Ah, tá. Então é um prazer te rever. Até mais.
Prazer.
Obrigado. Vamos passar para o próximo, então, pessoal. O próximo trabalho é da Daiane Freitas. High Throughput Hardware Architecture for Sharp Interpolation Filters of AV1 Codec Using MCM. Olá, Daiane. Tudo bem? Muito obrigado aí por mandar o teu trabalho aí para nós e discutir com ele, discutir o teu trabalho aqui no nosso evento. A minha dúvida é qual a estratégia, assim, se é isso, né, a motivação dos resultados lá de modelagem da arquitetura, né, que possibilitou tu chegar nos resultados que tu chegou em relação aos trabalhos relacionados ali, né, porque tu diz, claro, tu tem uma diferença dos trabalhos relacionados, que o teu é um filtro que não é igual ao trabalho 1, e não é todo igual ao trabalho 2, porque o trabalho 2 implementa todos, né? Mas eu queria entender ali qual foi a diferença na modelagem de arquitetura ou na implementação da arquitetura que possibilitou chegar nos resultados. Okay. E se ela teve um foco, né? Se tu focou em low power, se tu focou em altas taxas de processamento.
Sim, o nosso foco foi a alta taxa de processamento. E a diferença realmente, na realidade, ali nos trabalhos relacionados, realmente a comparação não é justa, né? Com nenhum dos trabalhos. O nosso objetivo era ter um alto processamento e como, na realidade, uma discussão assim, do trabalho ao todo, a gente teve uma dificuldade muito grande de encontrar projetos de hardware com a V1. Então, por isso que foram encontrados esses trabalhos, foram utilizados esses trabalhos, né? E o regular, ele tem uma diferença exatamente porque o filtro é diferente, tem taps diferentes, coeficientes, número de taps diferentes, coeficientes diferentes. Então, os resultados também são diferentes. E o segundo trabalho relacionado tem um foco na MC, né, que requer menos processamento, então os resultados também são diferentes, mas eu acredito que, comparando com esse trabalho específico, que a estratégia que foi utilizada diferente, talvez é que o autor, se eu não me engano, ele utilizou algum aproveitamento de hardware, né, porque o AV1 tem uma característica ali dos filtros semissimétricos e ele explorou isso, e a gente não fez a nossa arquitetura, de repente até pode ser explorado futuramente.
Perfeito. E nessa linha de um objetivo para a arquitetura, assim, foi de altas taxas de processamento ou ela foi focada em alguma questão de low power? Foi mais para atingir?
A princípio, com a alta taxa de processamento.
Tá,
até perfeito. A gente tinha uma versão anterior da arquitetura que tinha um processamento um pouco maior, porque a gente utilizava um paralelismo maior na entrada da arquitetura, só que depois a gente percebeu que com aquela zona de preenchimento ali que eu citei, existia um overlapping ali no paralelismo, e aí então a gente utilizando só 4 pixels na entrada, 4 pixels inteiros.
Perfeito, entendi. Felipe, quer fazer algum comentário?
Eu tinha exatamente a mesma dúvida que tu teve, Daniel, sobre a comparação.
Perfeito. Ótimo, então. Então, eu tô de olho aqui no chat, né? Acabei não vendo nenhuma pergunta para a Daiane, então a gente te agradece, Daiane, por ter teu trabalho novamente com a gente aqui, tá? E vamos passar para o próximo. O próximo trabalho é do Rafael da Silva, a Fractional Interpolation Dedicated Hardware for VVC Motion Estimation. Rafael, está por aí?
Acredito que o Rafael não entrou. Acho que a gente pode aproveitar o tempo.
Não entrou?
Por enquanto não. Quem sabe ele entra daqui a pouquinho. Vamos passar para o próximo, então.
Tá, perfeito.
Daniel.
O Matheus, eu sei que está por aí. O Matheus Garelli, qualquer coisa, ele entra daqui a pouco aí novamente para tapar o buraco. Tá, o próximo então é o Ícaro. Ícaro Siqueira. O Ícaro, então, o trabalho dele é Complexity and Partitioning Analysis of the AV1 Encoder. Tudo bem, Ícaro? Muito obrigado aí por participar da sessão de perguntas e respostas aí. Eu tenho umas perguntas para ti rapidamente, assim. Uma é mais metodológica, né? Se tu considerou, ali não ficou claro para mim nem na tua apresentação nem no pôster, se tu considerou codificações em uma ou duas passadas usando o AOM. Tu usou a AOM ali, né? Nos teus experimentos.
Foi o AOM.
Foi em uma ou duas passadas, sabe me dizer?
A gente usou a configuração padrão mesmo da V1 com as duas passadas.
Com as duas passadas, né? Que se eu não me engano, as duas passadas é a configuração padrão. Eu acho que isso eventualmente pode ter algum impacto nos teus resultados, porque a configuração em duas passadas faz uma primeira passada para colher, enfim, features ali da imagem que vai ser processada e aí acelerar o processo de codificação, né? Pelo que eu conheço do AV1, me corrija se eu estiver errado até, mas esse é o meu entendimento. E que isso pode eventualmente ter afetado um pouco os teus resultados ali, né? Porque se tu rodar em uma passada só, provavelmente os teus resultados de eficiência de compressão vão ser melhor e talvez aquela tua distribuição de tamanhos de bloco não seja a mesma. Então, uma sugestão aí é que talvez valha a pena olhar isso. Tá? E a segunda pergunta é se vocês chegaram já... Tu levanta, assim, uma ideia de que, eventualmente, os blocos menores não são tão importantes. Né? Dá para tirar isso de conclusão ali do teu trabalho. Queria saber se vocês chegaram a dar uma avaliada em eficiência de codificação, deixando de avaliar alguns tamanhos de bloco pequenos.
No AV1 a gente ainda não fez essa análise, mas pelo menos para outros codificadores a gente vê que tem um grande aumento no bitrate do vídeo, né? Então acredito que vai se manter esse padrão. Ele é pouco usado, mas acredito que ele vai ter um impacto bastante grande se só remover esses particionamentos, assim.
Sim, legal. Até porque essa não é a ideia de vocês, né? A ideia de vocês é ter um algoritmo que faça isso de maneira inteligente. Isso principalmente porque a gente já aprendeu aí bastante tempo na área de vídeo que errar, né? Eventualmente não usar um bloco pequeno pode ser muito danoso, né? Se a gente escolher um bloco grande para uma região que é ruim. Tá bem? Não, legal, parabéns pelo trabalho aí. Felipe, tens alguma pergunta?
Tenho uma dúvida que vai mais ou menos na linha do que tu comentou, né? Mas eu quero também dar a palavra pro Ícaro comentar. Primeiro, parabéns pela tua análise, achei bem legal ela. Acho que ela é um princípio de qualquer projeto, né? Uma ferramenta, que nem tu comentou na conclusão, uma ferramenta de insights. Então, eu queria saber quais são os teus insights com essa análise e que mais especialmente para o projeto, né, de hardware, e como tu pretende, ou alguém do teu grupo pretende utilizar esses resultados que tu extraiu.
Então, a nossa ideia, né, de usar esses resultados foram para mostrar a importância do algoritmo de decisão inteligente, né, e a gente vai tentar desenvolver um algoritmo mais eficiente e a ideia é que sim, a gente use um que seja mais amigável para transformar em hardware depois, né, para passar para uma linguagem de hardware, para poder fazer essa otimização.
Em nível de particionamento primeiro, né?
Isso, nas decisões de particionamento. Uma machine learning para decisões de particionamento.
Perfeito. Muito obrigado.
No chat não temos nada, então te agradecemos, Ícaro, e vamos ver se alguém toma o papel do Rafael para o trabalho anterior.
Olha eu aqui.
Matheus é o cara que se esqueceu de avisar, achei que tinha acontecido de novo, esqueceu de avisar o aluno na sessão anterior, agora não foi o caso.
O Rafa sabia, ele estava aqui.
Sabia.
Acho que ele foi buscar a esposa dele e aí está em trânsito ainda, não deu certo.
Sempre bom te rever.
E também.
Eu tenho umas perguntas aqui que eu anotei, tá? Então, primeiro, se na arquitetura não ficou muito claro na apresentação, se tem alguma estratégia de redução de consumo de energia ou ainda isso não foi pensado?
Não, ainda não. A única estratégia, de fato, é usar o MCM ali para reduzir, né, para achar uma forma eficiente de modelar os multiplicadores com somas e deslocamentos, né, Daniel? Mas a ideia, na verdade, nem é muito redução de consumo energético. A partir disso, agora, é aumentar o throughput para que a gente consiga ter ali um desempenho melhor para vídeos de alta resolução, por enquanto, né? E aí, claro, à medida que o Rafa amadurece essas questões de hardware do doutorado, a gente consiga também trazer técnicas low power e low energy para melhorar mais ainda, né, nesse eixo de otimização.
Pois é, isso meio que já respondeu, a minha segunda pergunta estava alinhada com essa, porque eu vi ali filtro alternativo, né? Em que linha isso é alternativo? Não está previsto no codificador? Essa parte eu não
Como
entendi.
eles chamam, que na verdade a arquitetura ela é para todos os filtros ali, né? Só que além dos filtros tradicionais que a gente está acostumado, do HEVC, o HEVC tem mais um filtro que eles chamam de alternativo.
Ah, perfeito.
Que é aplicado lá no precisão half pixel em alguns casos específicos, assim, não é em todos os casos, mas é um filtro que as arquiteturas novas de VVC agora para interpolação vão ter que adicionar mais esse filtro ali na etapa de interpolação, porque ele faz parte do processo e por padrão ele é ativado, né, ele é utilizado. Então por isso que tem ali o filtro alternativo a mais. Né?
Eu não estava familiarizado com tanto detalhe com os filtros, eu achei, opa, os caras parecem que decidiram usar um filtro diferente e pode ser legal aqui. Tá, é a nomenclatura mesmo.
Exato.
Tá, e só assim, mais filosófica pergunta, assim, né? Esse aí é legal até o Rafael acompanhar ali.
Essas perguntas são boas para os alunos.
Mas filosofar com um cara que já está bastante tempo na área vai ser meio... Mas é bom, sempre fala as questões legais. Assim, que a gente tem, desde o HD64, muitas arquiteturas na literatura que falam sobre filtragem, né? E, ultimamente, claro, tem vindo os padrões novos, com novos desafios de filtro, que tem na complexidade dos filtros ali, aumentado o número de taps, adicionado mais filtros, enfim. Que estratégias de desenvolvimento de hardware mesmo, assim, de modelagem de arquiteturas que tu acha que a gente vai conseguir, que são desafios em aberto com a chegada desses novos filtros, assim, o que tu acha?
A ideia, Daniel, é utilizar o que várias pessoas têm utilizado também na área de desenvolvimento de hardware digital, né, como computação aproximada, essas técnicas novas aí que permitem que a gente, mesmo utilizando né, arquiteturas já conhecidas ou técnicas já conhecidas de modelagem, né, a gente consegue também trazer esse temperinho a mais aí para deixar o hardware trazer um hardware diferente, né, e trazer desafios diferentes também, né, como aproximar um filtro, por exemplo, esse é um dos desafios do Rafa, né, como é que eu vou aproximar um filtro, né, sabendo que computação aproximada funciona bem com vídeo, né, com uma aplicação bem resiliente a erro, que tipo de estratégia a gente pode utilizar, né, e aí a partir disso vai outras questões, tipo, a gente está usando uma técnica de aproximação, tem várias formas, várias camadas ali, né, desde a aplicação até o transistor, né, para a gente explorar essa técnica. É a principal forma que a gente está enxergando nesse horizonte curto, assim, de desenvolver arquiteturas ainda inovadoras, mesmo utilizando técnicas já conhecidas e uma modelagem já conhecida.
Perfeito, legal. Felipe, tens alguma pergunta?
Não.
Então tá, agradeço o Matheus, é sempre bom discutir com o Matheus aí as coisas sobre vídeo, mas a gente está com o tempo estourando aqui, tá? Então acho que a gente passa de volta a palavra para o Alan ali, finalizar os trabalhos. Muito obrigado aí pelo convite, participar da sessão, sempre legal discutir os trabalhos aí com o pessoal da área.
Certo. Faço as palavras do Daniel e minhas palavras também.
Certo, Daniel, Felipe, muito obrigado vocês por participarem com a gente aqui no evento, de fato. A gente já caminha para o fechamento, né? O evento não é só a comissão organizadora responsável por trazer isso para vocês, é uma série de pessoas, né, que colaboram para que a gente consiga organizar, né? Então, dessa maneira, nesse fechamento, eu gostaria de agradecer os palestrantes que a gente teve hoje, né? Então, o Felipe Rosa, o professor Hussam, o professor Jimmy, o professor Jorge. Também quero agradecer todos os chairs de sessão, aqui os chairs de cada uma das talks, os chairs da sessão de pôster, né, e também os autores que consideraram o CASSW como um evento para trazer, para divulgarem os seus trabalhos, para exporem aqui as suas pesquisas em andamento, né, as suas pesquisas que eventualmente já estão finalizadas também. E, por fim, agradecer a toda a nossa audiência que acompanha o evento, que tem interesse nesses trabalhos que estão sendo desenvolvidos na área desse evento, né? E avisar todo mundo que amanhã a gente continua às 9h30 da manhã com o dia 2 do evento, né? Que teremos palestras e teremos também, ao final do dia, a sessão de post. Então, muito obrigado mais uma vez, Felipe, muito obrigado, Daniel, por ficarem com a gente até esse momento e nos vemos todos amanhã. Tchau, tchau.